Slyším.
Čau. Poslouchej, musíme odpovědět na ten mail tomu projektovému manažerovi. Jak to tenkrát bylo? Jak vy jste to říkali s tou Peťou, že to chcete udělat?
Já už jsem posílal Petě draft.
Super.
Takže už by na to měla pracovat.
Super. Jak to bylo? Vy jste chtěli to udělat nějaký separátní den?
Jo, myslím, že ten plán byl udělat to někdy v červnu.
Aha.
Ale taky už si nepamatuju přesně datum. Myslím, že Petě má právě někde poznačená.
Jo. Protože tam byla ještě jako možnost to spojit případně s tím workshopem na ten podzim jako fyzicky. Jo.
Jasně, ale já myslím, že takový ten administrativní meeting v podstatě to, co jsme říkali, že se tam potkáme s těmi zodpovědnými lidmi, bude možná lepší udělat teď online.
Dobře. Jo. Možná bude. Já teď právě nevím, jak to v tom návrhu to bylo nějak napsáno dohromady, že jo? Že vlastně tam bylo napsáno, jako, že ten kick-off meeting bude spolu s tím workshopem.
Ano, tam hlavně nebylo napsáno, nebylo napsáno vůbec nic. Tam bylo řečeno, že bude workshop, že součástí workshopu bude kick-off a žádné další specifikace.
Jo. Asi to tak nějak, jo, přesně tak. Jo. Super.
Takže jinak já to v podstatě odstartuju asi 5 minut před 9. Dám takové ty technické informace typu, ať jdou na Slido a v podstatě hlásí se normálně v Zoomu. A pak v 9 nastupuješ s oficiálním úvodem.
Jo, a v té první sekci seš ty.
Jo, v té první sekci jsem já.
Super. Já jako nevím, protože já budu mluvit ještě o tom grantu, že já možná budu mluvit díl než 40 minut, možná 50.
Že když na to přijde, tak klidně můžeš být jako úplně bez diskuze, nebo...
To ne, já tam nějaký něco mám, nějaký slidy, takže to by asi byla škoda, ale uvidím, jak to zvládnu časově.
Ale určitě bychom chtěli, ať Ulrik nastupuje potom rovnou 10, takže...
Jasný, to budu hlídat.
Jo, pokud bude místo na otázky, tak samozřejmě
určitě něco vyrobíme, kdyby měl nějaký slidy skočit.
Jasně. Dobrý.
Vy máte nějak registrované ty účastníky, jako kdo se přihlásil, nebo...
Tak máme oficiální účastníky, to jsou ti, kteří budou nějakým způsobem prezentovat, a ti, kteří budou na tom Zoomu, těch je kolem těch 60, myslím.
Jo.
A všichni ostatní jdou přes YouTube.
A to víte, kdo tam byl, nebo to je jakoby volný?
YouTube bude volné v podstatě. Jo, to jsme dali, víceméně to jsme poslali link všem těm CCA. Petr říkala, že to je adresa nějakých 300 lidí ze vším všudy. Jo, s tím, že YouTube to žádným způsobem nesleduje, takže jako musí se tam v podstatě přihlásit každý, koho to zajímá, s tím, že taky jako já jsem tím zvaným psal, a ten link klidně prostě pošíří. Jo, protože to z mého pohledu, čím víc nám tam naskočí jakoby zhlédnutí, tím to bude...
To se dá registrovat na tom YouTube.
Když se na to YouTube podíváš, tak tam uvidíš, že stream už běží, což znamená, že technicky zrovna teď nám to jako...
Přenáší.
Teď nás to tam přenáší.
Dobře, tak to zase vyzkouším.
Takže
super.
Takže žádné důležité informace. Ale je tam vidět, kolik lidí to sleduje.
Jo, takže já potom asi po té přednášce úvodní napíšu tomu Janisovi, nebo jak se jmenuje, tomu projektovému manažerovi, a tím to vyřeším.
Napiš když tak Petře, ať ti pošle upravenou verzi toho, co jsem posílal, a nějak to použijí.
Tak já jdu na to.
Nazdar, kdybyste mě sem pustili hned, tak jste se mnou mohli mluvit. Čekám. Nazdar. Čau. No, říkej dotazy.
Já ti zrovna píšu, pošli
mě.
No,
já jsem slyšela celou dobu, nepustili jste mě sem, no. Co potřebuješ?
Pošli mě nějakou tu odpověď tomu chlapíkovi, jo? Protože my jsme se o tom bavili, já už si vůbec nepamatuju ty kontury. Petě říkal, že se to posune někdy na červen, ten kick-off meeting.
Jo, já mu rovnou odepíšu, jestli chceš.
Jo, to možná je fajn.
Jo.
Že se to posune jako na červen a že vlastně tady jsou jako prezentace těch účastníků v rámci toho workshopu, ale ten kick-off meeting bude se převážně zabývat logistikou toho asi grantu, že jo?
Jo, no, jako asi i tak, jo, to je jedno. Jemu jde podle mě
tam
hlavně
asi nebudou vědecké prezentace, jestli jsem to dobře.
Jako úplně asi ne, ale asi se budete domlouvat na tom, nebo oficiálně se budete domlouvat na tom, jak jako se vědecky budete... No, jak to půjde a jako jak třeba probíhají ty tréninky a systematicky, jestli vědecky ty tréninky jdou tím směrem, kterým chcete.
Určitě.
Jo. Takže takhle, teda jsme streamovaný celou dobu, jestli to nevadí, a to se pak ostříhne. Jo. Takže dobrý, takže všechno funguje, programy jsem poslala, hele, akorát, Peťo, já nevím, jestli mě slyšíš, ale Ulrich psal, že jako poslal ten link na Zoom jako svýmu týmu, tak já jsem ho ještě odepisovala, jakože Zoom je fakt jenom pro aktivní, jo, účastníky, jo, že to možná někdo jako nepochopil, jo. Takže tak uvidíme, jo. Dobrý, hele, já tady jsem jenom mám zatím vyplou kameru, budu až tak od 3/4 zhruba jako aktivně tady, jo. Hoď mi tam toho co-hosta, jestli jsi to ještě neudělal.
Jo. Jinak ještě v tom Zoomu máme rezervu v podstatě, ještě 200 lidí by se tam v případě vlezlo, ale jako nemá smysl to...
Já si myslím, že šlo o to, že oni to prostě jako nepochopili, jo, že vlastně se Zoom týká jenom aktivních, jakoby těch, kteří mluví a kteří mají postry.
Jo. Plus, že jo, je fakt, že to je taky něco, co jsme finálně se rozhodli udělat až během posledních 2-3 týdnů, takže...
Jo, jasně. No, jako já myslím, že to je v pohodě, je to normální způsob, jakým funguje Evropská komise na velké školení, takže jako v pohodě, jo. Ale jako když zjistíme, že je málo lidí, tak ještě můžeme prostě poslat e-mail po katedře, jakože kdo chce na Zoom, může na Zoom, jo, protože prostě je málo lidí, jo, to se může klidně poslat prostě, jako, jo.
Pozvánku na katedru posílala, že? Nebo...
Ty to tím musel přijít? To ti nepřišlo, když jsem to posílala včera, tam je celá katedra. Z Non-Gaussu to posílám, se podívej do spamu. Mně přišlo akorát, že to nebylo doručené asi 6 lidem a to jsou všechno zesla.
Je možné, že to bylo. Přišly mi tam nějaké v podstatě e-maily z non-disclosed recipients, takže to byl možná ten.
Jo, tak to je ono, no jasně, protože já to nemůžeš dát, že jako to je mail 313 lidem, jo.
Já vím, takže, jenom jsem se prostě, že tím, že to nebylo jasně vidět, tak jsem si uštěla.
Jo, posílala jsem vlastně jsem posílala jak se jmenuje, Pracnovi, aby věděl, a pak jsem posílala vlastně jako managementu do Dánska a do Sorbony, aby holky věděli na ten management, že se mají připojit na Zoom, a pak jsem posílala obrovský prostě těch 313 kontaktů, co máme, jakoby to jsou i katedra, SLO, je tam prostě NICT, jo, a ti všichni, kteří jste vydávali ty kontakty.
Jo? Peťo, nezapomeň potom udělat asi nějakým, abych mohl šernout.
Jo, už si kohost. A budu dávat jako kohosty vždycky ty speakery na den, takže pohodě.
Jo.
Super. Dobrý, tak já se vypínám, kluci, a jdu ještě vyvenčit psy, jo?
Čau.
Když tak jsem na mobilu, čau.
Windows XP or something like that.
Is Linux difficult in use?
You can, it's possible to make a live USB stick. So
We have to start. You probably don't.
Hi everyone. Hello Radim.
Hi, Julian.
Good to see you.
Hello, good morning.
Exactly.
Morning, everyone.
Hey, Nicolas. Good to see you, Petre.
Perfect. Thank you.
Okay, so good morning, everyone. I'd like to welcome you here, both you in the Zoom chat and you watching us through YouTube. Before I give floor to Radim Philippe to officially start the workshop off, I just have a few technical notes. First, when asking questions, you here in Zoom, please use your hands up emoticon to signal you want to ask, and so that we can process it, because there will be quite a number of you. And of course, people watching YouTube, but also people watching here from Zoom can also use the Slido interface to ask questions and upvote questions of other participants. And these questions will be then asked, well, at the end of the talk. The chairs of the sessions will then be able to forward these sessions to the speakers and get the answers done. So this is for the technical stuff, and right now, in 3 minutes, Radim Philippe will start by giving us brief information about the non-Gaussian process, about the non-Gaussian project, and yeah, here is already the presentation starting. So in a few minutes. Okay, Vadim, please go ahead.
Yeah, very good. Hello, everybody. I would like to welcome all of you, at least in this online forum, to our first workshop, which we have in the new project, which just started 1st of January. I hope that you are all fine, despite the limitations which we have by the COVID. I hope that personally you, your families, your friends, your students are all fine. And yeah, like it will be much better if we meet face to face, if we could discuss at our faculty and enjoy a nice atmosphere. But yeah, like we are limited by the current situation, still limited. We discussed quite a lot whether we should move this workshop forward and wait until the moment when we could all of us meet. But then we decided that we actually will not do that, that we will somehow face the situation and all limitations with COVID, and we will make that workshop online. As well, we thought that, yeah, it's quite nice chance to, when we can't travel, to exchange what we did over the last practically 2 years, where we are limited in the traveling. Means I would like to first thank very much to Petr Marek, Petra Zabishova and Alisa Manukova, because they did a lot of work to prepare this online workshop, and it will never ever be possible without them, because yeah, like I am already quite busy by many other things. It means I very much thank you them for all that help in the new grant which we have. And that grant is actually quite special type of grant from European Union. The official title of that project is Twinning in Non-Gaussian Physics for Quantum Technology. It belongs to still to the program H2020, which actually was already closed. And right, I can't go further. Ah, now it works, perfect. It belongs to the
You're muted, Radim.
Yeah, thank you very much, Julian. Yeah, it belongs to the call which is called widespread, and this call is actually for new members of European Union. Although we are not anymore so new member, it's still for us, and it allows us to strengthen together with the other established research places in Europe to strengthen our research further and to make new networkings, as you will see, and in general to contribute for a more balanced distribution of research facilities and as well excellent researchers over the Europe. It belongs to the CSA, coordinating and supporting action of H2020. It will run for 3 years. And as I already said, it started this January. It's quite a well-supported project, as you could see here. It's not directly supporting the research facilities. We can't pay researchers, we can't buy new experimental equipment, but we could do a lot of other activities. And to build that project, it's as I said, it's important that one team is actually from these widening countries like Czech Republic, but as well it could be the other country. I hope that by this I could inspire some colleagues to apply for such projects. And then you need at least 2 partners. And after some discussions we agreed with Ulrich and Julian that they will be partners in this twinning project, and they will help us to improve a couple of points here in Olomouc. But as well, we hope very much that our young researchers and our experience and long-term collaboration will actually contribute to research in their laboratories. Means there are major points which we could support by this project. And I think some of them are very relevant to the general quantum information and quantum technology society. It means the main one, I would say, which is important for us in Olomouc, is that we would like to very much broaden the research profile in modern quantum science and quantum technology. We would like to enhance chances to enter the new fields, the fields in which our researchers never worked before. And this twinning project is an excellent tool to actually execute that. The other thing which we would like to improve in next 3 years is the networking with the top quantum technology laboratories, because our field changes quite dramatically from quantum science more and more to quantum technology. It means there are new laboratories which offer new possibilities, but as well new technology, but as well they are in the fields where we have limited experience. It means that we would like to enter to these new networks as well. And on the scientific side, precisely on the scientific side, we would like to improve and broaden the applicability of our theoretical research in non-Gaussian quantum physics. We recently do as well a bit more in experimental research, as you will see in that field, but still our main capabilities are in the theoretical and are on the theoretical side. And we would like to broaden the applicability of the research which we do here in the theory to the new directions and the new platforms of quantum technology. And of course, last but not least, we would like to disseminate more intensively all the outcomes we will achieve, and we achieved already, to the scientific community, and to possibly communicate about this as well to the general public. And mainly, and I believe that's very important, to young generation, to high school students, which potentially could be in short time our collaborators and people which will take over our research at some point. To run this project, we need team which is already experienced and team which is solid and which can contribute both on scientific side, but as well on the organization side. And we already have such a team. The team consists from practically 4 or 5 people responsible for the different tasks in different work packages. For work package 1, which is mainly about the training and collaborative process by which we try to exchange experimental and theoretical knowledge between Olomouc and our partners. For that work package, Vladislav Usenko is responsible. Then there is a second work package, and right now actually this event is part of that second work package. This is a work package about the workshops and summer schools, and that one will be mainly controlled by Petr Marek. The third work package, which is about the broad transfer of knowledge and expertise by expert visits, and as well by our presentations on international conferences and colloquia. That work package will be actually in the hands of Ondřej Černotík. And then, of course, not negligible part of any of such a project is administration and aspects which are connected with dissemination and communication to general public. And for that is always good to have very strong administration team, and this is in our case Petra Zabishova together with Jarka Kolashina. Like things which on the scientific side, this project plan to deliver are the new experimental proposals which will likely not only come to Lyngby and Paris, but they will as well come to other places from our theoretical team. We want to as well prepare for younger researchers a couple of reviews about the field of quantum non-Gaussian physics. And we want to as well strengthen in the grant applications and fellowships for young researchers. It means these are things which you could expect from the Non-Gauss project. And I think you are mainly interested in the international events, which you can then attend and enjoy together with us. It means today and tomorrow and day after tomorrow, we have online Non-Gauss workshop, but there will be plenty of the other events, which will be in Olomouc, in Denmark, in Lyngby, but as well in Paris. And yeah, you see that there likely will be the full, not online, normal workshop this autumn here in Olomouc. The reason is because we got funding for organizing of this workshop, for people to come and to accommodate them, and then it will be of course silly to give that funding back when we can use it for an nice event. It means this is what is planned for this autumn. We all hope that COVID will disappear completely and we will be able to meet here. If not, then we will move that workshop to another years. Then another plan still for this year, or maybe beginning of the next one, is something like a Christmas school in Denmark. I think that could be particularly attractive in that beautiful country, in the place like Copenhagen or Lyngby. And then there will be gradually other workshops in Paris next year, then summer school in Olomouc, then another workshop in Lyngby, then spring summer school in Paris in 2023, and then final workshop in the same year, which will then conclude that 3 years project. It means I think you can look forward to all these events where we will quite intensively and as well quite frequently exchange what is new in our field. And we all hope that actually that will very much contribute to advance our field. And after the 3 years, we will know much more than before, and more of the theories will be tested in the field of quantum non-Gaussian physics. It means this was something what I wanted to tell about non-Gauss, but of course I would like to as well a little bit update you about just few points from our recent results. And therefore I decided to add a bit of the scientific talk to that introductory one and extend these non-Gauss to a bit of description about new aspects of quantum non-Gaussian states, which we both investigated theoretically, but as well there are new experimental results in that field. You see, instead of the long list of the name, there is just a short word non-Gauss team. This is because the number of people which are in Olomouc interested in quantum non-Gaussian physics, in quantum non-Gaussian states, is already quite large. Of course, all of them, they don't do the same things. Their interest is quite diverse, starting from the basic research about quantum non-Gaussianity and ending by the applications of that in quantum communication, quantum sensing, but as well in new fields like quantum thermodynamics. It means it will be very hard to present all contributions from these people, both theoreticians and experimentalists. Therefore, I will just focus on few examples which I selected. Of course, that field will not rise well without experiments. And in Olomouc, over the last years, we were able to improve our experimental facilities, going from the experiments with the single photons to experiments with the quantum states of trapped ions, and as well with light emission from hot rubidium atoms. It means we already extended our experimental facilities towards quantum states and quantum non-Gaussian states of matter, but we hope that will actually quite intensively continue and improve over the years. Yeah, like we will never ever have all experimental platforms at one point. That's very expensive and more or less impossible. And therefore, we are very happy that we keep and enlarge the experimental collaboration with the laboratories, not only in European Union, but as well outside, overseas. And I think during the workshop, you will hear about that in a couple of talks and a couple of posters. Mainly, I think you will hear about the collaborations from Lyngby and as well from Sorbonne, and definitely from Akira, from Tokyo. It means, yeah, this is what is already quite well-established network in the quantum non-Gaussian states, but we try to go further and even extend this network. We started basically last year the collaboration with Yale University, and we would like to very much push further the collaborations with the new places where they have experimental facilities which we don't have here in Olomouc, and therefore we can by working together we can learn quite a lot in the new fascinating field of quantum non-Gaussian physics. Then I thought how to kind of visualize the situation in quantum non-Gaussian physics with quantum non-Gaussian states in these days. And I came to idea that maybe good to emphasize is that we actually have like two quite dominant poles of very different quantum non-Gaussian states. One pole, let's think about this like the North Pole, are states which are quantum non-Gaussian because they are pretty much limited in the Fock state basis. It means these states are like superposition of finite number of discrete Fock states. And because of that, they are by definition quantum non-Gaussian. They are very hard to simulate by the Gaussian states, by their mixture, because that mixture is always in a finite tail in the Fock state. But there are as well other states. We can think about them that they are kind of on the South Pole, and they have very different nature. They are rather superpositions of continuous variable eigenstates of position, oppositely to the discrete states here. But then the coefficients of that superposition, the amplitudes of probability, they can be in simplest form written in just this exponent of some function, which if that function is quadratic, actually brings quantum non-Gaussianity to these very different class of states too. Of course, these are, as I tried to visualize, just two extreme points, two extreme poles of the globe. And of course, there are many states here and there and there and there. And they have very different natures. They are kind of combinations of both of these aspects. And they can be quantum non-Gaussian in a very different sense, but they can therefore be very useful for various applications. But right now, we are rather covering only very little part of that space here at this globe. We don't know so much about these states. We know a bit more about this ones than about that ones, but I hope that in the upcoming years we will be able to learn much more and to realize the experimental potential of these states, and as well their possible applications to improve quantum technology. It means in the next slides I will focus rather on that discrete form of quantum non-Gaussian states when we have that sharp end of the distribution in Fock state basis. And to start, I think I should remind to all of you that there are already rising applications of these superpositions in various corners of quantum technology, in quantum sensing, as well in quantum error correction. These states, they became more frequent for quantum communications and quantum connections. There are as well considerations of these states for quantum computing, for some primitives of quantum computing, but as well they could feed quantum engines, and we can think about them in the sense of quantum thermodynamics. And certainly there will be more and more applications once these states are more and more prepared in various laboratories at diverse experimental platforms. But these superpositions, they are superposition of some building blocks. And although the Fock states are here in quantum physics already for many decades, I was personally very surprised that there is still a space and a lot of unclear points about them. And yeah, it brought us actually to their quite extensive investigation. Yeah, as I said, they are quite frequently discussed in the literature. These were states which were already the beginning of quantum optics. It means it's not surprising that they were the examples of non-classical states which were broadly investigated over the last 50 years of quantum optics. And I think this kind of slide is not basically anything new for anyone in the audience. It's just the repetition that non-classical states are these states which are incompatible with the mixture of coherent states, as it was introduced by Roy Glauber and others. And if you think about the simplest experimental test, how to verify such a non-classical aspect of, for example, single photon states, then we can think about the test of second order autocorrelation function, which is known as a G2 function, using quantum modifications of Hamburg-Brown-Twiss experiment, means HBT experiment. And then in the literature, you can find a very simple condition when such states are non-classical, written in the terms of probability of the single photon and probabilities of two and more photons. Means this is just about the non-classical aspects of the single photon state. But if you think about quantum non-Gaussianity, that condition actually changes quite interestingly. There is not only change in the prefactor, there is as well very important change in the power of probability of the single photon state. And this is what basically we found out a couple of years ago And it stimulated a lot of research, not only in the theory, but as well in experiments. We actually tested possibility to see such a single photon non-Gaussian states, even after some quite extensive attenuation. We tested that here in Olomouc in 2011. And then there was in parallel another test which was published in 2012 in Lyngby, which was done with the homodyne detector. Instead, here the test was with HBT measurement. We observed quite safely that quantum non-Gaussianity is detectable using basically at that time quite ordinary source of single photon states. But yeah, we were interested whether this is not just the specific feature of these experiments with parametric down conversion, whether we can see quantum non-Gaussian states as well as other experimental platforms. And one platform which was particularly interesting for us was emission from solid state quantum dot sources. We were able to observe quantum non-Gaussianity from this solid state source in heralded way. And right now we try to detect some similar features without the heralding. It's quite demanding, but we already know that at least in heralded way, it's detectable from solid state sources. And then we tried as well to see quantum non-Gaussianity from the emission of the single atom. We as well succeed that despite very low emission rate and very low collection efficiency. And both these experiments, they were done in Innsbruck. But we as well progressed in our lab to generate quantum non-Gaussianity from atomic sources. And you can visit the poster number 8 tomorrow and hear from Jaromír Mika the details about that. It means this is still ongoing research, how to see quantum non-Gaussian states, quantum non-Gaussian single photon states of light from such a different atomic sources. But we didn't stop in the theory on that. Our intention was to find actually hierarchy of quantum non-Gaussianity for these Fock states. This is something what is very limitedly possible if we think about distinguishing the Fock states using just the profiles and negative values of the Wigner function. It means we thought about such a simple detection method in which you, from the light source, you basically receive on some multiplex detector or multiplex detector, you receive some portion of light, and you are able statistically confirm that actually your state is distinguishable from some trivial states in that hierarchy, which are always below some threshold. It means mathematically such a definition of the hierarchy can be visualized here. You see that the formula, which looks maybe a bit more complex, but it's actually quite simple, is consisting from 3 parts, from something what we could call like core state, which is sandwiched by displacement and squeezings, which are both Gaussian operations. And the coefficients of these Gaussian operations, they can be mixed in arbitrary way using these classical probability distribution. It means here you put something what defines your core state, and based on that you jump in the levels of the hierarchy, and these core states, they can in addition be squeezed and displaced anyhow, and all these contributions could be mixed with various weights. It means that basic non-Gaussianity is that very simple case when the core state is just vacuum, and by that we exclude any squeezed, displaced, vacuum, it means any Gaussian state. The second level of the hierarchy is a little bit more sophisticated. The core state is actually arbitrary superposition of Fock state 0 and Fock state 1. And these superpositions, they can be additionally displaced and squeezed. And all these possible states you could mix as you like. And by that, you could gain states which can have very various, they can have very diverse Wigner functions, they can have negativities distributed in various ways. But apparently, if you have Fock state 2, the ideal Fock state 2, you will not be able to write this as this kind of state, or as well not as any mixture of that state. It means you can, if you find the threshold for all these states, you can distinguish something like genuine Fock state 2, and we very much look to that and extend this as well to higher levels, not only second level, but as well in general nth level, when this state is actually such a superposition up to n-1 Fock states. That problem was quite intensive analytically. It was very, very hard to solve it, but at the end we were lucky, and together with Lukáš Lachman, which did a majority of work on this during his PhD study, we came up with even analytical formula, which in a very important corner for many experiments, in the corner when basically all probabilities except the probability of vacuum are rather small. In that corner, it gives quite precisely the threshold which we need to basically surpass to observe these genuine quantum non-Gaussian features according to such a hierarchy. What is important here is that this evaluation, this hierarchy particularly, goes beyond the Wigner function and formalism and the evaluation of the negativities of the Wigner function. And actually, it happens in the two different ways. First, the hierarchy allows to observe states which could be quantum non-Gaussian, and they could jump up in that hierarchy, even if the losses are larger than 50%. It means then you see only positive Wigner functions at your detection setup, but still you could test this hierarchy. And second thing, which is as well remarkable, is there is no hierarchy like that just for the Wigner functions. It means this is the first case when we can conclusively, faithfully decide about difference between different non-Gaussian states based just on the experimental measurement. Of course, it was very tempting to test this hierarchy. Means this is what we somehow did in Olomouc here. We were not able to prepare the Fock states, but we were able to prepare states which had the statistics equivalent to the photon statistics equivalent to the Fock states. And we tested them. And these states, they were able to show this quantum non-Gaussianity up to third order of the hierarchy. Means we were able to confirm genuine quantum non-Gaussianity of states with 3 photons, as you could see here. But this was the maximum what heralded sources with parametric down conversion were capable of. It means, yeah, we need quite improvement of these sources using possibly photon number resolving detectors, and we in general hope that optical technology will go from conditional state preparation more to deterministic state preparation, and yeah, then we could use that hierarchy for much higher photon numbers and test the quality of generated Fock states. Actually, we somehow overcome that limit by beautiful step side, because we used the trapped ions experiments recently to go beyond that Fock state 3, not for photons, but for phonons. Yeah, anyway, bosons, it means it's, it's still quite something for what we can apply that hierarchy. And if you want to hear more details, then just visit the poster of Lukáš Podhora on the same day. This hierarchy, it can be applied quite broadly to the sources which are basically from parametric down conversion, from optical parametric oscillators, but as well to the sources which are from quantum dots. Like these sources, they can still very much use the fact that we can apply the hierarchy for states with positive Wigner function. I think this is quite nice. But as well, we can apply the hierarchy to another experimental platforms. As I mentioned, we can test Fock states generated in trapped ion experiments. We can test phononic states by that hierarchy. But as well, we can apply this to quantum acoustics. It means to the phononic states of quite larger systems than are just single atoms. Means, I hope that this contribution to quantum non-Gaussianity will help experimentalists to improve their experimental setups, to see more clearly the important features of the Fock states as basic elements of the superpositions which we need for the applications. But we didn't stop at that point. We as well thought, okay, once we actually test quantum non-Gaussian features of multiphoton states, we could look as well to more complex tasks, whether actually, for example, photon pairs, which we could generate, are simulable by two-mode Gaussian states. It means now the trivial states will be all possible two-mode Gaussian states, which you could imagine. Fortunately, when you solve this task, which is already by one level of the complexity more demanding than what I showed you at the last slides, fortunately, many times you find some simpler states, sometimes even two-mode squeeze states as the optimal states, as optimal Gaussian states. Means this helps you a lot to analyze the problems. And we, together with Lukáš Lachman, we succeeded really to find first quantum non-Gaussian test for photon coincidences. It means this is something a little bit higher type of the test comparing to the standard test when we measure photon cross-correlation function and decide about non-classicality of photon pairs based on that. And this is very interesting because already from 60s, we have sources in which we use a single atom and the emission of the photons from the cascade of that single atom. And these sources in this form or more modern form, when we use cascades, for example, in solid state quantum dot sources, they are in principle capable to show these, to demonstrate these quantum non-Gaussian photon coincidences. And this is right now of some intensive experimental collaboration if we will be able to see such quantum non-Gaussian coincidences. But when we talk about the multiphoton states, I would like to as well mention another approach which we pushed together with experimental team of Julien Laurent at LKB Paris, in which we tried to actually predict how well, in principle, statistics, photon statistics of multiple single photon states will allow us to, in principle, form arbitrary Fock state N. It means this task is that you have n times a little bit different copies of single photon states. You measure them very precisely, and then you apply all these measured photon statistics to computational quantifier, which allows you to predict whether these states are already so good that they will give you potentially Fox state n from that n replicas of single photon state. It means that procedure uses the process in the computer, but you can as well think about that in a more physical way, that it's like a linear network where in principle you could measure on all the outputs except the last one. And if you project all the outputs to the vacuum, then you kind of concentrate all that single photon states to just one output, and you test whether this output contains Fock state n when there were n single photon states at input. All right, we first analyzed that kind of quantifier theoretically, and we figure out quite interesting aspects. It was work together with Peter Zappel et al., which is now at VU MPL Erlangen. And we realized that actually the dependency on minimum efficiency of that single photon source as a function of the number of that single photon states is actually quite nonlinear. This was first observation. But then there was as well a second observation that if the efficiency surpasses some threshold, then actually we can guarantee, at least numerically, that there is a chance to generate arbitrary Fox state with, from such a single photon state. It means we were quite surprised how such a simple task used to evaluate quality of single photon states gives us a very different perspective than what I described you before, or what we can actually learn out of the Wigner function, or what we can see when we apply HBT measurement and evaluate G2. Of course, we were quite interested whether current states could actually reach such very high Fock state capabilities. This was the title of that feature which we wanted to test it. And we picked some numbers from experimental papers and observed that, yeah, some of the experiments, they could reach Fock state capability 7. It means if you merge these signals from 7 single photon sources, you can go to the Fock state 7 and see really the 7 negativities of the Wigner function as it should be for that Fock state 7. But then we as well saw that other sources, probably a bit better, they could reach even twice larger Fock state capability. It means from 14 single photon states, you can approach in principle Fock state 14 with really 14 negative values of the Wigner function when you look to the cut of the Wigner function along the quadrature axis. It means, yeah, this was very stimulating. And fortunately, Julian and his team agreed, and they were as well interested to test their single photon sources. The reason why that was important is that in the theory, we typically assume that our resources, here single photon states, are all basically identical. It means we kind of live in a symmetrical subspace of the whole Hilbert space. And that kind of life is comfortable. Many times you can calculate something more easily. Many times you can predict very good results, but actually in experiment, we always live outside that subspace. And that's quite important, and it's important to take this into account when we evaluate multi-copy protocols and when we evaluate basically multiple use of the resources. It means we did it for single photon states conditionally prepared from the parametric optical processes using very efficient single photon detectors at cryogenic temperature. And we realized really diversity of the possibilities. We saw that for some single photon states, we are very limited. We could go to the Fock state capability 2. Even sometimes if we see negativity of the Wigner function just a little bit, it will not help us to bunch the photons and see higher Fock states at all. We could improve these sources, and by increasing the single photon component, we could go to Fock state capability 3-4. But then, as I said, when we start to improve it even more, there is like a sudden increase of the Fock state capability. And at some point, we actually reach quite high Fock state capability, 14, as we predicted in that theoretical papers. This is all nice. We know that we right now have already quite powerful single photon sources, at least at this experimental platform. But we notice as well one point which is very good to keep in mind. And that point is that when we look to the Wigner function profile of that constructed Fock state 14 in our computer, and we compare that with the ideal Fock state 14, which was just adequately attenuated, we saw more or less perfect correspondence between the cut of the Wigner function of the real experimental state and that approximation by attenuated Fock state 14. But when we look to the distribution of Fock states, that picture changed quite dramatically. Because here, if you look to the multi-photon contribution 15, in a real experiment, there was a much, much larger contribution than actually in that ideal attenuated Fock state 14, which fitted so well in that cut of the Wigner function. It means this is another argument in the favor of this previous hierarchy, which actually analyzes these statistics rather than the negativity of the Wigner function, because that hierarchy is very sensitive to this and allows you, therefore, to categorize your Fock states much better. All right, I think we are going to the end of the talk. It was just about these basic elements, which possibly all of or majority of the talks will as well use for quantum non-Gaussian physics. But we recently moved from the Fock states to really their superpositions. And we analyze various superposition states and their non-Gaussianity given by the amplitudes of the probabilities. And yeah, we hope that soon you will hear from us about new possibilities, how to test that. But we as well extensively investigate that other pole, that south pole, where we look for quantum non-Gaussian aspects of these more continuous superpositions of states with amplitudes of probabilities, which are exponents of higher powers of x than 2. And yeah, like there are already some examples of these nonlinear phase states, the JKP states, and I think they will grow much more, especially if we are able to prepare such states in experiments. And yeah, there are already few first experiments when these nonlinear phase states actually were observed. It means, and JKP states as well. It means I think this is a very prospective field for young researchers and PhD students because it's very new and very fresh. If you want to hear about some of our attempts from our youngest colleagues, then yeah, please visit posters 7 and 10 tomorrow, and you can talk with the young people about this. Our next targets, yeah, they are very diverse and many, but yeah, they basically go from one side of quantum non-Gaussianity of photons, phonons, quantum non-Gaussian coincidences, but as well quantum non-Gaussian coherence and correlations. They go to ways how that things could help us to build optical gates for processing of quantum information, quantum applications, maybe at some point even for quantum computing. And through that, they as well continue to investigation of nonlinear, highly nonlinear quantum physics, where quantum non-Gaussian states actually appear very naturally as just outcomes of such a processes. It means there is no special way to basically think about them as we are used to right now. They just are ordinary outcomes, as now, for example, the squeeze states from optical parametric oscillators. Means this is the field which is very fresh, and I hope and we hope very much that it will grow very fast. All right, we as well we will try very much to enlarge the applications of all these states in all pillars of quantum technology, but as well beyond that in quantum thermodynamics and maybe new fields which will come. And for that, of course, we look very much for PhD students and postdocs. And we have a couple of the positions available already for the new center, which we just got from this year. Yeah, it's about quantum non-Gaussian coherence. It means it's pretty related subject. I think what is important here is actually that our field looks right now like that. We are building some picture of quantum non-Gaussian world, but we just have only few things in the puzzle, and yeah, we will see what will come up. It will be definitely interesting, definitely stimulating. There will be a lot of questions, a lot of debates, hopefully a lot of experiments. And yeah, I think this is my last slide. I would like to just wish you that you enjoy all these non-Gauss workshop. And yeah, I'm open in the last minutes for the questions.
Thank you for a very nice introduction, Radim. So now we really do have times for questions. I remind people in the call that they can ask by raising their hand. In the meantime, we have a question from the online audience. So there is a question: how can non-Gaussianity of arbitrarily squeezed and displaced states be distilled into a single condition on Fock space elements? Oh, that's a very good question, and actually very demanding question. Yeah, of course, there are papers which are addressing possibility to distill something. There are no-go theorems from Alex Złowski and Dominic Berry, which are protecting linear optics and photocounters to do that. There are papers which, as well, we have some papers that we can somehow like accumulate non-classical and non-Gaussian features to approach these Fock states. But yeah, like that point is not resolved yet. And I as well admit maybe the distillation of these features is not really the best strategy for the future. Maybe because we don't think to anyhow cancel any eavesdropper, for example, influence, as is in QKD. Maybe it's just better to work on the sources and make these sources better for the direct preparation of the Fock states, for the direct preparation of their superpositions. Yeah, because to distill, this is always costly, at least from point of view of probability of success. It means I would rather maybe orientate minds to improve the sources and improve the strategy than to distill. I hope that this is the answer which
which is stimulating.
Okay, well, that's the answer. We have another question related to a similar topic, and this is how can non-Gaussianity of arbitrary squeezed and displaced states be is there any advantage of this characterizing non-Gaussianity compared to the genuine non-Gaussianity beyond the probabilistic mixture of Gaussian states?
Okay, then maybe once more.
So basically the question is if there is inherent advantage of looking at this high order non-Gaussianity. So not just using a mixture of Gaussian states, but
yes,
mixture of Gaussian transformed low order non-Gaussian states.
Yeah, I think this is quite straightforward because if your source starts to prepare higher Fock states, then they will be all simply quantum non-Gaussian if they have sufficient quality and the multi-photon contribution n+1 and +2 is sufficiently reduced. However, you will not be able to distinguish basically whether you used just somehow the lower Fock states and their squeezed and displaced version to get the higher Fock state contributions, or you really did and invest non-Gaussian features in the right way to gain the adequate statistics corresponding to the Fock state. And it means it's like refining these non-Gaussian states to some classes in conclusive way, which is something what is very hard to see from the profile of the Wigner function and its negative values, and it's almost impossible to claim anything like that when you use just the standard formalism and measurements of G2 correlation functions or GN correlation functions.
Okay, I think that answers the question. So since there are no more questions and since time is moving, I would like to thank Radim again for his nice talk. And now I would like to invite Ulrik Andersen from Danish Technische University in Lyngby to present his talk this morning. His talk on microscopic quantum states of light and mechanics. So Ulrik, I hope you can hear us, and
I hear you.
Please go ahead and share your screen.
So thank you, Peter. So I'll start by sharing my screen as you suggest.
We still have 2 minutes, even if we want to stick to the schedule.
So do you see it, Peter?
Yeah, we see this. I mean, yeah, just the DTU symbol. So, but I suppose it's
it will be soon. Okay, all right. So welcome everybody to my talk, and I would like to thank Peter for introducing me, and also Radim very much for organizing this workshop and for coordinating this exciting new twinning program. So I'm very much looking forward to collaborate with you and your group, as well as with Julian and his group in Paris for the next 3 years. Of course, we have been collaborating for a number of years, but this will surely intensify the collaboration between our groups the next 3 years. So I'm very excited about this new program, and I'm delighted that you have invited me to join the program. Okay, so my talk is about generating macroscopic states of light and mechanics. So I put the quantum in brackets because the mechanical states are not yet in a quantum state, but we're working towards it. And I also made a subtitle, which is specifying more carefully what I will be talking about today, namely about continuous variable quantum computing. I mean, how to build such a system. I mean, focusing on the architecture and also how to reach fault tolerance at the end of the day. And then towards the end of my talk, and hopefully I'll get time for this, I will be discussing some new results on making mechanical oscillators that are also coherent and could be used in the future for quantum optomechanical experiments. Okay, so I will start my talk by showing a photo of our section that we call Quantum Physics and Information Technology, or QPIT for short. So we're about 40 people, and we have somewhat a large diversity in the group. I mean, we have many different nationalities from all over the world, which is therefore an exciting environment to work in. So we're not that many females, and that's an issue that we should work on, not only in our group, but something we will be working on in this new twinning program to make our research field more attractive to females, so we can have a better balance than what we see in our group. So we are delighted to receive funding from the Danish National Research Foundation. So they have generously supported the center running for 6 years and extendable to another 4 years, so in total 10 years. Has been running for 3 years by now, so we hope still that there will be funding for another 7 years for this program. We call it the Big Q, and the name of the center is Center for Macroscopic Quantum States, because I mean our aim is to really construct in the laboratory large quantum states of light and mechanics and use it in different applications. Okay. So I mean, of course, the core activity in our section is research, or fundamental research, with a focus on, or with a target on technical applications, because it's a technical university. But we also do some innovation. Recently, or within the last 2 or 3 years, we have embarked on many new innovation projects. We have applied for different patents, and we're now trying to translate some of our research into industry. So we are running a couple of programs where we are, for example, trying to translate the quantum communication systems, quantum key distribution and quantum random number generators into industry. In addition to this, we of course also do a lot of education, and here we have also been quite active the last couple of years in making new quantum information science programs. So we are offering 4 courses in quantum information science. We have made a study line on quantum engineering, and we also in the process of making a master program in quantum information science together with the Copenhagen University, which is very nearby DTU. Okay, and then of course we collaborate with a number of people around the world. In particular, as I already mentioned, we collaborate with the people in Olomouc, which will then be intensified the next 3 years. So you will meet some of the group members doing this workshop. I mean, Alex, I will present him on the next slide. He will give a talk later today. And then there will be 5 posters from our section, and they will be given by Frederik and Cecil on optomechanics, Nitin and Tobias on the quantum key distribution, and Jacob will be talking about, or presenting his work on how to generate non-Gaussian states. Okay, so in our group, section, we are six PIs. So Tobias is focusing his research and innovation on quantum communication, but also do some quantum sensing. Jonas is more focusing on quantum computing, but also quantum sensing. Alex, you will meet Alex later today. So he is in charge of our diamond activities, or color centers in diamond, that is being used for generating single photons, for example, but also used in magnetometry. Jonathan, he's working on quantum information theory, in particular quantum sensing, quantum thermodynamics, Ulrich is deeply involved in our optomechanical experiments, and we enjoy support not only from the Danish National Research Foundation, as I mentioned before, but also for a number of other Danish foundations as well as EU. So we are taking part in two flagship projects, Unicorn and Civic, on quantum communication. And and I should also mention that the Nordisk Foundation, which is one of the biggest private foundations in Denmark, they're supporting a large activity on quantum magnetometry. Okay, so we focus on 3 different experimental platforms in our group. So the first one, and this is the one that we have been developing over the last 15 years, and this is light. So using light for developing new quantum information technologies, squeeze light, entangled light, and single photon states of light, and other non-Gaussian states of light. We also work with mechanical oscillators for testing quantum physics. So that's at least our goal, testing the foundation of quantum physics, but also use it in quantum technology as quantum transducers, for example. So and then the last platform is Diamond, and the Diamond platform will be introduced by Alex in his talk later today. Okay, so I mean, now I have put these different platforms in independent boxes, but we are actually trying to hybridize the different platforms, and ideally we would like to hybridize all 3 platforms. So we have activities towards hybridizing light with mechanics. Of course, there's optomechanics, but we also have an activity where we try to combine spins of Diamond with mechanical oscillators, as well as we have experiments on coupling light with spins of Diamond. And then finally, towards the end of our center, we like to combine all 3 platforms. Okay, and we look into these 3 obvious applications, also very much along the pillars of the quantum flagship projects. I mean, namely using quantum information or using the foundation of quantum mechanics to enable quantum sensing, quantum computing, and quantum communication. Okay, so before really going into the details of quantum computing, which will be the main part of my talk, I will just sketch a few very recent experimental results that have been recently published in our group, or experiment by our group. So the first one I would like to highlight here is our new experiments on quantum state discrimination. So here is a very old task and a very important task, both in quantum computing and quantum sensing and communication. And here the idea is to be able to optimally discriminate different quantum states, different overlapping or non-orthogonal quantum states. So here we are considering 4 coherent states, so which is very common to use, for example, in communication, both quantum as well as classical communication. Now you want to devise different strategies by which you can discriminate these 4 states. I mean, there are different discrimination strategies or protocols. So one is called the minimum error discrimination, where you want to discriminate these states while minimizing the error. And this has been done for some years, or for some number of years now, in particular for 2 states. And it is also known that the optimal protocol for doing this is the so-called Dollender receiver, and has been implemented a couple of times. But if you want to discriminate 4 states, then it's not so simple any longer. Then the optimal protocol is unknown, but you can beat an obvious protocol. I mean, an obvious protocol would be a displacement combined with photon counting, but this can be beaten by using feedback, active feedback. So using Bayesian estimation and active feedback. So this we have demonstrated. Also, we are not the first one to demonstrate this, but we demonstrate this in the telecom range for the first time. And we have now extended this also to what we call unambiguous state discrimination. So here the idea is not to minimize the error in discriminating, but to get conclusive results. And if the outcome of your measurement is inconclusive, then you discard it. And then the idea is try to minimize this probability of unconclusive results. And this we also try to do using feedback. So people have tried to use, simple displacement operations combined with the photon counting in order to implement such a task. But we combine this with feedback and saw that you can actually improve the scheme using feedback. So here I'm plotting the conclusive result probability, which we ideally want to have to 1 as a function of the mean photon number of the input states. And if you do not use feedback, then you get the green curve here, which I refer to as m equal to 4 because we use the 4 detectors. But if you now start using the measurement outcome of these 4 detectors to adjust the measurement of the 5th detector and the 6th detector and up to 10th detector, then you can improve it. And this is what we did, and then you get the red dots here. So a clear improvement using feedback. So we're still quite far from the optimal unambiguous state discrimination, but nevertheless we have beaten the standard traditional approach. Okay, so we also do some sensing quantum magnetometry, and we do this using color centers in diamonds. So you can use color centers in diamond to measure magnetic fields. So this has been known also for a number of years, 15 years or so. And this technology has now been advanced to such a point that you can start using this in real applications. And that's what we have done in this recent report. So where we try to measure the magnetic fields from the leg of a frog. From a mouse. Leg from a mouse. It also works on a frog, but this was a mouse. And this was a mouse that was also genetically modified so that when you shine light onto it, then you activate an action potential, which will then radiate magnetic fields. Tiny magnetic fields, but that could be measured with our high sensitivity magnetometer. So the sensitivity of the magnetometer was around 50 picotesla per square hertz, and that enabled us to quite clearly see the signal from the mouse leg. Our next step, and that's what we are working on right now in the laboratory, is to try to do such an experiment on a brain tissue. Brain tissue from a mouse. Okay, so we have also been using non-classical states of light in order to improve microscopy, Raman spectroscopy. So Raman spectroscopy has developed significantly over the last 10 years or so, and commercial microscopes are now at the limit where shot noise of the probe beam limits the performance of the system. So the only way to improve the sensitivity of these, as well as the contrast and the speed of these microscope, is to either increase the power of your laser beam or to decrease the noise. Increasing the power you can of course do only to a certain point, because if you want to visualize biological samples, then you at one point you start frying your sample, or you start seeing photo damage of your sample. And here, the only way to improve the sensitivity is to start squeezing the light or reducing the noise of your probe beam. And this is what we have tested in this experiment here, where we see a clear improvement of the signal to noise ratio using squeezed light. So we're now working on making microscopy or making images using squeezed light. Okay, and then finally, I would also like to point out some very recent results on quantum communication, on quantum random number generation and quantum key distribution. So we have developed a quantum random number generator that produces random numbers in real time. With a rate of more than 3 gigahertz. So after post-processing, so it's really producing the random numbers in real time and with high security. So if you want to learn more about this experiment or this work, then it was just published in Nature Communication early on this year. So we also have a big activity on quantum key distribution, and one of the things we have been studying is to use machine learning techniques for phase estimation at Bob station to improve the estimation of the phase. And this becomes an issue when the phase is estimated with a weak pilot tone. So you have to estimate the phase by interfering your local oscillator with a pilot tone, and you want this pilot tone to be as dim as possible, because if it's too bright, then it's got to slide into our quantum signal, which we don't like. So therefore, we want to decrease the signal to noise ratio of the pilot tone, but that also limits the performance of the phase estimation algorithm at Bob station. So what you see here is the secret key rate as a function of the power of the pilot tone. If you use like a standard reference method where you do not do any machine learning, I mean, then you get the black curve. So what that means, we're basically not generating any secret key for these powers of the pilot tone, because the phase estimation is simply too poor. But now if you start using filtering and Bayesian estimation or machine learning algorithms, then you can improve it. And here we use two different algorithms corresponding to the red curve as well as the blue curve. The blue curve is an unscanned Kalman filtering techniques that show extremely nice behavior. So now we can actually have pilot tones with extremely low powers and still be able to estimate the phase to such an extent that we can generate secret keys. Okay, so that was just like a tour de force through some of the very recent publications from our section. Related to our experimental research. There are also a number of publications related to our theoretical research, but this has not been covered here. Okay, so for the rest of my talk, so the 40 minutes or so, I will be focusing on two topics. So the first one is continuous variable quantum computing, and the second one is how to make high quality mechanical oscillators. Okay, so we're focusing on bosonic photonic quantum computing. I mean, not the bosonic computing in the microwave regime, but in the optical regime. And here in the optical regime, there are basically, I mean, there are different approaches by which you can implement quantum computing, but probably the three most famous or most studied approaches are listed here. So the first one is an approach based on a dual rail qubit, where a single photon takes one of two paths. So that creates a dual rail qubit, where the two different paths represent the two eigenstates of the qubits. And this is studied in many groups around the world, including at the company PsiQuantum. So this has the advantage that it's relatively straightforward today to generate single photons, and the quality of single photons are also increasing significantly. So this is nice, but they also have some disadvantages, this approach, because it's very difficult to make two qubit gates deterministically. So then you need to do this probabilistically, and that creates a huge overhead. So there are significant challenges using this approach. Another approach is to use cat state qubits, which has been tested successfully in the microwave regime, but not in the optical regime. And here one of the big challenges in the optical regime is that it requires some non-Gaussian transformation. I mean, of course, it requires non-Gaussian transformations, but it requires non-Gaussian state generation. I mean, the cat state, but also non-Gaussian transformations, such as photon counting or other non-Gaussian transformations. So the last approach, and this is the approach that we are pursuing, is to use DKP qubits, or Gottesman-Kittel-Preskel qubits, which is also not an easy approach, but this is probably the state of that is hardest to generate among the three that we see here. So actually, the cat state qubit or the phase-space photos that you see here of the cat state and the DKP states are theoretically generated, whereas the single photon is actually something we produce in the lab. So this just indicates that it's much easier to generate the single photon than the cat state and the DKP qubit. But the DKP qubit approach has some advantages also. Okay, so this is just how it looks like, or the expression for the two eigenstates of a DKP qubit, and this simply corresponds to a comb of squeezed states. So this is the zero eigenstate, and then the one eigenstate is just the zero eigenstate displaced by a certain amount. And then you need, of course, a number or appreciable amount of squeezing in order to make these two states orthogonal. Okay, so the drawback here is, again, is tremendously hard to generate these DKP states, and in fact they have never been generated in the optical regime. They have been generated in other regimes, in the microwave regime, by the group in Yale, and also there has been experiments on generating them in the phononic mode of a single ion by Jonathan Holmes' group in Switzerland. Okay, so how come we want to use this DKP state if they're so difficult to generate, so difficult that we haven't even generated them yet? And that's because everything else is Gaussian, and that's nice. So we can perform all Clifford operations, a single mode and two mode Clifford operation using purely Gaussian transformations. And one example here is a single mode Clifford operation, which can be realized using a standard continuous verbal teleportation experiment. So you start by generating two mode squeezing, which is done by interfering two squeeze beam on a 50 beam splitter. And this two mode squeeze state is used to teleport your input state, which is a DKP state. And this is done using a Bell measurement, a continuous verbal Bell measurement, which can be, of course, implemented with very high efficiency. Two homodyne detectors measuring two different quadratures, and then based on the measurement output, you transform, or upon measurement, you transform the second half of the entangled state. And if you perform a standard Bell measurement where you measure conjugate quadratures in the two homodyne detectors, then it's just the identity operation that you perform onto your input state. But then now you can start playing with the measurement angle of these two homodyne detectors, and then by playing around with this, you can actually implement any single mode Gaussian transformation. And this can be easily extended to a two mode Gaussian transformation, a two mode Clifford operation. So this is nice. And we also need a non-Clifford operation, which is a non-Gaussian transformation. But if you have DKP states as your resources, then you can realize your Clifford non-Clifford operation using Gaussian optics and Gaussian measurements, which is shown here. So you have your input state, your qubit, which is then mixed with in a sum gate with a qubit GKP resource, a magic state also called, and then you perform a high efficiency homodyne measurement and use this information to control a shear gate of the DKP qubit on the DKP qubit, and that produces this non-Clifford operation that is required to enable universality of our computational scheme. This is, of course, not nice that you need these DKP resources, but nevertheless, everything else is Gaussian. And also, we also need a feed-forward operation here, and this is actually the only feed-forward operation you need to implement a universal quantum computer. You also, of course, you need a feed-forward operation in your teleporter, but this feed-forward operation can actually be applied after the measurement. So after you have done all the transformations and you have measured your state, then you can correct based on these measurements here. You don't have to do it in real time. This you have to do for the non-Clifford operation. Here it has to be done in real time. But this is the only gate that requires this. Okay, and then last but not least, you can also do error correction using Gaussian transformations if you had GKP states at your resource. And here, this error correction protocol is actually quite similar to a teleportation scheme. It's basically a teleportation scheme where the two-mode squeeze state is now replaced with a GKP bell state. And then you use this GKP bell state to purify your GKP state, your input GKP state through teleportation. So you simply remove your continuous variable or quadrature noise using such an approach. This is, of course, only the first layer of error correction. I mean, by doing this, you remove the quadrature noise, but you introduce a qubit noise by doing this. And this qubit noise can then be corrected using standard qubit error correcting protocols. I will come back to this later in my talk. Okay, so therefore, we focus on GKP quantum computing, not because it's easy to generate GKP states, because it's not, but because once you have it, everything else is basically Gaussian. Okay, and we're using a measurement-based approach, a cluster state computing also termed or coined. And here the idea is to start by generating a cluster state. Here is an example of a linear cluster state where we have entangled 4 optical modes, for example, in a linear cluster. And then you have an input state, and you perform a measurement of the input state, and thereby teleporting your input state to the next node in your network. And you know that when you teleport your state, you can implement a gate. That was what I told you on the previous slide. And then you can measure the gate and implement another. You can perform another measurement and implement another single mode gate, and so on and so forth. And then at the end of the day, you have implemented a 4 single mode gate in that way. But that only allows for single mode operations. So to make it universal, you have to build a 2-dimensional lattice of entangled states. And here there's a lattice of 4x4 entangled nodes, and consider a case where we have 4 input states. And now we can start measuring our nodes in the network, and thereby implement any type of transformation, and thereby implement universal universal quantum computing. Okay, so this is called a cluster state. So what is the recipe for measurement-based quantum computing? I mean, first you have to prepare a cluster state. So that's the step number 1. And then you simply map your circuit, the circuit you want to realize. You map this onto the basis settings of the different measurements. And remember, these measurements are just homodyne measurements. We don't need anything but homodyne measurements. So we then map our circuit into, I mean, the phases of the local oscillators of the different homodyne detectors, and then we measure, and then we have done our computation. So this is the way it goes. And so we started by realizing the cluster state. So this is now work that was done more than 2 years ago, and we came up with a scheme that is based on only 2 squeeze states of light, or 2 squeeze state generators, optical parametric oscillators, and the squeeze light is injected into optical fibers. So we produce squeeze light at the telecom wavelength 1550 nanometer. So the losses in fibers are at the minimum. So we can do everything else in the fiber after it has been produced by the optical parametric oscillators. So we start by producing 2-mode squeezing, which is done by interfering them on a balanced beam splitter. And here I represent this by graphs. And so the different nodes just represent different squeeze states. And then the length represents entanglement being created in the interference at the beam splitter. So we then delay one of the modes in the interferometer with respect to the other one. And then we let them interfere again, and thereby we create new lengths between consecutive pulses. And that creates a 1D cluster state. So that was actually demonstrated already some years ago by the group of Akira. Very nice work, and this was then repeated here at the telecom wavelength in optical fibers. Okay, but in order to make a universal computation, we need to add another dimension, and this was then done by introducing another delay line, and this other delay line is simply coiling up our 1D cluster state into a cylinder, and then we are connecting the different nodes using the last B splitter, BS3. And thereby we have constructed our 3D cluster state using a very simple setup. And this was then characterized using homodyne detectors. And we measured the nullifiers of the state, and that's one way of characterizing the performance or the state, whether it's generally entangled, multipartite entangled. And it was. And let me just take you through the lab. So we started out with generating the squeeze state in bulk, free space optical parametric oscillators made of bow tie shaped cavities. So we have 4 mirrors, and in between we have our crystal, and the crystal was a periodically poled KTP crystal. We produce squeeze states in 2 such systems, as you see here. And then right after generating the squeezing, it was then injected into optical fibers, and that's what you see here at these 2 points. And then the rest of the setup was done in optical fibers, and that made the experiment super compact. So the entire cluster state generation scheme is what you see here. These are the fibers. So the short fiber of 50 meters, that's the first delay, and the second delay was 600 meters, which is in this box here. And the output state was measured with these 2 detectors. Okay, so we are not the only group that has been producing large cluster states of light. So at the same time as we published our result, the group of Akira Furukawa from Tokyo University, he also published his result on 2D cluster state generation using a slightly different scheme, using 4 squeeze beams and using a free space approach, but with the same performance as our scheme. The architecture of the 3D or 2D state that Akira used was a bit different than the architecture of our state, but the performance of the 2 states are almost identical. Okay, and there are also work from Sorbonne University, from the group of Nicolas Traps and Valentina Parigi on producing cluster states using frequency combs. So here the states are not super large, but they're reconfigurable, so they can generate different types of cluster state, which is a very nice work. And we might also hear more about this later today. I mean, these 2 projects maybe. So Akira will be giving a talk later today, and also Nicola Traps, and I think also Valentina is giving a talk today or doing the workshop. There's also the work of Oliver Pfister. So Oliver Pfister has also been working on generating cluster state for many years, and he's also using the frequency degree of freedom in order to generate the cluster state. Okay, so now we have our cluster state. Now the next step is to perform a computation. And how do you do this? I mean, first you have to, of course, you have to define your algorithm, the circuit you want to realize, and then you have to subdivide this into different gates. And then finally, these gates are then turned into phases of your local oscillators. So and then you control your hardware based on this. So you basically just have to change the phase of the 2 homodyne detectors in our setup in order to realize computation. And the measurements are performed around the cylinder, around the circumference. So the measurement is performed around, so it's swirling around the cluster state, but the input states, they are encoded onto the circumference, and the actual computation is performed along the cylinder. So the actual computation is performed orthogonal to the measurement direction. Okay, so we started by implementing single mode gates. So here you just have the experimental setup again, as well as the cluster state, and then we prepare for single mode gates. And this was done by disentangling every single wire on our cylinder, which was done by performing measurements with a phase of pi over 4. And then by doing this, you simply disentangle every second wire, ending up with 6, in this case here, 6 single wires along which we could perform single mode gates. Yeah, this is also illustrated here. So here I'm just projecting out one of these wires here. So now the idea is to take an input state and then make a joint measurement between the input state and a two-mode state or a two-mode squeeze state of the cluster state and perform teleportation. So this is the input state. You perform a joint measurement between these two modes, two nodes, whereby you teleport your input state into the output state, and thereby you have realized a single mode gate. And then you can take this as the output, as the input to the next teleporter. You teleport again and again. So you can just continue forever teleporting your state through the cluster state. And this you can do on these 6 wires simultaneously. And this is nothing but the teleportation circuit that I presented on some previous slides. Okay, and the the transformation can be represented in the Heisenberg picture. So you simply transform the amplitude and phase quadrature using this transformation here, where G is the gate you want to realize, and we realized 3 different gates represented by these 3 different matrices. So the rotation gate, the shear gate, and the squeezing gate. And we tested whether they performed as we were hoping, and indeed they perform extremely well. So the dots are the measurement results, and the lines are theory. So we have perfect transformations of our gates. So that looks very good, but of course we have to keep in mind we are adding noise every time we perform teleportation because of the residual noise of our squeeze states. If we had infinite squeezing in our cluster, then we will have no noise, but we do have a finite amount of squeezing, and therefore we will inevitably add noise in every single computation of or every single implementation of a gate. So we characterize this noise. So we added around 60 dB of the noise in every single gate, both for the rotation gate, the shear gate, and the squeezing gate. So this is what we expect to add, and that's indeed what we added. I mean, around 60 dB of noise. So of course, I mean, we implemented the gate, but a lot of noise is being added through the realization of the gate, and this is partly due to the squeezing, but it's also part of the finite squeezing, but it's also partially due to the architecture. I mean, the architecture could have been a bit better in order to reduce the noise. Okay. So we also implemented 2-mode gates, which which you need for universal computation, and this was then the next step. So in order to implement 2-mode gates, then we need to entangle, or we need to couple 2 wires. So for example, if you have these 2 wires, the 2 inputs, and now these two inputs must be merging in a 2-mode gate, and this is done by entangling these 2 wires. So now that just means that we have to measure these 2 nodes here with a different phase than the pi over 4. And then by measuring them with a different phase, we now establish entanglement between the 2 wires, by which we could then implement a 2-mode gate. This is projected out here, and the 2-mode gate then consists of, or the cluster state for implementing a 2-mode gate consists of 10 modes, as shown here. And we did the transformations and also found that this behaves extremely well. in terms of transformations, but also it will add noise as expected. So here around 8 dB of noise is added to our 2-mode gate. So, and now we can start playing with our cluster state or making different circuits, because the different circuits can be easily realized just by changing the phases of the homodyne detectors. And we realized this circuit here consisting of 12 gates, for example, 2 2-mode gates and 2 Fourier gates and a lot of identity gates. The circuit, the symplectic matrix of the circuit you see here. And on the right-hand side, we have presented the measurements. And we measure with very good agreement the different entries of the symplectic matrix, and we also characterize the gate noise. Okay, so this work was led by Mikkel. So he was really the person behind this work, but he got support from Jonas as well as Kasper and Sushi. Okay, so but how do we actually attain universality and fault tolerance in quantum computing? I mean, first of all, of course, we need to generate the GKP states. So this is very important. Otherwise, I mean, we can't do any computing. And if we want to do large-scale computing, or actually any type of continuous variable quantum computing, we need to do quantum error correction. Because, I mean, noise is always added because of the finite amount of squeezing, and we need to get rid of this noise. So quantum error correction is of utmost importance also in order to enable any type of circuits, but eventually also in order to enable large-scale and fault-tolerant computing. Okay, so how do we generate optical DKP states? So there are many different approaches suggested, but so far none of them has actually been realized in an optical setting. And one of the reasons for this is that it's quite difficult to realize non-Gaussian transformations, and it's a quite special type of non-Gaussian transformation you need to generate DKP states. And these non-Gaussian elements could be photon counting, single photon sources, 2-level systems, I mean atomic systems, or maybe eventually using optomechanics in the nonlinear regime. And probably one of the most straightforward ways of generating a DKP state, although not simple, is to use a Gaussian boson sampler. So here you have 4 input states in a linear network, 4 squeezed states in a linear network, and then you count the photons of 3 outputs and thereby project the last output into a DKP state. And this you can do with high fidelity. The DKP state can be with high fidelity, but you of course suffer from the success rate. The success rate is relatively low, and also you need a very high detection efficiency of the photon counters if you want to generate high fidelity GKP states. But nevertheless, this is probably the simplest approach today to realize a GKP state. And you might be able to circumvent the low success rate with multiplexing. Okay, so we have been looking into using a cavity QED for realizing GKP states. And here the idea is to place a 3-level system inside a high-finesse cavity, and a light field is then reflected off the cavity, which is a single-ended cavity, and has been known for many years. Then, okay, now I cannot really change my slide. Okay, so it has been known for a number of years that if the atom is in the lower state of these lower lying states, and the cavity and the optical field is resonant with the upper field or the upper level of these lower lying field and the excited state, level, then the optical field reflected off the cavity will face a phase shift. But if the atom is in the one state, then there will be nothing happening to the reflected field. So that means you have this controlled phase shift depending on the state of the atom. And this is quite nice. And this can actually be done in the laboratory. There was a realization. Oh, sorry, I need to go on here. Also to explain, I mean, what happens if the atom is in the superposition state? Then of course you will, the reflected beam will then be entangled with this superposition state. And then by performing a measurement, a projected measurement of this superposition state, then you were projecting your optical field into a catch state. And this was realized recently in the group of Gert Rempe, but this work published in Nature Photonics a few years ago. So this can actually be realized experimentally. So you can generate these catch states deterministically using such an approach. And this is the idea that we have been elaborating upon. Instead of using squeeze states, then instead of using coherent states, we use squeeze states. So now we consider a squeeze state reflecting off this cavity QED system and looked at what happened. So first we prepared a squeeze state, which is illustrated here by its wave function. We displaced it, the squeeze state. I mean, before it was reflected off the cavity, and then reflecting it off the cavity, assuming that the atomic system is prepared in a superposition state. And we perform a measurement of the atomic system, and thereby it is projected onto a simple GKP state consisting of two superposition of two squeeze states. Now this is then re-injected, or it's then displaced and then re-injected into the cavity system, and then we are generating a superposition of 4 squeeze states, and so on and so forth. And then of course you can continue, and then thereby building up your comb of squeeze states, and thereby generating a large GKP state. So the way to quantify. Okay, time is running too fast. So the way to quantify the amount of or the quality of our state and the uses of the state in computing is to measure the squeezing of the amplitude and the phase of the quadratures of these different spikes in the comb, and the amount of squeezing in the amplitude quadrature is given by the amount of input squeezing. But the amount of squeezing in the P quadrature is dictated by the number of combs, or the number of spikes in your combs, as well as the envelope. So so if you don't have like an infinite number of spikes in your comb, then you might want to tailor your envelope in order to maximize or minimize the noise in the of the spikes in the P quadrature direction. And this can also be done by tailing our atomic system before the light interferes with it. So thereby by tailoring the superposition state, we can improve the squeezing in the P quadrature. I think I'll go on here. So another way of generating the GKP state is to only use the cavity QED system for generating squeezed catch states, and then use these squeezed catch states to breed the GKP state in the network that you see here on the right. So if you have squeezed catch state and then you interfere them in a linear network and perform projective homodyne measurements, then you can somewhat grow your GKP state. And that's actually a much more efficient approach that re-injecting your light into the same cavity. So here I just have some examples of GKP state that you would be able to generate. So using a system that has been realized experimentally, using silicon vacancy centers in diamonds, giving a cooperativity or internal cooperativity of 200, you can generate a GKP state that looks like this with a squeezing of 5.5. If you can boost your cooperativity to 2000, the internal cooperativity 2000, then the GKP state looks like this with a squeezing of almost 11 dB. Okay, so now we know how to generate the GKP states, which is of course not easy. And I think Jakob, who is behind this work, he will be presenting a poster later today or tomorrow regarding this work here, but also some other work he made on how to generate GKP states. Okay, so I have only 10 minutes left, so I will just go through the next point quite quickly. So the next question is, I mean, how do we make it fault tolerant? So I already mentioned that we need to do quantum error correction in order to get rid of the noise that is added in our teleportation process in all our gates, and in doing so, in correcting the continuous variable noise, we are actually converting this noise into qubit errors, and these qubit errors must also be corrected using some qubit quantum error correction protocols, and this requires a three-dimensional cluster state. So we need to add a dimension to our state, and one way of doing this is shown here. So this is quite similar to our previous cluster state scheme with delay lines and interference points, but we have inserted some beam splitters here, which are variable. So these are beam splitters that are turned on or off. So either they're transparent, I mean, basically they're not there, or they act as a 50-50 beam splitters. And by using such a scheme here, relatively simple scheme, you can actually realize a three-dimensional cluster state, which is shown here in time domain. So it's a three-dimensional time lattice cluster state, where the different lines here constitute different two-mode squeeze states along which you can perform single-mode operations. And then if you want to combine different wires, different two-mode states, then you do this through activating these two variable beam splitters here. So if you're activating the green beam splitter, then you're coupling this wire with this wire. If you activate the blue beam splitter, then you're coupling this wire with this wire. So we can couple, we have many degrees of freedom and can couple it as we like. And the architecture here is actually better than the architecture that from our 2D cluster states. So we actually already minimizing the noise in gate operations just by the architecture. And then in addition to this, we can do quantum error correction coding, and we can do qubit quantum error correction coding, because now we have the third dimension, so we can encode our state as on a surface on this 3D cluster state. So our qubit is now encoded onto the surface, and then the computation is performed along the last dimension. And using this surface encoding, we can attain a fault tolerance when squeezing is more than, okay, this is actually an outdated figure. I mean, here it says 13.2 dB of squeezing is required in order to make it fault tolerant, but we have actually improved the protocol, so now it's at 12.7 dB of squeezing that is required in order to make it fault tolerant. The colors here correspond to different sizes of our surface code. So the bigger the surface code, the lower is the logic error if we are in this fault tolerant regime. So of course we need to be well in this regime in order to get the errors down to a point where we can do scale up quantum computation. Okay, so I almost have no time left if there should be time for questions, but I would like to very briefly go through the second part of my talk. So this is about optomechanics, and this is these years are very exciting years for optomechanics, because I mean people are bringing these mechanical oscillators into a regime where you can start doing very interesting stuff. You can implement different type of technologies, quantum force sensors, quantum memories, and quantum transducers, but you can also use this to test the foundations of quantum mechanics. So, and the quality of these systems, these mechanical oscillators, they are often quantified by the Q factor or the QF product, where F is the frequency. There has been different methods to increase the quality factor. So this summary of different previous results is not exhaustive. I mean, there are a number of research being done in this direction. So here I just mentioned 4 of them. But almost 14 years ago, it was realized that if you introduce high tensile stress in your material, for example, in silicon nitride, then you can minimize the intrinsic losses of your mechanical oscillator, and thereby you can boost your Q factor. Some nice work was conducted about 4 years ago on making high quality membranes, also using high tensile stress materials. The technique of soft clamping was introduced about 3 years ago in the group of Albert Schleicher. So here by isolating the phononic modes from the environment through some soft clamping techniques, and that boosted the Q factor significantly by an order of magnitude. And in the group of Tobias Kippenberg, they also combined the soft clamping with tapering or strain engineering. So they, in addition to have this periodic structure for soft clamping, they also tapered the string mechanical oscillators, and by this tapering, they focused the mechanical oscillator to be located at the very center of the tapering region, and thereby isolating it even further from the environment. And by doing this, I mean, they attained the Q factors in the order of 1 billion at room temperature. So we have been using a different approach. I mean, all these approaches here are very clever, very smart, but they are mainly based on human intuition and human insight, and by looking at the approximative analytical formulas for mechanical oscillators. But we don't know whether these structures are optimized or optimal, because this is an optimization problem. This optimization problem can be done using topology optimization computational techniques. And here we teamed up with some of our colleagues at the university who has lots of experience with topology optimization. I mean, they used to do topology optimization on a very large scale. For example, on the wings of an aeroplane. I mean, how do you distribute the mass in such a way that is lightweight and is still very stable? Then you come up with such a design which is not intuitive, but is something that can only be made by this very clever computational program. They've also been using these programs to optimally find the mass distribution of girder in bridges. So, and then we thought, why don't we use this in order to optimize the mechanical oscillators on a micron scale? And this is what we did. So we used these techniques in order to optimize the structure of the membrane, with the target of improving the QF product. So the pre-constraint is that we need to have a central pad, because we need a pad that the light could interact with. So this was the starting point. And then the program is just redistributing, adding and removing materials. And while doing this, it looks at the QF product, and thereby finding the optimal structure. And the optimal structure, this is the process, how it looks like when you interrupt the program doing the calculation. So this is the initial design, and then this is the optimal design. Okay.
I'm sorry, but I will kindly ask you to please conclude.
Yes. All right. Okay. So I see I missed some slides here. Okay. Something actually went wrong with my presentation. So I mean, I was supposed to present the results here, but the results are missing. Then let me just mention the results. So the QF product is boosted as a result of this topology optimization. So the simple trampoline structure is not the simple trampoline structure that was used in this work here is not the optimal trampoline structure for improving or for boosting the QF product of the fundamental mode of the mechanical oscillator. It can be increased by using this topology optimization approach. And then I better conclude here. Yeah. So just in summary, so I've been talking about how to build a fault-tolerant continuous local quantum computer, and here at the very end, which was very quick, I'm sorry about this, I discussed our recent development of making ultra-coherent mechanical oscillators. Okay, so thank you so much for your attention.
Thank you, Ulrich, for a very nice talk, but unfortunately, we have literally no time for any questions. So thank you, as I said, for your talk. And I would like to invite Julien Laura as our next speaker. Julien? Okay, Julien, we can't hear you or see you.
So you can hear me now?
Okay, now we can hear you.
And you can...
Still no camera? Okay. Okay, now we can hear you and see you. So thank you for joining us, and please go ahead.
Okay, so yes, thank you. So you see my screen. It's okay, I just need to put the pointer. Yeah, it works. Okay, so thank you very much, everyone. And it's my turn to thank you, all of you, to be part of this first workshop for this non-Gauss project. So I think we are all excited, as Ulrich said, to be part of this new project. It will lead to a stronger collaboration. As Radim said, we are already collaborating for quite a while, but it will be a great opportunity to have much more work in common. And also, this workshop, I want to say it again, is just the first one of a long series of workshops on school that will happen in the next 3 years. So as you understood so far, this project is pretty broadband in terms of physical effects we want to study, in terms of quantities we want to look at, in terms of physical platforms we would like to study. And this is why, in this context, for this first workshop, I chose a quite general title for my talk, like distributing entanglement in quantum networks. We are all basically doing that. But it's a way for me to cover actually most of our activities in Paris, in my group at Laboratoire Castres-Bruxelles. So some of them are really non-Gaussian in terms of photonics. This is a test bed we have been using also with Radim to show some the capability witness criterion that Radim was explaining, and I will come back to that. So it's really a test bed for non-Gaussian state and non-Gaussian quantum state engineering. But we are also developing other platforms like memories based on cold atoms, or cold atoms coupled to nanoscale waveguides, which are emerging platforms. And we would like really to study also this kind of platform in the context of this project. So I will try today to address more or less all of this platform and show you where we are and what we are doing in these directions. So you all know this picture of Jeff Kimball about the quantum internet, how to make a kind of quantum networks based on quantum nodes and quantum channels. So to store and process quantum information, quantum channels where you want to distribute some quantum state of light. And we are tackling many of this part of the network. So we have a few labs working in this direction. So the first one is a hybrid photonics lab, where we are doing quantum state engineering, but taking a specific approach, which is to combine today what we call the continuous variable approach and the discrete variable approach. aiming at developing a kind of heterogeneous networks where you can combine these two approaches. The second activity is to develop free space quantum memory, very efficient quantum memory that we can achieve now. And the goal is to build little by little, piece by piece, a quantum repeater which require a quantum memory for synchronization. And the last activity, which now involves two experimental labs, is to couple cold atoms on nanoscale waveguides. So these waveguides, they can be nanofiber. This is the one we started with, and I will show you results about that. But we are also starting a new lab where the nanofiber is replaced by a photonic crystal waveguide, a slow mode waveguide, where the interaction can be much stronger and still in a single pass way. So I will try today to cover all these topics, mostly the first two. Hopefully I will have time for the last one. So let me start with this quantum state engineering lab. So the goal is to make quantum state engineering, as I said, but we're trying to combine these two traditionally separated approaches of quantum information, what we call the discrete and the continuous variable approaches, so leading to this optical hybrid quantum information. So you know that this is related to the duality of light. You can see it as a wave or particle. So you can be even counting photons like 0 or 1 or polarization as a degree of freedom, but you can also rely on the amplitude and phase, and then you will be using some demodulation techniques and measuring quadrature of your electromagnetic field. So you can try to combine these tools and concepts to develop new kind of protocols. So, for instance, the picture we have in mind is in the future that you would like to develop this kind of platform, of network, where you have some nodes, which can be photonic platforms, which can be material platform. I think about optomechanics, about atomic ensembles. Some of them will be better suited for CV encoding, continuous variable encodings, and some other for discrete variable encodings. So how you may be able to connect them together. To be able to do that, the first resource you want to have is entanglement between these two kinds of encoding. So this is what you need, that we call hybrid entanglement of light. That was a cover of Nature Photonics a few years ago. We had a back-to-back paper with the group of Marco Bellini, and we demonstrated this optical resource, where you see here entanglement between discrete variable on one side. So it depends, it can be different kind of encoding, but it can be, for instance, for us, a 0 or 1, a photon or no photon, on the Schrödinger cat state, so continuous variable qubit on the other side. All this topic, so I will give you more details now about this topic, but it will be also covered by a poster today by Beate Hersenbeck, who will give you more details, and you can ask also much more questions about the ongoing experiments in the lab about that. So let's go to the lab. So this is how it looks like. It's a bit similar to what Ulrich was presented before. There is no much fiber. It's not a telecom wavelength here. But what I want to show you on this table is it's a mixing already of many tools. So you have OPOs. So this is what we are using to make a non-classical light. So we have actually more than that on the table. We have 3 OPOs, which are equivalent to 5 independent single-mode squeezers. We have homodynamic detection, which enables to detect, make the full quantum state tomography of the light you are generating, but we also use them as a processing tool to tell you, for instance, the success of a protocol. And we are also using many single photon counters, which are based on the superconducting single photon detectors. So we are mixing here already many tools which belong usually to continuous variable approaches or discrete variable approaches. So let me zoom a bit on this setup. So again, we are using optical parametric oscillators, as you can see here. So it's either single mode squeezer or 2 mode squeezers. So it depends on the crystal you are using. So we are using either KTP and PPKTP with different phase matching. And we put that in a triply resonant cavity, so that gives us OPOs which have a very low threshold. So you can make, for instance, this kind of squeezing. So here you have a plot when you scan the phase of the local oscillator with 11 dB of squeeze light generated out of this optical parametric oscillator. We are working also, so we are working at 1064 nanometer, so near infrared for this experiment. And usual single photon counter are not so efficient at 1064. So it was very important for us over the recent years to move to superconducting detectors. But it was not obvious a few years ago at this wavelength to find some. So we had a very nice and fruitful collaboration with GPL and NIST, with the group of Seunam, to develop superconducting nanowire detectors working at 1064. So it was an iterative process and to find the good combination of layer that you put on the top of your system, for instance, to increase the overall efficiency. But at the end of the day, what we get is a quantum efficiency, a system detection efficiency, so including the fiber up to the detectors, which is above 90% on a daily basis. And the noise is below the 1 count per second. You are working at a cryogenic temperature close to 1.5 K. So this is what we are using in this experiment. So we are using homodyne detection, again, very efficient, above 99%, but also detectors for single photon, which are above 90% on all that in the near infrared. So all these experiments are based on heralding measurement. Right? We are using SPDC, so it's everything is probabilistic, but we can make it heralded. And the strategy we are using is a strategy where you make a measurement on correlated beams, and given this measurement, you get a state on the other side in a probabilistic but heralded way. And thanks to the OPOs we are using, you can already see it here because, I mean, when you get this kind of level of squeezing, it tells you something about the OPO you are using. It tells you that the escape efficiency is very high, and so the states you get can have a very high purity. So for instance, you can make very good single photon source. So here, if I use a 2-mode squeezer, so an OPO with a type 2 phase match crystal, we generate squeeze twin beams here. And if you detect here with our superconducting detector a single photon, then on the other side, you conditionally prepare a single photon. But thanks to this nice OPO, the heralding efficiency now in this experiment is 93%. So that means so there are different ways to interpret this heralding efficiency. If you look the state, that means there is only 7% of vacuum in the density matrix. So then if you reconstruct the Wigner function, this is what you have here, you have a very negative Wigner function for your single photon. In other terms, also this heralding efficiency, so this is a P1 term, the single photon component in your state. It means, given a click on your detector, what is the probability to really have a single photon at the output of your system? It is here 93%. So we can do that up to 1 megahertz rate with 50 megahertz bandwidth. And also, as we are using cavities for these OPOs, we have a very good spatial mode. We are making interferences between these photons, and the visibility can be well above 99% when you make this kind of gates. So we have been using this experiment to make single photon, to make witnesses for single photon entanglement, and also very recently, and Radim presented this work, and it was actually published in Optica yesterday night. It was a very good timing. So we have this paper about the fog state bunching capability. So trying to see if I give you many photons coming from our systems, which will have some discrepancies, and we try to mix them with beam splitters and so on, what is the highest fog state we can build? And we were showing that given the state we have to start with, we can go up to 14, and it was actually limited by the computing power for the quantifier. So you can also push, of course, to the engineering of higher fog state. So for instance, if you still start from these twin beams and now you get 2 clicks on your superconducting detectors, you will get a 2000 Fock state, and you can see here the Wigner function, which has also strong negativity, and that can be generated at 200 Hertz rate. So that's what I will call the discrete part of our experiment, trying to generate a Fock state. But as I told you, what we would like to generate is really this state, this hybrid entanglement of light between DV and CV, and between, particle-like and wave-like system. So this kind of superposition between 0 and 1 on one side, photon and no photon, and coherent state or cat state on the other side. So how we do that? So what we do first, so you see the experiment, which was on the table I was showing you right before. So you start from a 2-mode squeezer, still our OPO, you can see here, but in a 2-mode squeezing way. So you get twin beams, signal and idler, which are orthogonally polarized. So I can separate them on the PBS. And when I get a click after filtering on the superconducting detectors, then either you get a click and you get a single photon, or nothing happens and you basically have vacuum on this part. So that will be the DV states in our experiment. So now I want to generate continuous variable state. So I can make another experiment where I start from another OPO, which is a single mode squeezer. So that means that the output signal and the idler are degenerate, and you get squeezing. This is the one used before, as I was showing you, to get this 11 dB of squeeze light, except here we are using it further from threshold on just a few dB of squeeze light. So then the way to make a cat state is well known for a long time, is to take a very small part of your squeezing, a few %, and then when you get a click, you will generate a state which has a very large fidelity with a kitten state. So Schrödinger cat state, but with a moderate size with alpha around 1. So this is what you get. If when you get a click, you get a cat state, which here is an odd cat state. So you have an odd distribution of number of photons. And if you don't have a click, you get a squeezed state, which has also a very high fidelity with a small Schrödinger cat state, even cat state in that case. So we have two experiments in the lab. One which can generate by heralding some DV state, and the other one which can give you some plus and minus, so even or odd cat states. So how you make entanglement now between them? You run them at the same time. You mix the conditioning path in the middle in an indistinguishable way. And when you get a click in the middle, you don't know where the click is coming from. So either you generate this one photon on one side and squeezing on the other side, or you generate a vacuum on one side and the other cat state on the other side. And you have no way to know where the photon is coming from, and you end up with this superposition of this 0, 1 and cat plus, cat minus. So that was done in the group quite a long time ago again. It was more than 6 or 7 years ago we did that. It was a back-to-back paper again with the group of Marco Bellini, which was using another technique to generate a similar state. So what we have been doing over the recent years was to use this state now for some protocols. So for instance, you can use it to remotely prepare a continuous variable qubit, so Schrödinger cat state, at a distance. You don't want to propagate a cat state, which would be very sensitive to the loss. But thanks to this entanglement, you can generate in this way a qubit at a distance. So the point of this paper was to make here a detection on the DV part, but it was using a homodynamic detection to make the conditioning. And then we are doing some homodynamic conditioning. So you get a quadrature measurement, and then you decide to open or not the selection. And then you can prepare on the other side, you project into any CV qubit on the Bloch sphere. Of course, you can change the phase of the local oscillator. So this is why you can go wherever you want on the Bloch sphere. Another experiment we did more recently was to show that this hybrid entanglement can be used in a specific cryptographic scenario, which is a one-sided scenario. So we were able to verify that we can violate steering inequality using this hybrid entanglement. the last experiment, which was published last year, was the following. So the idea was we want to make an heterogeneous quantum network where we can have some kind of entanglement between discrete variables like dv-dv entanglement, like single photon entanglement. You can have hybrid entanglement, dv-cv entanglement. And we wanted to make a swapping experiment between these two different kinds of entanglement. So what we did here was to mix in the middle these dv modes here. So dv and dv part here in a middle station, make a Bell state measurement, and then generate entanglement between these two modes that never interacted in the past. So this Bell state measurement was a bit specific. We were using at the same time homodyne detection and single photon counting. So just to show you, I will not enter into the details. This is something you can also discuss during the poster session. But this experiment we're using typically 5 independent single mode squeezers because we need to generate the single photon entanglement. We need to generate the hybrid entanglement. And then you need to combine them, make an additional measurement, this Bell state measurement, to herald the success of your entanglement swapping. So this is what we did. We were using these OPOs on the SNSPD to generate single photon entanglement that you can see here. We were using them to generate hybrid entanglement here, and we needed then to combine the DV part, and to be able to do that, it was necessary to have a delay line to combine them at the good timing. And then we were doing the Bell state measurement here in the middle again, which is mixing single photon detection on a superconducting detector and homodyne conditioning here. When all that succeeds, we can then have this hybrid entanglement here at the end between these two modes that never interacted. So just to show you the result, so this is a full quantum state tomography of the output beams here when we make the Bell state measurement, and you see appearing some coherence terms that show you entanglement. If you don't do the Bell state measurement in the middle, just to confirm that in that case you have no entanglement. So it was a demonstration of hybrid entanglement swapping based on these resources. One goal now, and this is something we are doing now also in the lab, is to use also this kind of resources to make encoding conversion between CV and DV qubit. But I will not report about that today. So that was the first part of my talk about quantum state engineering. So again, we are pushing protocols using hybrid entanglement, but at the same time, in the context of all our work with Radim, it's also a nice test bed for making some tests of witness for non-Gaussianity. So it can be like the capability paper I was explaining before, Radim explained in his talk, this bunching capability. Something we did also in the past was to make bigger Schrödinger cat states by using also some squeezed Schrödinger cat, for instance. So we were able to make big cat states which are squeezed because what matters is actually the non-Gaussianity you have, and then everything rely on the Gaussian operation you need to add if you want to come back to the non-squeezed cat state. And we were also showing with Radim on this experiment that a squeezed cat state, you can propagate further. It's more robust to loss also. And that was a paper we did also 2 years ago. So let me go now to the other platforms, which are not so easily related actually to non-Gaussian states, but actually there are. And there are many experiments we are thinking of now where we can investigate this non-Gaussian aspect. So the first experiment I will show you now with cold atoms is how to make an efficient quantum memory for light. So we have been working on this. So you see here a vacuum chamber, you see beam. So what you see in the middle is a bubble of millions of cesium atoms at very low temperature. And we have been doing for a while now quantum memory experiment with this system. So for instance, trying to store some superposition of Laguerre-Gaussian modes. So that was this paper, which was a quantum memory for qubits, which were not encoded in usual degree of freedom, but in spatial degree of freedom here. We were also pushing this multiple degree of freedom using this vortex beam of light, where you have in the transverse plane a distribution of phase, but also a distribution in polarization. And we were able in this system to store both degrees of freedom at the same time and retrieve. But at that time, so that time means 6 years ago, 7 years ago, basically the efficiency was still limited. So what is the efficiency? Is the probability that if I store a photon to get it out of the system, and you want that close to unity. At that time, that was the state of the art. The efficiency was typically in this kind of memory around 20–25%, because the number of atoms we were using was not large enough. So what I want to show you now is how we can actually now reach a very large, close to unity, close to 90%, storage and retrieval efficiency in this kind of setup. So I don't need, I guess, in this audience to explain that we want to make long-distance quantum communication, and there are two ways to do it. So either you use a quantum satellite, and we have seen many papers, and that will be likely used in combination with a second way to do it, which is quantum repeaters. And if you want to make a quantum repeater, so long-distance distribution of entanglement, you need quantum memories for the scalability of this development. So this is our classical network. It works. It works because you amplify the light with erbium doped amplifier, which you all know that we cannot use in quantum communications. The no cloning theorem will forbid that. So we need to find other tools, and the other tools is a quantum repeater. I just go fast and flash this slide. You all know this topic. But the idea is just you have a very long distance, and then you cut it in many segments. Then you make entanglement between these segments. And if you do a Bell state measurement in the middle, you can extend pair by pair this entanglement and end up with a long distance where you have entanglement. And by teleportation, for instance, you can transfer a qubit from one end node to the other end node at a long distance. Long distance meaning hundreds of kilometers. This is the target to be at the continental scale. If you just do that, it doesn't work. If you just do that, it doesn't work because the number of segments is large. Most of the protocols are probabilistic. So what you need to do, if you don't want to increase the communication time in an exponential way, you need to store the entanglement into quantum memories. So like that, you have a synchronization tool, which is the goal of a quantum memory, not only for network. If you do linear optical computing, you would like to synchronize your resources, to synchronize your single photons to increase the rate. This is exactly the goal of a quantum memory in a network, is to synchronize the network. You need to wait for this segment to be ready. When it is ready, then you can keep this entanglement and prepare the other one. And when everyone is ready, you can build the tree, build your network. And this is what gives you the better scaling for the communication time. So the name of the game is really how to build these efficient quantum memories. So the goal is to do something like that. This is our paradigmatic picture of the Quantum Internet Alliance project. I will come back to it, which is one of the flagship in Europe. So the general strategy to make a quantum memory is that you start from a qubit. You want to write it in a matter system with two energy levels, and then you want to read it. And again, you want to do that preserving the coherences. You want to be able to store a qubit, and you want to do it in an efficient way. So there are different approaches to do that. The first one is to use a single atom, for instance. But you need to put that in a high finesse cavity. So I show you one protocol where you have a three-level system, but a single atom inside the cavity. And you have here example. This is a picture from the group of Jeff Kimball, but you have many other realizations now in a variety of platforms. The other way to do and this is the one I will focus now on, is the use of an atomic ensemble. So you have many atoms to be used, and of course, interacting a single photon, a single qubit with many atoms is much easier to do. You have a much larger probability to interact and to absorb the photon. But importantly, what you are going to generate in this way is a collective state. So that means if I take the example of all the atoms prepared in one state, the green one here, when I'm going to absorb a single photon, I will do it in a way that I don't know which of the atom will be excited. So you get this giant superposition of n terms, where n is the number of atoms. And when you are going to read it out, you will have an enhancement effect, which makes that the photon will be not re-emitted randomly in space, but you will know exactly where to catch the photon. So that means I can come with a single mode fiber, send it into my memory, and then when I'm going to read it out, I can put another single mode fiber, and I will get the single photon inside this single mode fiber. So this is due to this collective excitation. And also the nice point of this collective excitation is that you have many atoms in your system, and of course it opens the capability of doing some multiplexing, which is an important step for quantum repeaters. So many ways to use atomic ensembles. It's not just atomic ensemble, it's not just cold atoms, it can be ions, it can be warm vapors, and of course it can be also doped crystals, as you can see here. So in our case, we are using cold atoms. In all these protocols, the name of the game, if you want a large efficiency, again, probability to get a photon in and out, is the number of atoms. More precisely, is what we call the optical depth of the ensemble. So what is the absorption at resonance of your system? So its output is equal to the input exponential minus OD, and OD is what we call this optical depth. So you need a lot of atoms, of course, if you want this number to be large. Then the scaling can be different depending on the protocol you will be using. But in any case, if you want to increase the storage and retrieval efficiency, you need to increase this number. So we understood that, of course, a long time ago, but it's a challenge in the lab to make a very large magneto-optical trap with a very large optical thickness. So we built a new experiment over the recent years, which were an elongated quasi-2D mode. You can see here in a glass chamber. You can see here the two pair of coils with quite a lot of trapping power, a few hundreds of milliwatts, very big beams here. You can see the collimation packages you have on three sides of the vacuum chamber that you can see here also in the middle. Some stage of compression, also some PG cooling to get cold atoms at the end. And we end up with this kind of pictures. So this is really a picture you can see here of the chamber, the magnetic coils around. And here you see a 3 centimeter long magneto-optical trap. And in this one, so that was a few years ago, the optical depth was around something like 300. So then we are using as a protocol EIT for storing our qubits. So just a reminder, for EIT, you start from a 3-level system. So you have 2 ground states and 1 excited state. You prepare all your atoms in one of the ground states, and you will send on this transition the qubit you want to store. But you are helped with a control field here on the other transition. So if you just go through what you are going to do, again, this photon is supposed to be absorbed strongly because the optical depth is 300. So you should have exponential minus 300 of absorption at resonance. But if you send also this control pulse, then you open a transmission window, which is going to lead to slow light. This is the principle of slow light. But now, if the pulse is completely squeezed inside the atomic ensemble, if you also switch off the control field, you are going to transfer your photonic excitation to an atomic excitation, what we call a dark state polariton or a spin wave. And later on demand, if you switch on again your control field, you are going to release your photon. So the question is, if I send a photon here, what is the probability that I get a photon at the output after all this process? So with this new system, we did it with a polarization qubit in this memory. So this is as a function of time, the number of counts you get on your single photon detectors. So the blue line, for instance, is what you get without atom. So this is our reference. If you just do slow light, you see I can delay the pulse. This is what you see here. But now, if when the pulse is delayed, I switch off the control field and switch on again after a few microseconds, then you see the photons going out. So then you can quantify the memory efficiency. All that is done at the single photon level as a function of the optical depth. And as you can see, as expected, then the efficiency is increasing. The red points are the experimental data. The other line are our theoretical model with or without optical pumping in a single Zeeman level, which we didn't do actually. So this is why we are following the blue line. And we were reaching a plateau with a value around 60 to 70%. So that was pretty good result. We were pretty happy. The qubit fidelity was 99%. So that means we have a very good rejection of the noise. And the storage and retrieval efficiency for this qubit was something like 70%. So the question at that time was why this is only 70% and not 90%. Actually, if you increase further the optical depth, it will decrease. So that was really the maximum value we can achieve in the experiment. So we came back to some calculation, and that was done in particular by Alexandra Cheremet, who was a Marie Curie fellow at that time in the group. And we did actually many calculations about this kind of stories in the past when we were working 10 years ago with warm vapor, where you have to take into account the fact that in cesium or in alkaline atoms on the D2 line, you have many excited levels that you do have to take into account. So if you take them into account and you write the decoherence rate in the constant state, what you find is some additional terms which depend on the separation between the excited states. So of course, with warm vapor, you can think it's very important. You have very large Doppler broadening. So this is why we were studying that 10 years ago in this kind of system. But actually, it's also very important with cold atoms. And you have actually an off-resonant excitation by the control field of all the other excited levels. So you add many additional terms in your decoherence. And this decoherence is not a big issue if you work with a low OD, but if you increase a lot the OD, this decoherence will translate into loss. So this is a transmission window of the sample. So you can see it absorbs the light, but you can open a transmission window in the middle by EIT. But when you increase VOD, you see that the transmission window is actually suppressed and you lose a lot of light due to this decoherence terms. So we understood that at that time. It sounds maybe obvious now, but just cesium D2 line is not the good line to make quantum memory. So what you need to do is, so this is a prediction, as I was telling you, if you do that, you go up and then you go down due to this compromise between better efficiency and the loss due to this decoherence terms. And we were here in this experiment. So there was no way, if we are still using cesium D2 line, to go further. So we changed all our lasers, we understood that, and we went to D1 line. D1 line is much better because if you go in the excited state, there is on 2 levels which are separated by more than 1 gigahertz. So we built a new setup, and we were expecting that if we get 400, 500 of OD on the D1 line, you see, we should be able to be at 90% efficiency. So we did it, and actually it worked, and that was a recent paper. So if you plot here, so you have, I give you here the G2, the W parameter of the G2, so the suppression of the multiphoton component. 1 is for a coherent state, 0 for a perfect single photon. And we were generating by another way a single photon. So P1 is actually the excitation probability of a DLCC setup. I will come back to that. But what I want to show you here is that we store a single photon with basically 90% storage and retrieval efficiency. And if you measure the G2 before and after the memory, basically you keep the same value. So there is no added noise by the process. And this is the efficiency scaling. As you see, we can reach this plateau. And already for an OD from 300, 400, we are close to 85 to 90% storage and retrieval efficiency. And again, for a true single photon. So what we wanted to do then in the context of a quantum network is to make memories for entanglement. So what we did, so that was done in the past with different setup, either DV or CV, also different platforms like cold atoms or crystals, but the entanglement transfer. So if you measure what was the entanglement you start with and how much you end up at the end, if you measure it with some monotone measurement like the concurrence of entanglement, basically the transfer was 25%. But it's a very important number, actually. If you come back to some paper like this one by Nicolas Sangoire and co-workers, which is a very important paper in terms of quantum repeater architectures, what you see is, so we give here the distribution time it takes for something like 600 kilometers for many different architectures. I don't care today. So all these letters are DLCZ, SPS, whatever. It's different kind of architectures as a function of the memory efficiency you can achieve in your setup. And what you can see is typically if you go from 60 to 90% efficiency, again, whatever the architectures, what you win is 2 orders of magnitude in the distribution time in your network. So any small increase you get in the memory efficiency has a huge impact on the efficiency you can get in a quantum repeater. So we were showing that in this paper. So we were working with single photon entanglement, which was generating by Hanover atomic ensemble, storing the entanglement in 2 quantum memories, and measuring them, the entanglement, after storage. And we calculated the entanglement transfer. So we are measuring the input and output concurrence, so, which is a monotone measurement of entanglement. And we get a 85 entanglement transfer, which is in good agreement with this efficiency we were achieving. So just to show the experiment, as I said, we were using the DLCZ protocol in a cold atomic ensemble to generate the first single photon. So here the OD was much smaller. It was an OD of 6, and G2 was below 0.1. When we got this single photon, then we split it on the beam splitter, and we get a single photon entanglement that we store in 2 spin waves, which were actually in the same atomic ensemble, but they were independent. So 2 spin waves, which were entangled. And then you can retrieve entanglement and characterize it by doing fringes and by doing photon counting and measure the entanglement you get at the end of the day. So all this work was done in the context of QIA, the Quantum Internet Alliance. And you see here Félix Offé and Mintao Shao, who did all this work already 2 years ago. So QIA, so this is a Quantum Internet Alliance, which is coordinated by Stephanie Venner in Delft. And in particular, we have one work package where we are working on developing quantum repeaters, and in particular the hardware for doing that, namely quantum memories, with many challenges in terms of efficiency. So I told you, we can now push it up to 90% in our system. Lifetime, I didn't tell you, but in our setup, it's typically limited to 15 to 20 microseconds. So we need to go to a cooler atom or other trapping techniques for extending the lifetime. It has been done with cold atoms. And also an important point is the multiplexing capability, which is very important in our classical telecommunication system, but it will be also very important if you want to increase the rate of a quantum network. So there are different degrees of freedom. The one we are pursuing in my group is to use spatial mode multiplexing. So of course, we were doing it already years ago by storing a few modes, but now we are trying to push it to much more modes using spatial division multiplexing, which can be used in this kind of large OD for all of them at the same time. So this is what we are working on now. So let me go now in the next 10 minutes, something like that, a bit more, to the last system we are developing, the next interface, which is to couple cold atoms, you can see here, close to a nanoscale waveguide. And there will be 2 experiments. I will not show you the last one, but we are developing a new one, and that will be the conclusion of the part. So why we want to do that? So this goal of making a single atom to interact with a single photon, of course, it's a hard topic. And I want just to give you an overview of the techniques to do that. Of course, you can do that in free space, but the probability of interaction is small. It's limited by the cross-section of absorption, which is typically lambda squared, and the area of your beam, which is also diffraction limited. So basically, if you want to increase this interaction, you will go to very strong focusing, but the interaction probability will be limited from 10 to 20%. You can go to 4 pi microscopy, for instance, and go to a bit larger number. Another way to do it, we all know, is cavity QED. You make many round trips, so you will win by the finesse of the cavity. But another way that has emerged over the recent years is waveguide QED. So here the goal now is to go to the nanoscale, to put an atom close to the waveguide. And then if you define the decay of the atom inside the waveguide and in free space, outside of the waveguide, you can define dispersal factor, which is proportional to 2 terms. It's proportional to these geometrical terms here, but you find it back in cavity QED or in free space. But here you are at the nanoscale. And there is a second term, which is a group index here. So that means if you propagate the light slowly, so it's still not a cavity, it's a slow mode waveguide, you can also increase the interaction. So now if you realize that, then you can calculate what will be the reflection of a single photon by a single atom. Or also, if you put many atoms, you can have a large OD, which will be proportional to the number of atoms times the Purcell factor. So something we would like to do in the future, it's kind of the graal of the field, is to have a very large Purcell factor in this configuration. All that in a single pass. Again, there is no cavity mode. You want to be coupled to continuum of guided mode, like in a fiber. But one atom can reflect the light. And also, as diffraction is not limiting anymore, you can have many atoms and use all the collective effects, like the quantum memory or the generation of collective excitation I was presenting just before. So let's go to the lab. So we have a first experiment in this direction, which is a nanofiber experiment. So this is a lab with nice light painting that Neil Corzo did a few years ago. He was a postdoc at that time, and is now a professor in Querétaro in Mexico. So if you zoom into the chamber here, there is a vacuum chamber, and inside its vacuum chamber, there is a nanofiber. So this is what you see here, some scattering here, but you have a nanofiber, which has a diameter below a wavelength, typically 400 nanometers. So that means half of the energy is circulating outside of the fiber. But still, if you go from the beginning of the fiber, which go into the vacuum and go out of the vacuum, the probability, the transmission is overall 99% or above 99%. So you don't lose light, but you can put atom in the middle and you can trap them in the evanescent field. So the way to trap them is to use a two-color evanescent dipole trap. So you contra-propagate light and you make an optical lattice in which you are going to trap your atom. The trap is really microscopic, so you have at most one atom per side. You are in this blockade regime. And also, you want to use some blue detuned light to compensate some surface interaction. So overall, what you get is really the picture I'm giving here. You get something like a few thousand of atoms, typically at 200 nanometers from the surface. So the coupling is pretty weak in that case. If you calculate the beta factor, it's typically from 10 to minus 2 to 10 to minus 1 in the best case. And this is why we're also developing another platform, I told you, where we will be using the group velocity as another ingredient. But let's focus now on the nanofiber. So one of the first experiments we did with the nanofiber was to make memory. So we did some EIT again. So this time the atoms were not trapped. We were just overlapping the nanofiber with a cloud of cesium atoms. The signal was at the single photon level and was propagating inside the fiber. So it was all fibered, input, output, and the control field was outside. So of course, we were able to observe some slow light, some reduction in the group velocity, but we were also able at that time to make a memory. So this is what you see here in terms of counts. This is a pulse without atoms. And now if you switch off the control field and switch on later, you get some retrieval. And the efficiency is not as good as in the free space. The OD was limited, it was a few units at that time, but we get 10% efficiency, all fibered at the single photon level. Then we learned how to trap the atoms. And in particular, if you make this dipole trap, you can change the wavelength of the trap, and you can change the distance between the atoms. So what we did was to make a trap very close to resonance. So typically the distance between the atoms is lambda over 2 plus a very small mistake, because you still want to trap the atoms. And each atom will behave as a small mirror with a small reflectivity. So what you should get, if you send light now, is a Bragg mirror. And this is indeed what we observe. So I give you the reflectance in blue and the transmission in blue as a function of the probe detuning. And you can see that we were able to achieve something close to 70% with only 2000 atoms, thanks to this tunable distance between the atoms. And there are many other nice effects to observe in this system. For instance, you can have some chirality, so that means you can have an asymmetric decay inside the waveguide. It depends on the polarization of the probe. So just by rotating by 90 degrees, the polarization of the probe that you are sending into your device, into your nanofiber, you will be either in the case of a symmetric decay in the waveguide or an asymmetric, strongly asymmetric decay in the waveguide. And then you can see that there is a change then in the reflectance you are measuring. So this is something we did a few years ago, and we are coming back also to this system to see how we can control this kind of Bragg mirror using a 3-level system now. The last result I want to show you on this nanofiber experiment is a paper we published 2 years ago, which was to create in this waveguide system a collective excitation, so a non-classical state, then you can read out as a single photon, and all that in a fiber configuration. So the process we used is a DLCZ process, the Lukin-Sirac-Zoller, which is very well known and used in free space. This is a way we generated a single photon in the quantum memory experiment I was presenting before. But here we wanted to do that in this all fiber system. So we prepared all the atoms along the fiber in this dipole trap, preparing them all in one of the ground state. And then when you send a right pulse, you are going to scatter light, in particular, some of them into the guided mode. And if you detect a single photon in this field 1 mode, in the guided mode, then you are going to herald a single collective excitation. So you get this single collective excitation that you can store. And then later on demand again, you can send a read pulse, which is phase matched. And then you are going to read this collective excitation and to emit a single photon into also the guided mode in the direction opposite to the field. So if you want to characterize it, you can just forget what is in the middle, like in SPDC, look field 1 and field 2, and calculate what are the cross-intensity correlation between this field 1 and field 2, what we call G1-2. Exactly like in spontaneous parametric down conversion, it depends how strongly you pump your system. So for the right beam, so this is what this plot is giving you. P1 is a probability to get a click in field 1. So you can change this excitation probability. And you can see here that for a low excitation probability, where you are deeply in the single excitation regime, then we can go to a G1-2 above 100. So there are some operational benchmarks which are known in DLCZ kind of experiment. If you want to violate a Bell inequality, for instance, the G1-2 needs to be above 7. And if you want to make a rudimentary segment of a quantum repeater, as it was done in free space, you need a G1-2 of 25. So already with this system, we were showing that we are largely above these operational benchmarks, which was difficult because here you need a lot of filtering. So this is why it took a lot of time to do this experiment, because the atoms are trapped in this dipole trap, which is always on. And this trap is always on with a few milliwatts of light. So you want at the same time in this system to have the atom trap with milliwatt of light running into the fiber, and at the same time make at the cesium wavelength a single photon quantum optic experiment. So at the end of the day, we had some filtering, some volume Bragg grating, some cavities, and we ended up with an overall transmission above 50%. So we were not losing so much light, and still with more than 150 dB, 160 dB of noise rejection. And of course, it was very important to get this result. So then you can have other characterization. What is the retrieval efficiency? If you have an excitation, what is the probability to get it out? And you can see here that basically the plateau is at 25%. If it's too weak, then you have noise. If it's too strong, you go to the multiple excitation regime. But the plateau is a single excitation regime. And you can check that it is indeed the single excitation regime by measuring the G2, the conditional G2. So the single photon that you can generate actually at the output of your system. And you see that we can go up to 0.1 or below for this single photon. So that was really the first demonstration of a collective entangled state in a waveguide QED platform, which is an important step because in many proposals, it's also an initialization stage that you would like to create this entangled state and then make some further protocol. And we are showing here that it was possible indeed in this nanofiber-based system. So as I said, we are pushing this platform further now because we still believe it's also a very nice platform to go to high efficiency and long-lived quantum memory. But also, there are many other features that we want to study. I told you, for instance, making this Bragg mirror and controlling the Bragg mirror with a control field, so going to a three-level system and eventually with the control field inside the guided mode, then you will be able to control it at a few photon level. There are also many theoretical studies about super radiance and subradiance effects or selective radiance in this kind of system that we want to study, and many collective effects also. And this is a kind of platform that we would like to study with Radim, also to characterize the state we can generate from this ensemble of atoms. The last platform we are now developing is to add into the game the group index. So having some structuration of the waveguide. And that can be done with a photonic crystal slow mode waveguide. Again, it's not a cavity. It's a slow mode waveguide, something like this W1 waveguide, for instance, where you have a missing line of holes, and you can have a group index of a few tens. So you can increase in this way the interaction. So we are developing now, in the context of a French and European also collaboration, this new platform. So just to give you a kind of overview of this kind of light matter interface in the group. So we have learned to make very efficient quantum memories that we are pushing now in free space towards multiplexing and quantum repeater application. We are also controlling a few thousand of atoms in the vicinity of an optical nanofiber with all these effects of non-linearities, chirality, cooperative effects that we can explore in these one-dimensional arrays of atoms, and pushing now to a new regime where we will have at the same time collective effects, but also single photon addressing, having a large Purcell factor, all that in a single pass configuration. Just to summarize what I told you today, to give you an overview of the group for this first non-Gauss workshop. So Photonics Lab, which is a kind of test bed, I will say, in our collaboration with Radim about non-Gaussian state, and different cold atom-based platform that we would like also to include in all our studies for this twinning program. So I will stop here, and I will thank all my colleagues, postdoc and students, and also Dima Kuprianov in St. Petersburg, with whom we are collaborating on all this 1D platform. So thank you very much.
Thank you. I would like to thank Julien for a nice talk. And since next in program is a break, I believe we do have some time for questions from the audience. So if anyone has any questions or comments, please raise your hand and ask.
Okay, I'm raising hand and asking.
Yes,
Julian, I already wondered many times in these recent experiment in Optica with EIT, like when you show that the WV parameter is a function of P1, yeah, that it has clearly the rising tendency, right?
Yeah. So P1. So in a DLCD protocol, P1 is actually how strongly you excite your system.
Yeah.
So if you want to make the parallel with an OPO or with SPDC, this is the power of the pump. So that means if you push the pump, you go further in multi-photon components.
Yeah.
So if you want to stay in the single photon regime with very limited multi-photon components, you need to have a low excitation and so a very low P1. So this is a trade-off of SPDC and the trade-off that you find the same way in a DLCD experiment. Yeah. So we know that we want a very low multi-photon component in any case for a quantum repeater. So this is why we need to go to very low multi-photon components, either when you are using DLCD or when you are using SPDC source. This is the same game.
Yeah, yeah. And for EIT, when you characterize the memory using the same graph, there was this graph with the rising, in the rising profile of the dependency, and then you said that actually it looks that the G2 before and after the memory is practically the same, right?
Yes.
But this was as well tested in a low pumping regime, right?
It was
low excitation regime. It was this graph, yeah, exactly.
Yeah. So we were doing that at different quality of single photons, let's say, at different G2. The point we were using then is this one, you see here. So P1 10 to -3 because it was done in DLCD, so it's our way to quantify it. But if you look at G2 here, it's below 0.1 before storage and after storage. And we did it also for other points, but taking less statistics. But these are worse photons, actually. The one used in the entanglement experiment is this one, where G2 is below 0.1. And there is no change before and after retrieval.
For these worse photons, when they contain larger photon number contribution,
yes,
it looks like at least, yeah, it's maybe hard to guess, but it looks like that after the memory, there is a bit of more noise than actually before.
I will not conclude about that. I mean, I think just we didn't take much points about that, so there's no so many statistics. We are really focusing. I mean, if you look this point, you're already at G2 close to 0.5. They are useless for quantum network or whatever. So we are just showing this this characterization of the DLCD process actually. But the point we were focusing then to make the entanglement between the memories is really this good single photons with a G2 below 0.1. Where you see the error bar is much smaller because we took, of course, much more data.
But this is still like a very low probability of single photon contribution for the state which isn't coming to the memory, right? It's like the P1 is 10 to the power of -3. Which means
no. I don't remember exactly the number. No, because you start from so we have loss in the system. So I would say, yeah, maybe you're right. Maybe it was something like a few, maybe 10%. I don't remember the number. It's in the paper. No, the point is you start from a DLCD. So you create a collective excitation, and you know when you have it.
Okay.
Then you read it, and at the output of the single photon generator, the P1 was more than 25%.
Okay.
Then we have lost because we put a delay line to go to the memory because we are using the same system. But at least at the output of the DLCD, it was 25.
Okay. Yeah.
That was the same with the nanofiber. If you take the nanofiber experiment where we make this collective excitation, the retrieval efficiency, so what is the probability to get a single photon inside the fiber, so which is the P1 you're talking about, it was 25%.
Okay, perfect. Thanks a lot. Yeah.
So this is why it's already interesting for us to discuss about non-Gaussianity. When you have these kind of numbers, we are not at 50% for a negative Ignor function, but we are already at 25 for the P1.
Very good.
Okay, thank you. So since it seems there are no more questions, I would like to thank Gillian, Ulrich, and Radim for their talks today. And right now it's time to take a break, and we can meet at 1 p.m. for the next batch of talks. Thank you all.
Thank you very much.
See you for now.
Thank you, bye-bye.
Okay, hello everyone. We'll be soon starting our afternoon session. So I would kindly invite Nicolas to share his screen and check if we can hear him. And
yes, can you hear me properly?
Great, connection is great. Video, audio.
I will try to share my screen. So I will do something specific. Don't worry, I will do.
Just I would suggest to give a few more minutes because I think the people that are coming yet. We have about 34 followers watching us live on the stream, but still I think there are many people joining. So maybe some more, let's say 3 or 4 minutes would be nice.
Yeah, exactly. We will be starting at 1 as per program. So
okay, clear.
I just wanted to get ahead.
Okay, I guess you can see my screen. Fine.
Yeah, we can see your screen. We can hear you. So everything is ready. I'll then let you know when you can start. In the meantime, I'll take the opportunity to remind that everyone, both here and watching the YouTube, can ask questions through the Slido interface. These questions are stored throughout the whole talk, so it's best to pose them immediately as they occur to you. Other people can see those questions and they can vote on which questions deserve to be answered. They can add their own questions, so it is a nice tool to actually collect the questions and then relay them to the speaker. We are still waiting for the chair for this session, but
actually here.
Okay. Vladislav is already here, so chair for this afternoon session will be Vladislav Yusenko, and here, and I would then like to greet him and give him the word. So Vladislav, take it away.
Thank you, Peter, and it's my pleasure to welcome all of you to the afternoon session of our Non-Gauss workshop. And the first speaker of the session is Nicolas Treps from Laboratory Kastler-Brossel in Paris, and he will be telling us about non-Gaussian quantum states of multimode light field. Please, Nicolas.
Okay, thank you. So first of all, thanks all of you for setting up with this workshop within this consortium. It's a very nice opportunity to discuss and to collaborate all together. So this is really a great initiative, and thank you for that. So I decided to focus really on what we do, which is specific to non-Gaussians. I apologize a little bit for people in Olomouc that heard something quite similar 2 weeks ago or something like that. We didn't do a new experiment in the last 2 weeks, so I'm sorry for that, but I will show you, try to go a bit into details and get a bit of perspective. I will start this by doing a quick review of what I will talk about, a bit of if I can change my slide, sorry, a bit of a summary our experiment, and then I will come back to the details. And obviously, you're welcome to ask questions even on the way. So the story of this, I will tell you, started a few years ago, well, nearly 10 years ago, and the first good results we got was 2014. Somehow, is when we started to do a multi-mode state in the continuous variable regime with optical frequency comb. And so why did we started to work in such a regime? It's because, as you know, if you take optical frequency combs, if you look in the frequency domain, they are made of many frequencies, so which is many degrees of freedom. And if you look in the time domain, you have optical pulses. Optical pulse is nice because it has a high intensity, and thus you can hope to generate multiple pairs of photons using nonlinear effect because of its power issue. And if you do so, just slide again, sorry. This is the way you can see the kind of states you could hope to generate, and this is what I will try to demonstrate in the rest of the talks, is that you have many frequencies, and each of the frequency is a quantum harmonic oscillator. And if you use parametric down conversion to populate these many frequencies, you will generate a very general, let's say, Gaussian states. So this is why you have these Wigner functions out of all these frequencies. So you get a very large entangled state. At least that was the hope at the origin. And then, well, as we have heard today, this is Gaussian statistics. So this is not enough to do a quantum computer. We are still far from that, but to do something that cannot be simulated with a classical computer. So still some work to do there. And this will be really the focus of my talk today, beyond explaining how we do this large Gaussian state. We will try from this Gaussian state to go directly to a multi-mode non-Gaussian state. So, well, this is something, well, I still have this review here. We heard about that this morning. So this is, and anyway, the small review I did here is not exhaustive, but just to give a hint, which you know already, of the different methods, but somehow you can think that some part of the community tries to generate directly a non-Gaussian state in a deterministic way. So this is really the point of single photon sources. You know that a single photon is kind of the best non-Gaussian optical source. Then you can try also to do directly GKP state, for instance, in trapped ion. Or, and I will come back to that just after, try to deterministically do a cubic phase gate. And this was something which was proposed here in Olomouc, for instance, but which are quite challenging experimentally. So as you all know, in optics, we have the second option is to do probabilistic methods. The most common is to herald a single photon out of a parametric down conversion. This is to work in the DV, discrete variable regime. However, in our field, continuous variables, what people would do is a probabilistic de-Gaussification, let's say, of Gaussian states by removing a single photon, very similar to what Julien also was talking about. This was what was done in the group of Philippe Grangier, for instance. And through this kind of schemes, go to more complex photon subtractions or multi-mode photon subtraction or photon manipulations on a Gaussian state to do a GKP state or cubic gate and so on. What I will be interested in these talks is to extend the single photon subtraction process to the multi-mode scenario. And so this is a summary of the total experiment I will speak about today, and with the list of points I'd like to address. So what we do in our experiments, we generate multi-mode Gaussian states. Then we will implement mode dependence, so this goes beyond simply the beam splitter. So mode dependent photon subtractions to control a network of non-Gaussian states. So I will speak about very limited size networks, and if you want to go to larger size, you will follow the talk of Valentina a little bit later today. And then, yeah, I will go through these things. I will try also to study a bit how non-Gaussianity spreads when you have a cluster state, for instance. But let me go back in time a little bit and start to remind you or to give you some details on how we generate time frequency squeeze mode, which is the resource then for our system. Well, as I told you already, and maybe I will specify a bit more, we use an optical frequency comb. And here the numbers are important. So we have about 100 femtosecond pulses. We have two experiments. I will focus on the one when we have about 100 femtosecond pulses with 100 megahertz repetition rate. And this is very interesting. You know that optical frequency comb you can have. So now we choose 100 megahertz repetition rate. It was easy for our experiment, but this give you a natural clock rate somehow at which you can hope to do experiment. And then you have a broadband light. So here it's 800 nanometer central wavelength with a 10 nanometer width, and this gives you about 10 to the 5 and 10 to the 6 longitudinal modes. So this can be used both for quantum metrology and quantum informations. So in our group, we also spend some time doing quantum metrology, and also with Radim in particular, we try to think how can non-Gaussian state be applied to this kind of a quantum metrology. I won't speak about that today, it's a bit too preliminary, but that's also a research line to pursue. There's a lot of things to do there. I will focus mainly on the quantum information point of view. And first, let me try to do Gaussian state. So as I told you, the way to generate Gaussian states, non-classical Gaussian states, obviously, is to use parametric down conversion. So the good old one, when you have a single photons at a given wavelength, the blue in our case, that splits into two photons. So I guess you all know, but it's interesting to give some details still. What does it mean generate two photons? Is that you have these two creation operators that corresponds to two frequency lines here. And you have a coupling matrix, which depends on the two experimental parameters you have. One which is the pump amplitude. So it depends on the pump amplitude at the sum frequency, m plus n, and obviously on the crystal properties. And here, this is also a broad part of research, is how to optimize these two parameters to decide on the structure of the state you generate. In a nutshell, this is again the same slide as before. You generate pairs of photons that splits into many frequencies. You could wonder on why the frequencies remain discrete. The fact is, in our experiments, there's two ways to see, but in our experiment in particular, we will use a cavity that will set the available frequencies in your system. And before explaining it a bit more, I have that, so I think I would use, so which is a short movie of the experiment when you can see most elements. I will run it later, but here you see the laser source. So we did that for students that could not visit the lab because of the COVID situations, but then at least you can benefit from it too. So this is the laser source. This is where you prepare the light. In this plastics box, what is there is a cavity. I will show you just after. And all the rest, I guess, which is important in our experiment, and you see this all this black box here are spatial light modulators. I will come back to that, but this is what we use to do pulse shaping, so to control the mode we will address in our experiments. And the big stuff over there is a multi-mode detection system. Okay, so let me move to the cavity itself, so which is in the box here. So this is how the cavity looks like. We have a 4-meter cavities, and this is what I told you before, because you want a cavity with in an optics world with a free spectral range matches exactly the different frequency line you have in your optical frequency groups. In other words, and the cavity length corresponds to 100 megahertz. It's exactly 76 megahertz repetition rate of our laser. So here you have the nonlinear crystal and the light that goes out of it here. So one of the advantages to use a pulse light, as I told you, is that you have high nonlinearity. So there's two things you can do. You can use very short crystal, which is important to have a low dispersion inside your cavity. And maybe more important, you can use a low finesse cavity, which means that losses inside of the cavity are not that important. Still, if we are there, one of the limitations of this work, which we are working on, is the intracavity dispersions that come from air and mirrors and a bit of the crystal that limits the breadth of modes we can measure. So we have heard already of multi-mode light and large cluster states today. I want to precise a bit the vocabulary I will use. And using this slide. So this is well, not really mathematical. I have to set the notations and to really understand what we speak about, because as you have seen so far, our light is within only one beam. And how do you do multimode within one beam? Well, what you all know is that you have, if you take your frequency comb and you extract a single frequency, what you get is a plane wave, which you can see here. With the classical description of the function of the real and imaginary part of the two classical quadrature of your field. And this is where you get the usual Fresnel representation, so the phase space representation of your classical field. When you go quantum, when you go continuous variables, these two quantities do not commute, and you have, as I told you, a quantum harmonic oscillator for a single frequency. So now we have many frequencies. So what is a mode in our case? A mode is a given superposition of all these frequencies. So mathematically, is a vector f of dimensions 2m if you start with m frequencies, and 2m encodes for both quadrature, the amplitude and phase of each frequency. And when you take a frequency comb, you make a given superposition of all the available frequencies with a given amplitude and phase. What you are doing is pulse shaping. So what your ode is simply a pulse shape in time or in frequency. Which means that when I say we do a multimode measurements, it means in practice that we measure a given quadrature of a given mode. So if I take this mode F, I can measure amplitude quadrature of this mode F, which is given simply by the superposition of the X and P operators of all the individual frequencies with the weight corresponding to my vector F here. And as you see, when you do that, and this we will see quickly experimentally, we are able to do a pulse shaping to address this kind of modes. You have access to a very large number of modes experimentally. Let me stress, for those who are not used, I told you that we have 10 to the 6th frequency in this kind of frequency gomb. Experimentally, this is not accessible resolution so far. And you will see we can address only much less modes right now. Anyway, so this is what we do. And now when you allow yourself to measure in any modes, it means that you can write your Hamiltonian here in any mode, and the mode being a given superposition of the operator which are here. I wrote before a superposition of X and P in the quadrature space, but you can do the same in the creation operator space. So which means then that you can do your Hamiltonian is Hermitian, so nothing prevents you from finding a basis where your Hamiltonian is diagonal. So you move from a double sum to a single sum, where now your Hamiltonian corresponds to the creation of pairs of photons in eigenmodes of your systems. So this eigenmode, so here what you recognize is a sum of squeezing Hamiltonian. So sorry, each time the Hermitian conjugate are missing, this is just to make it simple. But this is a sum of independent squeezing Hamiltonian. So what you see is that parametric deconversion is nothing else than a sum of squeezers, but in a basis which is given by these operators that you can find by diagonalizing this matrix N. And if you do it for standard cases where so your pulse shapes are Gaussian and your phase matching function of your nonlinear crystal is close to Gaussian, what you find is that your eigenmodes are Gaussian function. Would it be in the frequency domain or in the time domain? And here they are represented in the time domain. And what this multimode Hamiltonian means, it means that when you generate two photons, these two photons will go in only one of these modes. So either in the first one, the second one, or the third one. So what your system consists in is a set of eigen pulse shapes, individually squeezed and non-correlated between each other. Well, I stress that because it means that in the same system, if you look in this basis of pulse shape, you see independent squeeze mode. But if you look in the basis of frequencies, what you have is correlations between photon numbers. So this is, for instance, a covariance matrix we have measured in the frequency domain. And sorry, each time I forgot to add to this figure the X and Y axis. I'm sorry, but this corresponds to wavelengths. So what we have done here is that we split our frequency domain into 16 parts, and we measure the covariance matrix. So you have the correlation is diagonal, the noise of each frequency is diagonal, and the correlations between two different frequencies of diagonal. So what you see here is that you have many correlations, while in this domain here, what you should have is many independent squares. So we don't have time for that here, but if you look in particular, this is a collaboration we got with Werner Vockel, looking at this kind of multimode states, and he could demonstrate that what you have is a really highly and completely multimode entangled state, which in whatever the partition you take of these states, you can prove entanglement. Okay, but then, sorry, let me go back one. Then this is to measure in the frequency domain to get your correlation. So what happens now if you want to measure in a proper basis? So would it be the eigenbasis or any of them? And this is the way we do. So we extend the usual homodyne detection using pulse shaping. So what you do is that you take your optical pulses and you shape exactly. So this corresponds exactly to the mathematical slide I've given you a few slides ago, because the experimental implementation. You spread your spectrum, you control amplitude and phase for each wavelength of your spectrum. Each, I mean, this is about 600 pixels in a standard spatial light modulator. You bring them back together again, and you get a pulse which have a complicated shape. So this is a time frequency representation of your pulse that you interfere with the output of our OPO cavity. And this is a projective measurement. So what you can do with that is get the Wigner function of this mode that goes out of this cavity. Okay, so in a nutshell, to summarize this part, what we get, and I'll show everything, what we show in our experiment, and this is getting a bit old already, is that if you measure in the frequency domain, you can show that you have a 16 modes which are entangled. If you use pulse shaping to measure in these time frequency modes, what we could show that we have up to 12 squeeze modes with a limited squeezing. I will come back to that if you want. And then you can think, well, what do I have to measure either in the frequency domain or in the eigenmode domains? I can do measurements anywhere in between. And making measurements anywhere in between, this is really trying to generate a given shape of your correlations, because I remind you that in the Gaussian case, all correlations, and this is what is here, can be constructed from basis change on a set of squeezers. And with that, we have been doing cluster states. So this is what I've been presented by Ulrich this morning. So in our case, these are much more limited size cluster states in this train of pulses. But what is a bit different here, so what you see on top is the shape of cluster we could generate. What is different here is that we never change the source. So the source is given by this cavity. And in order to reveal this different shape of cluster states, and here below what you have is the corresponding nullifiers or inequalities that prove that you have this shape of cluster state on top. What we do is we change the measurement basis. So in practice, when you move from one graph to a different graph here, what you change is what is the meaning of these different dots which are here. And each dot corresponds to a given mode, and a mode corresponds to a given pulse shape. So in our case, when you change which pulse shapes makes your dots, you will reveal a different cluster state or a different graph state. As said, this is interesting because it's versatile. I will conclude on that. It's far from the size of the cluster state in the group of Akira or Ulrich, or even the one of Olivier Pfister, and I will come back to that on my last slide. But in our group, what we decided to focus on is the application of this to quantum information. And this is also what Akira and Ulrich are doing, but in one point which we think is important for quantum information, which is, as we have discussed already, when you generate states with parametric down conversions, your Wigner function is Gaussian. Thus, all the measurement statistics you will get are Gaussian if you use homodyne detections. And thus, this gives a limitation that you can see in two ways. Because everything is Gaussian, you have no hope, because Gaussian Wigner function can be considered as a probability distribution. You have no hope to violate any Bell-like inequalities, at least with homodyne detections. And in another way, any Gaussian statistic can be simulated efficiently with a classical computer. So what you need is to go non-Gaussian. So you've heard about that with Julien this morning. So let me remind just quickly the concept as it was introduced by Philippe Grangier quite a while ago, which is that if you take a squeeze state and you remove a single photons, it's like applying the annihilation operator on the squeezing, and what you get is a non-Gaussian state. What is interesting is to think, I mean, in our case, of course, always interesting, but what's interesting in our case is to consider what happens if you apply that to a multimode state. So if you take our multimode state, which is composed of many squeezers in different time modes, and you have a beam splitter, and you measure a single photon here. What is the issue here is that you have a superposition of many modes, while your beam splitter here is completely mode independent. So it will treat all the modes the same way. There is no phase relation between them, which means that you don't know from which mode the photons come from. And this is really intrinsic to the way the beam splitter works, which means that what you will do is apply the annihilation operators as before to your squeeze states, but in a statistical superposition. So it could be I remove photons from the first mode, or I remove photons from the second modes, and so on. So what I get is a mixed state of a photon subtracted squeeze state. But then this results in a mixed state, which is completely useless for quantum information. What we would like is to have a coherent superposition of photon removal. So then you will keep a pure state in that case. So this can be done this way. And this is, as many of you know already, this is something which is introduced in particular in the group of Christine Silverhorn, which is linked to some frequency generation. And this is really, nonlinear optics is a magic tool for any quantum optics experiment. So what we do in our case is not use a beam splitter anymore, but use some frequency process. So what you see, some frequencies that you take photons from what I call the signal beam, a photon from the gate beam, and you upconvert in this way. So with small animations, you generate a photon here, blue photons. So if a blue photons goes into your detector here, you know that one and only one photon from your signal beam has been upconverted. The beauty of this is, on the one hand, you have subtracted one photon from the signal, but on the second hand, your nonlinear effects, and this is where what was explained by Christine, and Benny in particular, are mode dependent. So if I control the time frequency mode of my gate beam, I will control where I remove my photon signal from. So here, in this example, what I should get at the output is a state like that when I remove a photon. What I would like to do here is to comment a little bit before going directly in the quantum part on the classical part of this because it's important to show how multi-mode this kind of things is. So I decided to explain you how we did characterize this system at the classical level. So why do I say at the classical level? Because if you look still at the quantum level, what happens here? So if you have a signal here and a gate and you remove a photon here, if you know nothing about your system, the only thing you know is that you have removed one and only one photon. This you know because you place yourself in the weak interaction regime. So you rely on the fact that the probability to remove two photons is low. Of course, this means that it's a low probability, but that's... So if you don't know where you remove the photon from, what you get is that the output density matrix is a sum of all possible superposition, of possible photon subtraction in a given mode. So it doesn't have to be diagonal in the basis you consider. So what you have is that this chi matrix that tells you where you can remove this photon from, and it's a two-dimension matrix because you have a whole set of modes where you can remove a photon from. So if you want to characterize this matrix at the quantum level, it's quite hard. However, this is really an amplitude matrix. It's quite similar to when you do parametric down conversions. You can directly measure the coefficients here if for rho in here, you put current state. And if you put current state as rho in, what you will do is simply look at the probability, so the amplitude in blue, and that will give you the amplitude of its chi functions. So what we did experimentally is that we seed the signal here with many different modes. So here what you see in this graph, this 1, 2, 3, 4, up to 7 modes are, there's only 6 in the drawn here, but that's fine, are the 6 different pulse shapes we put in the signal beam for a given gate beam. So here the gate shape is fixed to this one, and we put signal beam for these 6 of these 7 different pulse shapes and for superposition of these pulse shapes, so to get the off-diagonal coefficients. But we do all that classically, and we simply measure what is the conversion efficiency for this kind of modes. And with that, you can reconstruct your chi matrix, and this is the result. So this is this chi matrix we measure in this Hermite-Gauss time frequency basis. And what you see is that in our case, this matrix has only one element and is very pure. It means that indeed, classically, you will get up conversions if and only if your signal is in this pulse shapes, and all the rest will not get converted. So this is really a tomography of your system. And then you can play by changing your gate beam. So we did, of course, all possibilities, but here I'll show you only a few. So I've shown you when I use the first Hermite-Gauss mode, no, sorry, the second Hermite-Gauss mode was for example here. Now I use Hermite-Gauss mode number 6 here, so which has to be highly oscillating. And you see we have a bit of crosstalks in this matrix, but it remains still very pure. So the quality of the photon subtraction, I didn't put the Schmidt number here, is something like less than 1.2, so it's still very good. We have a very good quality of photon subtraction. And you can do even more. You can, in your gate beam, you can use a complicated superposition of whatever pulse shapes. So we also decided to do a evenly weighted superposition of these 5 first pulse shapes. And what you see in that case is that your matrix corresponds exactly to what you expect. And calculating the Schmidt number, you will find it's very, very close to 1. In that case, it's better than 1.1. And then you have what you show is that at the classical level, you have a nonlinear process which is highly mode dependent with a very, very good purity. And because it is a nonlinear effect, and it's basically lossless. So I decided to include that in this presentation because it's good to show that this system is really highly multimode. It has a very good quality, and in the result you will see, nothing, of course, it's experiment. It's not all perfect, but this system, this part here, is of a very good quality. So let me now shows a complete experiment. So in the complete experiment, you have the TISAF laser that will go into the cavity, which I've shown you before. Then we have the nonlinear crystal to do the sum frequency and photon subtractions. And then we do a tomography of the state or the output for a given set of modes. Well, in practice, it looks like that. The first experiment you do is that you just do nothing. So you have your squeezing going through the nonlinear crystal. You don't do sum frequency and you do tomography. And what you see is that you have a Wigner function. So this I go quick on that, but just to remind you how these kind of things are done. And then we choose where we remove the photon from by putting here a given pulse shapes. We do the same tomography, so with our quadrature measurement as a function of the relative phase, so a function of the quadrature we look at. What you see is a typical I-shape system, and what you get is negative Wigner function in this first mode. So now if I can summarize in a way this kind of results. So I show the example with 3 input modes, a bit simpler. So what I've shown you is that if we place the gate beam, so the reference beam in the first mode, you get negative Wigner function in the first mode. Well, then what you can do is to change this reference beam to remove a photon from the second mode, and these are all experimental results you have here. And these are the reconstructed Wigner functions, and what you see is that for mode 1, you have indeed, again, a highly non-Gaussian state, and which is still negative. And then you can play around, as I told you before, by putting a superposition of modes here in your gate beam, because we know that our photon subtractor can handle multi-mode superposition. So here we put a superposition of these 3 modes, and you will notice with the I in between here. So as you see in this graph on the left, mode 0 and mode 2 are squeezed in the same direction, while mode 1 is squeezed in the orthogonal direction. So if you place an I here, it means that you remove photons from a mode which is squeezed, because now you put the 3 of them squeezed in the same direction. So now we remove photons from a mode which is complicated but which is squeezed, and if we do the tomography of this very same mode, what you see is again non-Gaussian Wigner function. I was hesitating, I'm not 100% sure, it's a negative here for this superposition of modes. So in a nutshell, these are the kind of results we find, is that depending on which mode we choose, we can have one Wigner function which is highly non-Gaussian and can reach negativity. Well, this is one part, which means that within a multi-mode scenario, we can get on-demand and well-controlled, not on-demand, but well-controlled negative Wigner functions. But what we are really interested in for further application is how you generate something which is multi-mode non-Gaussian, and in practice, how you can transfer and spread your non-Gaussianity. So in order to do so, we first looked at it theoretically. And just to give you a quick summary, I'm not going to explain everything. What we did simulate and did calculate theoretically is what happens if you take a given cluster state. And I insist, the theory, of course, applies to any modes in a continuous variable scenario. So, for instance, what I've been presented by Ulrich, the same analysis can be applied exactly. So if you take a cluster state, for instance, here made of 5 modes, and you remove photons from this mode here, so originally your cluster is fully Gaussian, but if you remove photons from here, what you see is that the whole cluster becomes non-Gaussian. So those non-Gaussianity spread within the mode. What is interesting in this example, for instance, is that the single mode Wigner, none of them here is negative, but the Wigner function of the total state is negative. Then you see that the negativity spread among the modes. And what we could show is that the negativity, sorry, not the negativity, the non-Gaussianity spreads 2 steps away. And because of the structure of cluster state, it is limited to 2 steps away. And to convince you of that, if you do that in a linear cluster, so this is a 7-mode linear cluster state, you see that you remove photon from the first mode, non-Gaussianity spread 2 steps away, but the remaining of the cluster is completely unchanged. It's exactly the same as before. If you remove a photon delocalized from 2 modes, which we can do, then everything which is 2 steps away from your 2 modes becomes affected, but the rest is completely the same as before. Another thing which is important here is that theoretically it's nice because we can calculate and draw a nice Wigner function. Experimentally, this is another story. What is the point is that you have 2 problems. Well, if you want to measure all these Wigner functions, it's a lot of measurement times. So this is one issue. But in fact, if you want really to reveal your full quantum state, you should also measure all the correlations. So you have to do a complete tomography of your quantum state. Obviously, when you have a Gaussian state and you want to do a complete tomography, it's simple because you can use the covariance matrix. So that's fine. You have a limited size measurement. However, when you're non-Gaussian, you have to measure all the moments. So you get exponential complexity as a function of the number of modes. So experimentally, it's not tractable anymore. So we need witnesses. There's a lot of work ongoing in this kind of witnesses. In this work here, we're doing something very simple, which I will explain just after. We just look at the kurtosis of our modes, which is not enough completely, but for what we wanted to do here was enough to reveal the quantum state. So that's to show you what we have done experimentally. So now we move to experiments. We took a 4-mode cluster state out of our system. We look at the kurtosis, I just told you. So kurtosis is simply the first order moment, renormalized so that it is equal to 0 for a Gaussian. And these are the experimental measurements we have before photon subtraction. And after photon subtraction, what you see is that it deviates a lot from the Gaussian case. And what is important is that we remove the photon from mode 1, which is this one here. And what you see is that the kurtosis really is changed from mode 3. So what you have is a spread of or transfer of the non-Gaussianity from mode 1 to mode 3 in this case. And the other thing which is interesting is that you see that in blue now is what we calculate theoretically as a function of the covariance matrix we have. And what you see is that we have a very good agreement. And this corresponds to what I told you at the beginning, is that in our experiment, in fact, it might be surprising, but what limits the quality of the results we get here is not the photon subtraction itself. So we have a very good mode dependent of subtraction, very low dark count and so on. So this works very well. What limits is the fact that the original covariance matrix is a bit noisy, meaning that the input state is not completely pure. And this is also mainly due to some technical effect, like dispersion in the cavity. I'll be happy to discuss this point if you're interested. So we also, maybe there's no need to spend too much time on that. We also looked at a linear cluster, and we show a bit what I've shown you before by removing a photon in mode 4 here, we have negativity in mode 3. In a superposition of modes, we have negativity, non-Gaussianity in mode 4 and so on. So we can transfer this kind of non-Gaussianity. I would like to finish these presentations by giving you a bit of insight on what are indeed the exact conditions to induce Wigner negativity. So now, if you place yourself in a scenario, multimode scenario, and you want to use photon subtraction, for instance, to generate multimode Gaussian states and spread this non-Gaussianity and go to Wigner negativity, which is what you really need for quantum informations. What are the conditions? Well, the conditions are, as I told you, it's a multi-mode scenario, but in fact, you can write them only in the two-mode case. And if you consider this two-mode doesn't have to be pure, in fact, it applies to any two modes within a graph state. So the only thing I assume here is that this two-mode state is Gaussian to start with, but it doesn't have to be pure because it can be embedded in a large cluster state. And what I want here is to perform a measurement on operations on the left mode, which I call G, with a given operator, which is in particular a POVM element of a measurement operator. And given I measure this POVM, I want to know what is the state I generate here. So you will see the states here want to look like a GKP state, but we are very far from generating a GKP state here. This is just for illustration. What we get here is a conditional state. So we get the density operator of this state as a function of a measurement of A. So the questions we want to answer here is what are the properties of the conditional state Wigner functions, and what are the requirements on rho, in particular at the beginning, to induce Wigner negativity. So as per you, all the calculations, but I still decided to give a little bit of details, not too many. So we perform this calculation using the Wigner function formalism because it's a bit easier. So if you take the Wigner function of your complete state, what you have then is the Wigner function of your measurement operator as a function of the quadrature of mod G, so which is what this xg stands for. And then you have the Wigner function of your mod F upon measurement of A and as a function of the quadrature of X. And this you can show that this is simply equal to the mean value of A knowing XF, so it's like a conditional measurement of A, time the Wigner function of F itself, so time the reduced function of F. So what you have is this conditional Wigner function is in fact the original Wigner functions multiplied by the condition measurement mean value. And then, so this is just to give the notations, and then you look at how you can get nonlinearity and what you can extract. I didn't put back the reference, sorry, I forgot that, but this is a known result. What is known is that the Wigner function in G knowing F, so this is your conditional Wigner functions, is a physical one, so it means it does not violate Heisenberg inequality if and only if you don't have EPR steering between F and G. And this is for the Gaussian state. This if and only this is valid because we start from Gaussian state. Well, if you accept this result, which is known in the literature, is very interesting because the fact that the conditional Wigner function does not violate the Heisenberg inequality means that your conditional Wigner functions of xj, of G mode, describe a quantum state. Thus, if it describes a quantum state, a physical one, it means that the mean value of any measurement operator, and in particular the one you're interested in, is positive. It's a proper measurement operator. So the measurement of A condition on the value of the measurement of xf, if the original, if this one is a physical, it's positive. If this one is positive, it means that if your Wigner function, which is up there, this term here is positive. Because your original Wigner function is a Gaussian state, is also positive, it means then you cannot have a Wigner negativity. Okay, so here you see that there are links directly between Einstein, Podolsky, Rosen, and so if you don't have any EPR steering, then you cannot generate Wigner negativity by making measurements in G. Okay, and this is boiling down to the fact that the conditioned Wigner function is a quantum state when you don't have EPR steering, which is, by the way, the definition of EPR steering. Just maybe I forgot to say, EPR steering is really when you do measurements, then you can violate in Heisenberg inequality. So this we have generalized, and now I don't give any more detail. I just give you the results. So what we could prove, what I told you, is that EPR steering is a necessary resource. This is what I've just explained you. But more than that, EPR steering is a sufficient resource for conditional preparation of a Wigner negativity. But for that, you need to work a bit more. Photon subtraction is not enough. You have to introduce a slightly more general measurement operator, which is photon subtraction in between basis change. So you have first to do not basis change. You have first to do a Gaussian operation, so which can include some squeezing on G, and then do a single photon measurement. And if you allow yourself for this kind of measurements, then EPR steering is a necessary and sufficient condition to generate a Wigner negativity. So this is a very nice criteria because it tells you when you have a cluster state, when we have usually, which is Gaussian, where we know very well the covariance matrix, then we have a criteria that tells us if I make a non-Gaussian operation in that node, do I have any hope to generate Wigner negativity in other nodes? To finish on that presentation, and I'm nearly there, just to say one word about our experiment. So we didn't do all these possible measurements, but what we did was to check, do we have EPR steering in our experiment? So to do that, sorry, the representation is a bit different than before, but this is the optical spectrum of our multimode state in the Gaussian case. And what we do, we split it in 4 parts, and we look at we have steering between 2 of these parts. And we even have done a bit more, is that we allowed ourselves that within each part to redivide in 2 or in 4, and to do a basis change inside to optimize this steerability. And what you see is that depending on the number of partitions you allow yourself for, so the triangles is that when you don't do any subparts, and when you go to the square that you allow for 2 subparts and the circles to 4 subparts, what you see is that except for a small subset, most of the cases we have steering in our experiment, which means that in fact you have a very large opportunity to transfer Wigner negativity in our experiment, which, as I've shown you, is quite noisy. It's not completely pure, but still, it's a sufficient resource to have many possibilities of transferring negativity in our case. Well, it's time to conclude. I decided I will do not too long, but I want to say a few things on this last slide. So this is our experiment, as I've shown you before, and I want to comment a little bit on what we want to do next in this experiment. And there's quite a few things you can do. First, I told you one of the main limitations in our case is twofold, but is really linked to the Gaussian source, so to the cavity here. So one is the intracavity dispersion. So this we are working on it, just technical. Another one is we didn't put here, but it's a spectral width of the modes, and so we are working on expanding our local oscillator spectrum. But then, well, one of the main limitations of what I've shown you is that when we make a measurement, we measure one mode, which means that we destroy all the others, and this is not what you want for measurement-based quantum computing. So what we have done already, I just didn't show you a result directly on that. So we did implement multi-pixel detection, so where you can measure all frequencies, well, in practice 16, at the same time, and have a direct measurement of 16 modes in your experiment. So in what we have done so far, quantum efficiency is not enough yet. So we are working on improving that. But then now it means that the basis we measure on is defined by this frequency basis. Well, you still have 2 degrees of freedom here. You have one, so when you make 16 measurements, you can still do by post-processing a basis change, so to adapt the mode basis you want. But the other one that we are implementing now is that we can do pulse shaping. So we can change the shape of the pump of the process. And if you change the pump of the process, you change the eigenmodes of your system, and you can try to adapt to this multimode scenario. And in particular, so this we are doing a lot of work on that, and both at the theory level and the experimental level, how we can make a tomography of our multimode non-Gaussian states, and I recommend the two posters from Mattia and Ganel this afternoon. Then what we can do, and this I will be very quick because Valentina will speak about that, but you know what Ulrich had been presented, this time multiplexing way of generating a million of beams, so which was originally introduced by Akira Furusawa, but that also Ulrich is doing. But it turns out that in our case, in fact, if we do experiment without a cavity, the modes here can be single pulses, and it's quite easy, let's say, to extend what we do to this scenario. What is not easy is to do the single pulse experiment, and Valentina will speak about that. But once we have that, it's not hard to move to this time beam multiplexing, and thus to combine the time beam approach they developed with our multimode approach here. Well, finally, let me acknowledge, so this is a whole group, at least as far as the name are concerned. So this is all people in the group, so that includes all our activities, would it be in quantum metrology with spatial modes, quantum networks, and so on. In italic are the people that left recently the group, and this is a picture that starts to date a little bit. I think it's close to 2 years old now, at least 1.5, where we could still gather together, and as everybody, you know that this is what looks our group meeting right now. Hopefully this is soon over, and we will be able to do a meeting all together. But in the meantime, thank you for your attention, and I'm happy to answer any question.
Thank you, Nicola, for the very interesting talk. And we have a bit of time for discussion. So I see there are questions from the audience. So the first question is concerning the cavity imperfection. So in the presence of noise, meaning cavity imperfection, generated multimodes are correlated, or as far as I understand, or are just collection of many modes? If correlated, then what would be the correlation? What could be the correlation type?
So yeah, it's not easy to answer questions written because I'm not completely sure I got exactly the questions, but anyway. So first, the fact that the modes are correlated or not depends on the basis you choose to measure them. So if you're a pure state, you're always a basis where they are uncorrelated. When you add some losses, then indeed losses can induce classical correlations. And these classical correlations that remains because of losses, there's nothing you can do with it. This is losses, and you cannot rechange basis, because if you rechange basis of the classical losses, then you will have quantum correlations due to the eigenmodes. So if I understood well the questions, there's not much you can do apart from limiting the losses, because losses indeed will induce on a spurious correlation. So they will decrease purity, and if they are not in the same basis as your eigenmodes, they will induce some classical correlations that you do not want. So they reduce purity, and not much you can do with it.
Thank you. And another question concerns the macroscopicity. So does the existence of additional modes put any limitation, like increase in macroscopicity under proper condition, that it kills the quantum character and increases classicality?
Sorry, I didn't get the question.
I guess the point is that in the presence of many modes, if we're still able to see non-classicality of the states, I guess it also depends on the measurement.
Yes, so exactly. So what theory says in our system is that we have indeed many modes. So we are far from measuring all of them. And then indeed it boils down to how mode selective your measurement is. So if you have many modes and your measurement is not mode selective enough, it means that when you make a measurement, you will collect a little bit of the modes you don't want. And this will, again, end up, it's like kind of noise. And these are things we can see experimentally, in fact, because experimentally we have done measurement both with the multi-pixel detection here, which has, well, in practice, what we did 8 pixels, so which is not very mode selective. And here you can see the purity of your measure is lowered. While when we do measurement of a single mode with Pulse Shaper, when it's much better in a mode selective point of view, the purity of what we get is much higher. So indeed, at the end of the day, what is important is the quality of the measurement. But we are happy with many modes. This is good.
Thank you. And there's another question. One of the participants asks to elaborate a bit on why you need to do Gaussian operation before doing photon subtraction on a particular mode in order to observe Wigner negativity.
So if I got well the question, that is why do we do non-Gaussian at all? Is it?
Why do you do Gaussian operation before doing photon subtraction?
Sorry. But if you do a photon subtraction on the current state, it doesn't do anything.
Yep.
So this is not what you want. What you could do is do a photon addition. But still, what we want is to avoid. So otherwise you go to DV. What you could do is generate many single photons, what people do, and generate a cluster in the DV regime. What we hope is that if we start from a cluster state which is Gaussian, then you can benefit from the fact that you can deterministically generate a high dimension cluster states and use few or fewer, at least non-Gaussian operations to get something interesting. I guess that would be the main answer.
All right, and there's another question. We still have a bit of time. So kurtosis is a classical measure of non-Gaussianity. Have you looked at quantum non-Gaussianity of your multimode states?
Yeah, so this is a good question, but I try to explain. Well, anyway, so I need to show. Kurtosis is what we could do at that time. So unfortunately, we were not able to implement criteria of Gaussian non-classical or non-classical Gaussianity or non-Gaussianity. So for this, we need more data and more complete tomography. And we discussed these things with Radim, and we are still looking from what is the best test we can have for this within this multimode scenario, demonstrate something which is purely quantum. So this is indeed so for a single mode, it's easy. As soon as we do tomography and show Wigner negativity, it is fine. Within a multimode scenario, we still need something which is tractable experimentally. And so we have 2 questions from the audience here, I can see. From Radim and
Flat, you're muted.
Yeah, I see no other questions, if I'm not mistaken.
Oh yeah, but, we are directly in the chat with hands drawn. So if I can, I have just one quick question. In your results, you shown that you managed to do like 12 or 16 modes.
Yes.
Do you foresee how much you could scale it up? Like how many modes is achievable in principle for you?
So yeah, so what we are doing with our aim with Valentina is to go, let's say, to 30 or 40 modes. So it might be easier to do in the experiment you will present, which is single pass without cavity, because the cavity dispersion is really a limitation. So with cavity, my hope is to go to 20 modes, let's say. But with cavity, what we are doing is first we are trying to improve the quality of the modes. The advantage with cavity is we can get more squeezing. So there's something we can do that we cannot do without cavity. Without cavity, I really hope that 40 modes is a reasonable goal. That's it.
Thank you.
Okay, it will be as well quick, because nice talk. Can you show back that figure in which you characterize the subtractor for the different modes? There was kind of like a table with Wigner functions. Some of them on diagonal were negative. Yeah, exactly here. Yeah. It means, if I understand that well, then there is still a little bit of the crosstalk between these orthogonal modes, right?
Yes.
It means how did you actually optimize for the best result? Did you optimize for the largest negativity, or you just tried to decompose to the Schmidt modes which are orthogonal, and then you left that and plot the
No, indeed, here we optimize with negativity. So we try to match the best possible way the squeeze eigenmodes with the gate beam.
Okay.
And yes, there is still a little bit. It's not much. It's due both to. It's a small effect, but that indeed is there. You can see a slight change in the Wigner function of the other modes. It comes both from a bit of losses which are induced by the photon subtraction itself, a very little bit, and indeed from the fact that
what surprises me a little bit is that there is like a noise. The noise track is kind of phase dependent in both or in all three other modes.
Yes.
It looks like that there is still something
sorry, I'm not sure.
Just the noise caused by loss, I guess.
I'm not sure what you speak about here, because here in the first column, they are phase dependent because they are squeeze states.
Yeah, sure. I mean for AG1 and AG2.
So AG1 is here. So I'm not sure what you mean, because here it's phase dependent because it's squeezed. All these modes are squeezed. Except here it's a squeezed photon subtracted states. So this is normal.
It means you are sure that there are no residual correlations between these modes, which basically we could use to maybe improve the negativity.
Well, there might be, but it's a very small compared to. So this we can, especially when we work only with three modes, we can really place ourselves in the basis, which is very, very close to the eigenmode basis.
Okay.
So you have a very slightly bit of remaining correlations, but it's very small. That's not the main effect you would see here.
Okay. Perfect. Thanks.
All right. We are running a bit out of time, so I would like to thank Nicola once again for the talk and for the discussion. And we are moving to the next talk.
Okay, thank you.
Thank you, Nicola. So the next speaker is Alexander Hack from DTU. And he will speak about open cavity with diamond with germanium vacancy centers. Please, Alex. We don't hear you. Microphone probably is muted.
All right, so now I'm here, I hope.
Yes, we hear you.
Thanks very much. Okay, super. Thanks very much to the Alamos team, actually both for setting up this nice program and also this workshop today, and giving me the opportunity to talk here and present our talk about our projects and activities, which is on interfacing germanium vacancy centers and diamond with an open cavity system. And so I would like to, now here we go. So as Radim already pointed out this morning, kind of I think we're on a transition, actually going from pure quantum physics, quantum optics in the direction of quantum technologies. And this is quantum technologies in the context that we try to find new technologies, new solutions to physical and general scientific problems. And but this also requires actually that we find new classical technological solutions actually to make use of quantum physics and implement and demonstrate scalable technologies. And one of those solutions, I think, is kind of provided by color centers in diamond. So diamond in this context is like so I see this as a wide bandgap semiconductor material with a bandgap in the range of 5.5 electron volts. So it's sort of relatively large compared to other materials, and if I have pure diamond, then this is it can be considered as sort of a solid state vacuum environment. But then at the same time, I can dope it. I can dope it with defects, and some of those defects, they have extremely well-defined optical transitions. Now, we also have learned over the past decade or so that there's many spins in the diamond. These spins can have long coherences, and now what we try to attempt here is sort of to interface such a diamond crystal with single color centers. So the diamond crystal can be seen here in the background with an optical fiber. The optical fiber is coming in from the right hand side. There's a nice little cavity forming between the fiber and the diamond, so that we eventually try to determine and create a very efficient interface between the color center and a single optical mode, which is supported by this optical fiber. And sort of such a system of this kind, I think, or we hope is relatively robust. So the color centers, the optical emitters, they're kept in place by the diamond crystal. Diamond can be made very pure, so it is a nearly perfect solid state vacuum environment, and sort of a system and interface of this kind then can hopefully yield applications for like forming a single node in the quantum network, where it can be made to generate a quantum repeater structure, the spins with long coherences that can be used as a memory, and so on and so forth. And then more in the context of our group, so this is I want to just put your attention onto a proposal which already Ulrich mentioned this morning. So it's about the generation of a GKP state, a proposal which was put forward by Jacob and Ulrich. So it basically relies on that I have a squeezed vacuum state which is being displaced, and then this state is scattered on a cavity system which contains a free-level atom. So this free-level atom could be a color center and diamond. When the ground state of that system is put in the superposition state, a controlled rotation gate is being implemented. The measurement in the superposition state then sort of projects the input state onto a superposition and repeated in a repeated fashion. That scheme eventually yields to the generation of a GKP state. So that would be a nice application, and this is, I think, a good motivation what we're heading towards to. Now, this sort of brings me to the outline of this talk. So I would like in the next 40 or 45 minutes address color centers in diamond, more specifically the germanium vacancy center we are working with. Then I would like to present our activities on GV center coupling to a microcavity system. This is all done at room temperature. And then in the last part, I would like to go a bit deeper into our current efforts, which is about the cryogenic integration of that system, hopefully towards achieving a coherent interface between optical mode and the color centers in diamond. Now, so I thought maybe before going into GV centers, so I thought maybe taking a little detour. So when we talk about color centers in diamond, I think what most people, or what comes to the mind, the first place of most people is the so-called NV center. So the NV center is kind of constituted of substitution of nitrogen atom replacing a carbon atom in the diamond lattice sitting next to a vacancy, and has sort of the nice property that when I excite the diamond, which is rich in NV centers, when I excite this diamond with green light, then the diamond sort of lights up in a nice red color. And the most intriguing feature is that if I now at the same time sweep a microwave frequency across, then I sort of see a dip of the fluorescence, of the brightness of this red light at the resonance frequency of an electron spin. And the electron spin is kind of kept by the NV center. Now applying a magnetic field, the precession frequency of this electron spin can be changed, and the change in this precession frequency then can sort of be used as a measure for an applied magnetic field. And sort of this property, which is termed optically detected magnetic resonance, is sort of the main feature which has caught a lot of attention and interest in diamond color centers over the past 2 decades, and can be used to sense magnetic fields with extreme resolution, so down to the nanoscale, down to the nano or picotesla magnetic field range in extreme environments, and also within biology, because diamond is essentially an inert and a very robust environment, which works very nicely at room temperature and even at high pressures. Now, the NV center itself, so the electronic properties is one aspect, but then actually in the diamond environment, I also have a lot of nuclear spins, or not a lot, but some nuclear spins. And the nice part about nuclear spins is that they about a factor 1,000 times weaker than the electron spin actually interact with the environment. So at room temperature, I have nuclear spins which have a coherence time which is in the range of milliseconds to seconds. And those nuclear spins again can be coupled via the hyperfine interaction to the intrinsic electron spin of the NV center. So this is coupling strength, which is in the range of megahertz, or a few megahertz up to 130 megahertz for carbon 13. And now the aspect is pretty much that I can use, as I've shown on the previous slide, I can use the photon electron spin interaction. I can use this to initialize and to read out the electron spin. The coherent part of this interaction I can use for communication. So having a coherent interface between the photon and an electron spin. And now the hyperfine interaction between the electron spin and nuclear spin can be used for coherent control of nuclear spins. I can implement gates, or with the long lifetime or coherence time, I can use the nuclear spins essentially as a memory. And sort of this set of properties of that system has led to a number of very important results. So for example, the spin photon entanglement has been shown, error correction, or even the loophole-free bell test. Now, this sort of sounds all very nice, but there's a little downside to the NV center, and that is basically when looking at the optical transition. So even when cooling the system down to a temperature of just about 4 Kelvin, it is essentially only about 3% of the total optical transition which goes into the zero photon line. Yeah. So the optical electron spin interface is extremely inefficient of that system. And more precisely, so we're now sort of investigating this optical transition in detail. So performing repetitive scans of this transition, I kind of see that the optical transition is not very stable. So it's typically it's typically oscillating actually quite significantly, an effect which is termed spectral diffusion. Now in ultra pure diamonds, so diamonds with a impurity level concentration in the range of parts per billion, and annealing at extremely high temperatures above 1400 should be degrees Celsius. Sort of I can purify the environment, stabilize the emitters, and kind of get very stable and nice transitions. But engineering such a transition kind of is really a challenge, in particular for nanophotonic or nanostructured devices or diamonds, which is important for technological applications. Now the underlying effect is basically that the NV center has a non-centrosymmetric structure. So that is that it actually contains this extra electron, which is mostly contained at the lattice vacancy site. At the same time, the nitrogen gives away one extra electron. So that is actually, so this is the structural property which gives rise to that the NV center has a permanent electric dipole. And the permanent electric dipole sort of gives rise to the observation of the linear Stark effect. So applying an electric field, so one can observe a linear shift of the transition of the optical transition energies with a slope in the range of gigahertz per megavolt per meter. Yeah. So when looking at those kind of numbers, that basically means that at even single charge fluctuations, which are in the range of a few 10 to hundreds of nanometers away the color center kind of give rise to energy level fluctuations within the line width of the optical spectrum. Now, so what is the solution, or what is the way around this? Well, I mean, the NV center is perhaps extremely nice and extremely powerful when it comes to sensing and when it comes to spin physics, but it is maybe not the ideal candidate when it comes to optical transitions. So maybe the question is, well, among the more than 500 known color centers and flavors I have in Diamond, so maybe there's a few of them which have also very interesting and very interesting optical properties. So, and in fact, so looking at the carbon group elements, so there's a set of color centers which are known as the silicon, the germanium, or the tin vacancy center. So these color centers, because of the atomic size, actually do not form a substitutional defect center, but actually so in that case, the color center is lying in between two vacancies. So this gives rise to a centrosymmetric system. It does not carry a permanent dipole moment, and at the same time, because it's the same atomic group, so it's also not a dopant, so there's no free charges, and one can expect a higher stability. So in fact, investigating the optical spectra of these color centers, one actually can observe a very sharp zero phonon line, so low scattering into phonons, and this is up to 60% at room temperature into the zero phonon line. For the silicon vacancy center with a transition around 740 nanometers, germanium vacancy, a transition around 600 nanometer, or the tin vacancy center with a transition in the range of 620 nanometer. And more precisely, so the line width of a single color center, or a germanium vacancy center, is typically about 5 terahertz, even at room temperature. So the level structure is a bit more simple. So I have an optical ground and an excited state. These are orbital states split by about 2 electron volts for the GeV center, and then due to spin orbit coupling, those orbital states are further split up with a frequency around in the hundreds of gigahertz range for the ground state, and about terahertz for the excited state. Now here on the right hand side, so this is an investigation of the spectra of single GeV centers. So this shows about consecutive spectra of 20 emitters. And what we see here is the main transition line, and it's actually so what it displays is a rather narrow low inhomogeneous broadening. So this is kind of the promising feature, why I think they're interesting, or why it's a promising candidate to investigate in such a system. Then another feature I wanted to highlight, and this is the possibility to measure indistinguishable photons from such a system. So this is a result I took from the group of Fedor Jeleczko at Ulm University, and it shows, and this is representative for native silicon vacancy centers. So what I have done here is to grow a diamond. During growth, dope the diamond with silicon, so it spontaneously forms silicon vacancy centers, and that's kind of the way how you obtain single color centers with the lowest amount of a disturbance to the environment. Now, what is shown here are sort of two different measures, two different measurements. So it's an aerial scan of the transition frequency of branches of the color centers along two different crystal directions. And what you can essentially see is that the transition frequency of one crystal direction here labeled in blue and another crystal direction labeled in red essentially falls exactly into two different branches of the spectrum. And the inhomogeneous broadening is to such a finite extent that you can obtain two photon interference or homomundal interference from two different color centers without external tuning. So essentially addressing two color centers individually, interfering them on a beam splitter, you observe a nearly very significant homomundal dip in the experiment without applying external control fields. Now, sort of this set of property now brings me to the next part of this talk, which is about the coupling of a GeV center to a microcavity system. Now, because cryogenic integration is always sort of a tricky part. So in the first part, I would just address a room temperature experiment, which we carried out a couple of years ago. Now, for interfacing an emitter with a cavity in the solid state, so there's sort of two different ways of how this can be achieved. One of them is an integrated cavity. The other one is an open cavity. So in case of the integrated cavity, what I essentially do is I take my solid state matrix, I localize where's the emitter, and then I start to build a cavity just around this single emitter. So what I do obtain in the end is a single emitter with a single cavity, one system, one realization. Now the challenge in that case is, or the benefit in this case is that I can make photonic crystal cavities with an extremely small mold volume. So tuning such a system in the right way kind of brings me mold volumes which are just of the order of lambda cubed. So I can have extremely high mold confinement, but at the same time, processing diamond is really a challenge. So making such cavities with high quality factors kind of imposes some technical limitations. And for this reason, we have decided to actually go for the open cavity system. So in the open cavity system, it relies on a flat diamond material. So this is just a slab of diamond, which is located on a bulk optical mirror. The diamond contains color centers, and then the cavity is formed between this flat diamond composite system and an optical fiber, which is processed and encoded in the right way to form an optical cavity. Now, the advantage here is that I do not only build a cavity just for one emitter, but essentially I can locate different emitters in the environment, select the emitter which has the needed properties, and then address this in the most efficient manner. On the other side, the challenge with the open cavity is that because it is not monolithic, I'm very prone to fluctuations. So stabilizing the cavity within the line width or within the finesse is sort of a technical challenge which has to be addressed. Now, I'm processing the cavities. So the first part we need to do is kind of to form a concave mirror at the end facet of an optical fiber. So this is a process which is relying on a tightly focused CO2 laser beam with a wavelength of about 10.6 micrometer. So it's infrared light, which is very well absorbed by a silica optical fiber. So cleaving an optical fiber brings me a nice interface. Tightly focusing an infrared laser locally melts the material and eventually remelts and forms a concave optical mirror. So like shown by this interferogram here on the left-hand side with a radius of curvature in the range of 40 micrometer. Now these elements, both the flat mirror and the optical fiber, can be coated with DBR mirrors. Such mirrors are straightforwardly engineered and designed. So here on the right-hand side, I show the transmission spectrum, both for the flat part of the substrate and the optical fiber, and they're made in such a way to obtain on resonance, so around 600 nanometer for the GeV center, a transmission coefficient which is in the range of 10 to the power of -4. Both for the fiber, that's the black line here, and the purple and the orange line, which is the flat mirror or the flat substrate containing the diamond. So with a transmission in the range of 10 to the power of -4, that yields a cavity finesse, which is around 10 to the power of 4 to 10 to the power of 5 to 10 to the power of 5, which is sort of in the range of state-of-the-art values which can be achieved. Now, so there are two different cases for the flat substrate. The orange line is without the diamond. the purple line is with the diamond, and it's, as we see, when adding the diamond is a high index material. Adding the diamond kind of slightly improves the reflection coefficient, and it will be nearly equal to the transmission of the fiber mode, such that the light being generated in the fiber can with nearly equal probability sort of escape through the two different sides. We typically sort of pump the system either on resonance of the emitter or off resonance. So for this we use a green laser at 532 nanometers, and for this purpose, so to avoid coupling of laser light of green pump light into the fiber, so the fiber itself is highly reflective coated at the green pump wavelengths, while the flat substrates are highly transmissive. So we're able to get light into the system. Now, diamond processing is a rather it's not a simple process, but it's a rather straightforward. So in the approach of an open cavity system, it only requires a planar etching of the devices. So typically what we start with is a commercial diamond of this kind, as shown by the picture here. So that's a diamond plate with a thickness in the range of a few hundred micrometer. It has a cross section of a few millimeters square. So what we do is we first thin the samples down to a thickness of between 50 and 100 micrometer. Then these samples can be implanted with ions. In our case, it is germanium. High temperature annealed yields the color centers, while the energy of the implantation kind of determines the depth. So this is optimized to implant the color centers at a field antinode of the cavity. Annealing activates the emitters. Then the sample is being flipped around and finally thinned down in a dry etching process to a thickness which is just about a micrometer or even less. Now, what is of utmost importance for an approach of this kind is the surface roughness of these diamond plates. So diamond has a high refractive index, about 2.2 or 2.4. So this gives rise to a single interface diamond air reflections, which is around 20%. So what is of utmost importance is to keep the surface roughness to a very low level in order to avoid Rayleigh scattering from the device. So what we need to keep in mind is that we have a target finesse which is just about 10 to the power 4. So that means any kind of reflections or scattering from the surface due to Rayleigh scattering, which is in the range of like one event in 10 to the power 4, so would actually spoil the cavity and sort of make the system not usable. So a typical experiment now looks like this: that we load this diamond crystal onto the DBR mirror I've just shown before. We approach this, we insert this into a microscope, and from the backside through this flat mirror, we excite the system with green light. This is all at room temperature. Now the substrate is highly reflective for the emission line of the color centers. So in order to observe emission, we approach it from the other side with a microscope objective bandpass filter. The emission or the fluorescence light at 602 nanometers. So this is the transition line, and then scan at the transverse plane, and we scan the diamond sample across the focus of the pump beam, and then plot in this color plot we plot the fluorescence signal recorded with an APD. And then like in any confocal scan, so we ideally observe a number of bright spots. Then we can sort of focus onto one of those spots, analyze the properties in more detail. And so for instance, for the spot up here, which is nicely isolated, recording a second order correlation function, we see a nice dip at 0 time delay. So this nicely indicates or strongly indicates that we're actually indeed investigating a single germanium vacancy center. Then at the same time, you might maybe think, oh well, I mean the photon counts per second, so this is in the range of a few thousand. per second. This is already taken at a relatively high excitation power. These counts are quite low, and this is indeed true. So the experiment is, or the photon counts we obtain in this approach is not very high, and the main reason is actually that now we have a diamond crystal. It has a thickness of about a micrometer. The color centers are located λ/2 from the mirror away, and the configuration here sort of gives rise to guided modes, which are guided here in the XY plane, and this is what we can see here on the right hand side. So this is a calculated spectrum of the calculated power density as a function of longitudinal wave vector. So so the modes for wave vector between 0 and 1, this corresponds to the radiation field. So this is all the modes we can collect with the microscope objective. While this zoo of modes we have for higher wave numbers here kind of corresponds to guided waveguide modes of that structure. So it is essentially that these modes, they take up a lot of energy or radiation from the emitter, and thereby limit the attainable photon counts we have here in the experiment. Now let's have a look at sampling the cavity. So in the next step, we approach the backside of the cavity, or of the diamond mirror structure with the optical fiber forming the cavity. We send white light in through the fiber and observe the spectrum of that system through the microscope objective. Now scanning the cavity length and then monitoring the spectrum, you sort of you typically monitor such a dispersion diagram as we see it here on the right hand side, and in contrast to a free space spectrum or a regular air cavity, you would explain simply parallel straight lines corresponding to the guided modes in that system. However, here we sort of see such a wavy type of structure, and the underlying reason for this is that because of the high refractive index between of diamond and the reflections at the diamond air interface, we essentially have a coupled two cavity system in here. So this is shown here on the in these two graphs at the bottom. So depending on the cavity length, I can have either a diamond-like mode. So the diamond-like mode is when the electric field is mostly contained in the diamond. So this is the preferred situation we have for coupling to the color centers. And we have here where the slope is a little bit is lower compared to the parts up here where the slope is steeper, which corresponds to an air-like mode. So in that case, the majority of the electric field inside the cavity is contained in the air part of the cavity. And this example, or these simulations, they also highlight the importance of a low surface roughness. So for a strong light matter interaction, I would like to have most of the electric field being contained in the diamond. Now the diamond-like mode, in contrast to the air-like modes, actually have a field antinode at the air diamond interface. So that means with a high electric field at this interface, I actually need to maintain a low surface roughness in order to avoid scattering and maintain a high cavity finesse. All right, so measuring the cavity finesse, so we have followed two different approaches. So the nice approach we could do at 637 nanometers. So at this wavelength, we had available an electro-optical modulator. We could modulate the probe light field with 4 gigahertz, test the cavity transmission, and we have measured the spectrum out of this. So using these 4 gigahertz as a calibration line, we could calibrate that the cavity finesse at this wavelength was about the cavity line width at this wavelength was about 2.5 gigahertz. Now the transmission coefficients actually quite strongly depend on the wavelength. So this is not necessarily a reliable measurement to obtain the cavity finesse. So instead, at a more interesting or more relevant wavelengths of 602, we had to rely on the standard measurement, so scanning the cavity length over one free spectral range, and then comparing to the line width of the transmitted peaks. We obtained a finesse which is about 11,000, so that is kind of in the range of what we expected. But the error bars are quite large, and this is the reason here is pretty much that a cavity with a finesse in this range, sort of the line width in length space is just about 100 picometers. So we're quite prone to fluctuations of the system in that case, and therefore these large error bars. All right. So now the next challenge one has to face is to locate emitters in that system with the cavity integrated. Now it's not just about to address the emitter, but it's about to actually tune the cavity resonance on the emitter, and at the same time, so fixing the cavity length. So what we have implemented is what we call a 3D cavity scan. So for each position in the transverse plane, we also scan the cavity length. We do record the maximum counts at the transition at the emission line, and plot this again in such a color plot here. And the result of this fiber scanning technique is shown here on the left-hand side, and compared to the confocal scan we have seen before, I think it is rather similar. And in fact, we could sort of locate at the same emitter which we analyzed before, which was isolated, is also visible now in this fiber spectrum. So we're quite confident that using this method we could locate and address a single GeV center here in the system. Now, so characterizing the system, so we see here on the top left-hand side, this is a spectra recorded from this color center. So these are spectra recorded from the color center as a function of relative fiber position, and there's a faint line in here. So this is essentially tuning the cavity resonance across the 5 terahertz the zero phono line of the emitter. So integrating this one sort of nicely resembles the spectrum measured of the emitter in free space. Now tuning the cavity on resonance and sweeping different longitudinal modes, we also see a nice longitudinal mode spectrum going from m equal 18 down to m equal 16. Further down we couldn't go because we at some point the fiber touched the substrate. But also recording the photon counts as a function of pump power, we see a nice saturation behavior, and as expected for the m equal 16 mode, the mode volume is quite a bit smaller than for the m equal 18, so the attainable count rate is also increased for this one. Now, sort of physically, the system right now, the system in that state is deeply inside the bad emitter regime. So the cavity resonance with a line width of about 1 gigahertz is much more narrow than the emitter transition with a terahertz line width. So there's no attainable or no measurable Purcell factor in that system. However, in order to quantify the coupling, what we have decided to do is to measure the free space count rate corrected for the detection efficiency and the measurement bandwidth. And in free space we have a count rate of which is in the range of 90 counts per photon per second per gigahertz. Now the same system inside the cavity, the number increases to about 2,800 photons per second per gigahertz, which is an enhancement of about a factor of 31. But again, there's no Purcell effect or no Purcell enhancement of the transition rates in the system whatsoever. Now the next part is that we're in the process of integrating that system into a cryogenic environment, and this is what I would like to address in the remaining time of this talk. So first of all, so we decided to implement our system in the BAF Bryostad system. So BAF Bryostad has no active cooling devices installed. So we hope that just a passive isolation with a passive isolation with a vibration isolation stage will serve to stabilize or to obtain a stable cavity resonance. And in fact, this is what we can see here on the right-hand side. So this is the displacement spectrum of a cavity resonance measured in vacuum, which is the gray trace and filled with air. So in vacuum, for a cavity finesse of the order of 10,000, as we had it in the experiment, we have a stability which is exceeding a second. So I hope that this is actually quite encouraging, that the system will also work when cooled down to 4 Kelvin temperature. Another aspect is, which is more on the technological side, that we're also in the process of making new fibers with a reduced mode volume. So previously, the mode volume, the cavity radius of curvature I've shown you was in the range of about 45. So now we made a new setup where we can more controllably focus down the infrared laser beam onto the tip of a fiber. So we have incorporated this with a nice positioning system, and we are now in the range, or we're now able to actually obtain radii of curvature which are about 20 micron or even a bit less, while maintaining the depth of the concave mirror in the range of 2 to 3 micron. So to have a shortest possible cavity. Now dealing with such an infrared laser setup is kind of not for an optics person like me, this is not the most straightforward way to work with. And the challenge is really that if you focus infrared light into an absorbing material, well, first of all, there's no way that you can observe where is the spot. So what we typically do is that we place the fibers in the focus of the CO2 laser where we think it is right, and then we perform a number of test shootings around the jacket of this fiber. And when we think that we have located the fiber in the focus, we aim at the center and then carry out the final shooting. And as I said before, so now we are sort of in the range of obtaining a radii of curvature which are 20 micron or eventually a little bit less. So we have also incorporated or investigated these diamond membranes with GV centers now in the cryogenic setup. Our cryostat can go down to 4 Kelvin at the moment. And if exciting it with 532 nanometer light, performing a scan of the sample in the laser focus, we again obtain these nice fluorescence scans, identifying single spots, then guiding those spots into a spectrometer. We sort of see now the spin orbit coupling appearing around the zerophonal line. And what we typically do then is to characterize, to identify these individual emitters, and by the frequency of the main transition, which I label the transition between states number 1 and 3 in here. So the spin orbit coupling with hundreds of gigahertz is not enough to fully ground state populate the emitters. So the states 2, 3, and 4, or state number 2, is firmly populated. So when off resonant exciting, I sort of see typically at 4 Kelvin, I see typically 4 transition lines, which I can associate with these 4 allowed transitions in the system. Now, so we use these spectra to now locate our a resonant laser onto the transition 1-3, which is the strongest one in this case, and then perform a resonant scan of this laser across this line. And if the emitter is behaving what we think is nicely, then a repeated scan across the emitter kind of yields a spectrum as we see here. So this is about 50 scans carried out over about 1 minute, and we see that this emitter at least behaved rather nicely. So it's a fairly stable transmission. Looking at the strength of this transition as a function of excitation power, we see a saturation behavior, and measuring the line width of these transitions as a function of base temperature of the cryostat, we see broadening due to the occupational scattering of phonons, and going down to 4 Kelvin sort of gets us in the range of the line width, about 100 megahertz, or sometimes even less. So kind of approaching the natural line width of the system, which is in the range of 30 megahertz for these defects. Now this is really I mean that it is not just one emitter which shows these properties, but it's actually many emitters. So this is a very nicely and reproducible kind of behavior we have. On the other side, I think we also have to be realistic and realize that, well, this is a solid state system. In the solid state, many things can go wrong and many things can happen. So we also see many emitters which actually do not show such a clean and nice spectrum. So here I'm showing 2 examples of, so on the left-hand side, this is an emitter which shows, we call it a spectral jumping between two resonance lines. The energy difference between those is about 800 megahertz. But we also see many emitters which have a more complex spectrum. So here there's about 5 transitions shown in that case. And if you now sort of take the cases with just 2 resonances, so two spectral lines, and we make a histogram. So this is shown here on the right-hand side. Well, we have that so some of the emitters, they scatter. They have jumps which go up to the gigahertz range, but most of them they actually contain down to they're contained down to frequencies up to gigahertz and kind of peaking up close to 0. Now again, so I mentioned this before. So for these central symmetric systems, there's no linear Stark shift. But what the calculations actually indicate is that we have that we're prone to charge noise here, which is occurring within a radius of about 5 nanometer from the emitters away. And what I think, or what we think, what is the origin of this is that here we're working with implanted germanium vacancy centers. So implantation means that the germanium is shoot into the diamond with an energy of about 300 kilo electron volts, and that leaves per implanted ion, it leaves about 100 vacancies deposited in the structure. And now these vacancies, they're not necessarily mobile, but they can actually cluster. They can cluster in the vicinity of the color center, and vacancies are kind of known to be charge, or to function as charge traps deep inside the diamond. And I think, we think that this is kind of the origin for these spectral jumps. So if we have a spectrum with only one, with 2 different lines, so this indicates that we have one charge scatterer. If we see, like in this case, 5 different lines, so this indicates that we have 2 or more charge scatterers, which are kind of causing these spectral jumps. Then I hope you're still with me. So in the last, this is my last slide. So even for the nice spectra, so if one carefully looks at these resonance scans, one can actually see that while scanning through the resonance, so sometimes the emitter actually goes into something like which looks like a dark state. So indeed now the image here, or the graph here in the center. So we put the laser on resonance. We record the counts as a function of time, and we indeed see that the emitter actually starts to blink. So there's for certain periods the emitter is bright, and then it goes into a dark state, but it recovers actually naturally again. So now what you can do is to bin the duration of these bright states into a histogram. This is what is shown here on the bottom plot. Characterize the time constant, and then plot this time constant as a function of excitation power. Now what we see here is that it's actually what we see is, and we're quite sure about this, is a quadratic scaling with the excitation power, and this strongly indicates that it's actually a 2-photon process which is happening here. So what we believe it is that when resonantly driving the transition between 1 and 3, we occasionally ionize the emitter from the ground state into the conduction band by the absorption of 2 photons, which leaves the system in a dark state, which then eventually recovers spontaneously and then activates the emitter again. All right. So this is an experiment which has been, I think, going on for quite some time. So I would like to highlight the contribution of Rasmus and Olivier and Erica in collaboration with the group of Lilian Childress from McGill University. So these 3 have thoroughly driven the room temperature experiment, and this was taken over recently by Maxime, Daniel, and Nelia, who are now working with the cryogenic integration. And with this, I would like to finish and thank you for your attention.
Thank you very much, Alex. And the talk is open for discussion. I don't see questions on Slido, but maybe someone in the audience has questions.
Yeah,
okay. Radim, please.
Alex, hi. Nice talk, really. As you can imagine, I was quite attracted by this Hangul mandala effect, which you maybe could possibly see from 2 different centers.
Yeah.
Is that your result, or because I wasn't sure if I saw directly the reference?
Pardon, these results actually they're fairly old. This is a physical review letters from 2014, I think.
Okay, and this is doable in your lab?
What? It was not done in our lab. So this is
Is it now possible in your lab with any kind of centers you have?
I mean, no, I would not say we I think in general it would be possible to carry this out, but I don't think we have the setup for this right now. But I think this is merely, I mean there's 2 aspects to this. So the first aspect is that means, of course, to set up the experiment, because you need a 2-channel microscope for this.
Mm-hmm.
The second aspect is that it was kind of a magic sample. So growing a diamond with native color centers kind of means that you need to put a dopant into your very clean and highly treated, or like very well treated growth chamber. And I'm not sure that many people would like to do this. So usually you try to sort of maintain a high purity. Now you put a dirty material inside. So, but what is actually necessary is to incorporate these color centers during growth, which basically means that you avoid the formation of many vacancies during implantation, which is the other approach for color center creation. And it's basically those vacancies which cause some of the trouble we sort of observe in the optical experiments.
Mm-hmm. Mm-hmm. It means it's not really like the standard way how you grow the samples and how you basically prepare them, if I understand it correctly.
I think this is yeah, this is correct. Yes. So I think these samples, they were actually created, I think not on demand. So this was kind of, I think the story behind was that while optimizing a CVD process, so they actually etched the windows of this chamber, which contain silicon, of course, and this incorporated some of the silicon into the diamond.
Okay. Was there any progress after this paper from 2014? I think so. I think the reproducibility or
pardon?
To increase reproducibility of the sample preparation or anything.
I don't not that I know. Okay. I think so I mean there's many investigations, I think, now going in the direction of nanophotonic integration, but I mean processing diamond is very challenging. The other approach is actually tin vacancy centers. So they also seem extremely promising. But tin vacancy center. So if you go one row further down in the periodic table, the challenge there, however, is that tin vacancy centers they have a very high or a relatively high thermal activation temperature. So you need to anneal the diamond at temperatures above 1600 degrees Celsius. Yeah. This requires annealing in high pressure environments, and this is not easy to do. Yeah. But otherwise, I think the prospects are quite promising.
Okay, thanks a lot. Thanks a lot, Alex.
Thank you. Are there any questions? Okay, seems to be not the case. So thank you very much again for the talk.
Yep.
And the next speaker. So the next speaker is Samuel Delguise, if I pronounce it right.
Yes, Delguise.
Thank you, Delguise.
Hi.
Hello, Samuel.
So you can hear me, right?
Yes, yes, we do.
Great.
So Samuel will talk about electromechanics towards heralded non-classical motional states. We hear you, but we don't see the slides yet. So
yes, now I should be able. Yeah. Yep. That's fine. Do you see it?
Not yet.
Oh yeah. Here you go.
Yes, here they are.
Okay, perfect.
The floor is yours. Thank you.
Okay. Yeah. So first of all, thank you. Thanks a lot to the organizer of this workshop. Thanks a lot for giving me the opportunity to present these results. So I'm a researcher at LKB in the optomechanics and quantum measurements group. And I'm going to tell you about experiments where we are trying to demonstrate the non-classical behavior of a macroscopic mechanical resonator. So what you see here on this slide is actually a silicon nitride membrane. So this is this very thin blue object that can vibrate out of plane like a drum. And what we are trying to achieve is to control the quantum states of such a system to the point where it cannot be described by a positive Wigner function. And so to achieve this goal, the approach that I'm going to present here relies, at least in part, on the tools of optomechanics. So, so in the simplest form, you can think of the canonical optomechanical system as depicted on this cartoon. The mechanical resonator here is used as the end mirror of an optical cavity, and so the mechanical motion will modulate the length of this cavity. So there is rich dynamics in these systems because on the one hand, the mirror will experience a force that is proportional to the intensity inside the cavity. So this is radiation pressure. And on the other hand, by moving, the motion will modulate the frequency of the cavity. So historically, this kind of optomechanical coupling was studied in the context of interferometric measurements, because combined with the quantum noises of light, this radiation pressure interaction gives rise to fundamental limits in the precision of the interferometer. So in this case, the optomechanical coupling is rather a disturbance to the measurement sensitivity. And one of the big activity of our group is to develop a squeezed light source that is compatible with gravitational wave interferometers to enhance the sensitivity of advanced Virgo. On the other hand, a big experimental effort is going on to use radiation pressure as a resource to control the quantum states of a micromechanical system. So you can see here several examples of a micromechanical oscillator that have been cooled using radiation pressure close to their quantum ground state. So this whispering gallery mode resonator, where the optomechanical coupling occurs between the light circulating in the cavity here and internal vibrational mode of the structure. Here, this is a photonic crystal cavity where the photonic crystal is used to confine at the same time phonons and photons in the same very small mode volume. And here, the third system that you see is of the electromechanical, microwave electromechanical category. Essentially, the vibrating element is this aluminum plate that is sitting on a vacuum gap, and that will essentially modulate the value of a capacitor, and hence the frequency of a microwave resonator. So the inductor here is this these lines that form actually a spiral. So the experiments I'm going to describe belong to this last category. So experiments where mechanical motion actually modulates the frequency of a microwave degree of freedom. And in spite of the the apparent diversity of these systems, like in geometry, and also the mass here spans more than 10 orders of magnitude, they are essentially all described by the same Hamiltonian, which is depicted here. So here A is the annihilation of photons inside the electromagnetic cavity, and B is the operator for phonons inside the mechanical resonator. Here, G naught is a parameter that describes the strength of this interaction at the Hamiltonian level. It's called the vacuum optomechanical coupling rate, and essentially what this describes is how much the frequency of the optical cavity fluctuates due to the 0-point fluctuation of the mechanical system. And so the first remark that we should make is that the frequency of the two harmonic oscillators that are coupled by this Hamiltonian are very different. For instance, in the experiment I'm going to present, the mechanical system is vibrating around a megahertz, while the microwave cavity is typically in the 10 to the 10 hertz. And the first consequence of this is a thermodynamical one. Because of this very small mechanical frequency, the mechanical resonator is coupled to a thermal bath with a very large thermal occupation, while the microwave field, if we are able to thermalize the system in a dilution-free environment, is coupled, essentially sees a bath with zero occupation. The other thing is that usually this G naught, this coupling, is too small. It's much smaller than the frequency of the mechanical resonator and the damping of the optical cavity. So it's too small to observe the effect of single photons in the system. So the approach that people are usually following is the linear regime of optomechanics. So the idea is to pump the optical cavity with a strong classical field of coherent amplitude alpha, and then look for the linearized dynamics around the steady state. So essentially what we do is we replace operator A by the displaced operator A plus alpha. And if we do that, we end up with this linearized Hamiltonian, where essentially the coupling has been enhanced by a factor that is proportional to alpha. But on the other hand, now the coupling becomes linear between the two systems. So another interesting consequence of the fact that we have so different frequencies is that it's going to be very easy to choose which terms are going to be resonant in this Hamiltonian by simply tuning the frequency of this classical drive. So for instance, if we set the drive frequency exactly one mechanical frequency below the microwave resonance, we end up with this exchange Hamiltonian, where essentially we can swap phonons and photons. And essentially the dynamics of the system described by this beam splitter Hamiltonian is exactly the same as the fields at the input of a beam splitter. On the other hand, if we set the pump one mechanical frequency above, the energy of the pump photons exactly coincides with the sum of a resonant photon, the energy of a resonant photon and the phonon. So you can generate pairs of photons and phonons. And so the dynamics this time is really equivalent to that of the field inside a non-degenerate OPO. And So this essentially, this gives us a comprehensive set of tools to manipulate the quantum state of the mechanical system. For instance, we can use this interaction to cool the mechanical system by essentially swapping the hot mechanical thermal state with the cold electromagnetic state, or we can entangle photons and phonons using this beam splitter, this parametric down conversion interaction. However, because these Hamiltonians are linear, they only couple one operator of each system together, and because we are dealing with fully harmonic oscillators, there is no way to create a non-Gaussian state starting from merely Gaussian states such as thermal states or vacuum. And for this, we need an extra nonlinear element. And as I guess people in the audience know very well, a very good example is a photon resolving detector. So for instance, with propagating laser beam, what you would do is to generate entangled twin beams like that, where there's a small probability to emit a pair of photons in the two beams. And then if you detect a click on the detector here, you know that you've immediately projected the other beam on a single photon Fock state. So this is, of course, a probabilistic preparation method because you only get a probability epsilon square to count a click in this experiment. However, as soon as you count the click, you know that you've projected your system in the desired quantum state. So the optomechanical version of this experiment basically, as demonstrated recently in the optical domain by the group of Simon Groblacher, in this version, you replace the propagation along the path of the beam by a sequence of steps. So the preparation, essentially, you would first cool the mechanical resonator by using this red sideband pulse that essentially cools the mechanical system in its ground state. Then the entanglement, you switch on a pump on the blue sideband, which generates this entangled state between the propagating microwave field and the mechanical system. And at the same time, you just detect the field at the output field of the system. And if you count the click, then you can make later on the tomography of the mechanical state. So of course, a key ingredient for this experiment is a photon resolving detector. So you need a detector that's sensitive to this quadratic quantity in the field of the operators, and in the optical domain, where the energy of the photons is essentially sufficient to trigger like irreversible phenomena like photoionization. These are commercially available. However, in the microwave domain, essentially there are only a few proof of principle which all relies on various schemes that will convert the incoming photons into an excitation of a superconducting qubit. So very important figures of merits for the detector are the dark count probability, that is the probability to count a click even though there was just the vacuum at the input of the detector, and the inefficiency, the probability to not count a click even though there was a photon at the input. And there is the common conception that what is most important is the efficiency of the detector. However, for this heralded scheme preparation, the dark count is probably a very important parameter, as dark count essentially will end up in mixing the interesting state with the Gaussian state that you started with. So this will directly affect the fidelity of the prepared state, whereas the inefficiency will simply lower the success rate of your experiment. So in this talk, I will describe first the optomechanical, the electromechanical system that we are developing at LKB. And then in the second part, I will describe work that have been carried out in collaboration with the group of Zaki Lectas and Emmanuel Fleurin at LPENS, where we came up with an original scheme to realize single microwave photon detector with very low dark count rate in the microwave domain. Okay, so first of all, I'd like to motivate why we are using this silicon nitride membrane. And so in this graph, you can see here on the vertical axis, the quality factor. So this tells you how much the mode is decoupled basically from its noisy thermal environment. And on the horizontal axis, this is a 0-point fluctuation. So that's a quantity that scales as 1/square root of the mass times the frequency of the system. And so that tells you how easy it is to couple your mechanical resonator to other systems, and in particular to electromagnetic field in the context of optomechanics. And what you see in this graph is that you have this kind of depressing trend where essentially as you go towards nanoscopic systems, so this is here nanowire, here on the left, you have these Weber bars and bulk acoustic wave quartz resonator. And so as you decrease the dimension of the system, so to basically enhance the 0-point fluctuation, you at the same time reduce the quality factor. And this is a sign that most of these systems are dominated by surface losses. So actually, if we look closer, since a few years, there are a certain class of resonators that seems to miraculously evade this trend. So these resonators that have been pioneered by the group of Jack Harris are silicon nitride membranes and string. And the physical phenomenon really that's behind this new trend is called dissipation dilution. And it is directly traceable to the fact that you can deposit silicon nitride with a very large tensile stress. So to understand this phenomenon, let's consider a square membrane of side L and thickness H that would be clamped. So here, for instance, on the silicon frame at the 4 edges. And by definition, so the quality factor is the ratio between the elastic energy that is stored in the deformation of the material divided by the energy that it's lost at each oscillation cycle. So if we interest ourselves first to this stored energy, so let's take an elementary element of volume in a material, and this volume element is going to be deformed when the membrane vibrates. And so in the absence of pre-stress, essentially, there is basically no deformation when the membrane is at rest, such that the element of volume sits at the origin of this stress-strain diagram. And now, when the membrane starts to oscillate, essentially, the element will start to be stretched in this case, and then half a period of oscillation later, you will have the opposite constraint. It will be strain, and essentially, as the membrane oscillates, this point will follow this segment in the stress-strain diagram. And so the length of this segment essentially depends on two things. First of all, the distance from the middle, so which is highlighted here by this blue line, the distance of your volume element from this middle line, and the mode curvature at the point of your volume element. And so now we can calculate the bending energy stored in this volume element at the maximum displacement of the membrane. And this is given by the integral of the stress times strain over a quarter of a period. So essentially, this is given by the area of this blue triangle. And now if we want to evaluate the energy that are lost over a period, we need to come up with a phenomenological model for the losses. And so a good model here, when the system is dominated by internal loss, is this Zener model, where essentially the Young's modulus acquires an imaginary part which describes the fact that the stress is slightly delayed compared to the strain in the material. So in this case, the point in the stress strain diagram is going to follow an ellipse like that, and the work that is lost at every oscillation period is then given by the area of this ellipse here. So the quality factor is just simply given in the absence of pre-stress by the ratio between this blue triangle and this ellipse. And this quantity actually only depends in this case on the real and imaginary part of Young's modulus. And this is by definition called the intrinsic quality factor of the material, which is on the order of 6,000 only for silicon nitride. However, this equality between the intrinsic quality factor of the material and the mode's quality factor only holds in the absence of pre-stress. If you start now to apply pre-stress to the membrane, as you would do, for instance, with a drum skin or a guitar string, you end up displacing the point in the stress strain diagram. And now, if the membrane moves exactly with the same amplitude, the energy lost at each cycle has exactly the same dependence. It's related actually to the bending energy as before. However, there is this extra contribution to the stored energy, which is essentially stored in the elongation of the material. And so this is essentially energy that is essentially lossless, that we get for free, and which is going to allow us to dilute the internal losses of the material. So essentially, the quality factor in the presence of pre-stress is going to be diluted by this factor. And so this dilution factor is the product of two terms. One term which corresponds, which is proportional to the stress of the membrane. So in our membrane system, the stress is close to 1 gigapascal. So this is very close to the yield stress of the material. For instance, this would correspond to suspending a 100 kilogram mass to a guitar string. And then this other term here is the aspect ratio. We can really understand pretty well why the aspect ratio plays a role here, because essentially bending energy is dominant for volume elements that are far away from the center of the membrane. So if the membrane is thinner, you have less of these elements inside it. And so here again, we have very, very large aspect ratio resonator, because the membrane is typically 100 nanometer thick and like 3 millimeter in length. So as a comparison, if the Golden Gate Bridge would have the same aspect ratio, it would basically have a thickness of only 10 centimeters. So essentially, in theory, the dilution factors here, square root lambda, that we should get in this system should be close to 600. So you have a 600 increase compared to the intrinsic quality factor of silicon nitride. So we've learned how to fabricate this silicon nitride membrane in the lab. We start from silicon wafer coated with silicon nitride on both sides. And then we etch selectively silicon nitride by the silicone, sorry, by dipping the sample in hot potassium hydroxide for 18 hours. So we do this in these custom-made holders. And basically, we fabricate these batches of 9 membranes at a time. So then we characterize first at room temperature this mechanical resonator in a shot noise limited interferometer, thanks to a balanced homodyne detection. And so in reality, the interferometer looks like that. You see it's a fully monolithic design built in a cage system. And basically the whole interferometer is mounted on a translation stage that allows to essentially scan the interferometer with respect to the sample and to measure all 9 samples at once without the need to open the vacuum tank. Moreover, by scanning the position of the interferometer, we can essentially raster scan the position of the laser on the resonator and perform a tomography like that of the vibration profiles the membrane. So the resolution of the interferometer is sufficient to see actually the Brownian motion of the various membrane modes at room temperature. So these are these various peaks that you see here in the noise spectrum. And so these are the experimentally reconstructed vibration profile that match pretty well with the simulations. We then can measure the quality factors of the membrane in by performing ring down measurements. So what we do is we modulate first the intensity of the laser beam with an AOM. So this we modulate it resonantly with a vibrational mode. So this is this first part. And then we stop the modulation and just look at how the vibration decays down in the system. So the quality factor here corresponding to this measurement is a bit more than 1 million. And so this is within a factor 2 from the values that is predicted by this dissipation dilution theory that I presented below. So actually what we will see is that this value increase also dramatically at cryogenic temperatures. So for this, we place the membranes in an electromechanical setup. So essentially, the microwave part of the circuit is located on this separate chip. Essentially, the membrane will be brought in close vicinity of this microwave circuit thanks to these aluminum spacers that are typically less than a micron thick. And so the interesting part is this resonator that we see here. If we zoom in, we see that we have two parts. We have this capacitive part, these two niobium capacitive pads, and here this meander, which actually is an inductor, and this forms an LC, a lumped LC resonator. We have also this transmission line that allows to send microwave signal in and out of the resonator. Then we essentially coat, so you see here the mechanical sample, the membrane, with a niobium pad that is deposited here. And once we bring the two chips together in a flip chip geometry, essentially this superconducting pad is going to come in front of this capacitor, and you realize this this moving gap capacitor, where essentially the value of this capacitance depends on the position of the membrane. If we make a cut through this, essentially the flip chip assembly looks like that. We are able to make gaps between the two chips on the order of less than a micron, actually. And actually an important technological aspect is that we need to essentially etch all the surfaces that are not useful, and this is essentially to reduce the probability that the dust becomes squeezed between the two chips. So we then place the sample inside the sample holder and then measure it inside a dilution fridge. So the data that I'm going to show in this presentation have been measured in a fridge that was gratefully landed by this group of Zaki Lektas at INS, because at the time we didn't have yet dilution fridge in our lab. So essentially what we are going to do is that we are going to drive the system. So we thermalize the microwave drive to reduce the thermal noise here with various attenuators at the different stage of the fridge, and we amplify the signal. So the first thing we do is we reproduce the ring down measurements at low temperature. So for this, we send essentially two microwave tones that are separated by the mechanical frequency. So the bit node between these two tones will create intensity modulation that will drive the mechanical resonator into motion. And then, as before, we switch off the modulation and simply read the mechanical motion with a red sideband that essentially converts the mechanical phonons into microwave photons. And so what you see here is the decay of this mechanical amplitude. And the important thing to notice is the x-axis here, which is in seconds. So actually, you can have coherent oscillation for even minutes in this system. And so the quality factor here at low temperature is around 300 millions. And so this huge boost of the quality factor at cryogenic temperature, which has also been observed in the group of Gary Steele, corresponds to the fact that the intrinsic properties, the intrinsic quality factor actually of the silicon nitride likely gets much better at cryogenic temperatures. So in fact, even if you consider the fact that this system is coupled to an environment with a non-zero occupation, you can see that the coherence time of the system exceeds actually the best microwave resonator. And actually, the interesting thing is that it's a very compact chip scale system in this case. So this is very interesting system also in the context of quantum engineering, for instance, to be used as a quantum memory. And so now what happens if we increase this readout pulse, we start to see that essentially the effective lifetime of the mechanical resonator decreases. And this is actually the effect of electromechanical damping, the fact that you are converting mechanical phonons into photons. And so you are adding a microwave damping to your mechanical resonator. And so now we can study this effect in the frequency domain. So we wait for the mechanics to reach the steady state. And then we just send the output microwave field into a spectrum analyzer. And we see this spectrum, this very narrow peak that you see here is actually the thermal noise of the membrane. And as you increase the pump power, you see two effects. So first of all, you see that the peaks becomes wider. So this is essentially the frequency domain counterpart of the effect we just saw before. The damping, the effective damping increases, and at the same time, the area below the peak decreases. Essentially, this is a log scale, and so this is a sign that we are cooling effectively the mechanical. So if we plot here as a function of the pump power, the effective temperature as inferred from the area below these curves, we see, so we have actually a good news and a not so good news. The good news is that we are able to achieve cooling factor by 3 orders of, cool this membrane by 3 orders of magnitude. So in principle, this should be enough to be deep inside the ground state, starting from the thermal population at 10 millikelvin. However, the bad news is that the initial temperature we start with is not 10 millikelvin, but it's rather above a Kelvin. And this is attributed to the fact that we are essentially seeing vibrations caused by the pulse tube of the dilution fridge. So to solve this problem, there are several approaches. There is this passive damping of the whole cryostat stage, as we saw before. Another very interesting strategy that we are exploring right now is to apply phononic engineering strategies. So the idea is to decouple the vibrating system from the noisy environment by using phononic crystal decoupling. So by the way, there is a poster by Eduard Ivanov that I encourage you to see for more details on this. But so essentially, these phononic crystal membranes that we fabricate in the lab looks like that. So we essentially took inspiration from this work by Albert Schlisser in Copenhagen. So here, the phononic crystal is directly etched inside the silicon nitride membrane. And if we look at this purely periodic region, so this represents a phononic crystal with a well-defined band gap for out-of-plane modes of vibration. So essentially, vibrations in this frequency range cannot propagate or will be exponentially damped in this phononic crystal. And if we engineer a defect in the center with the proper engineering, well, we can manage to have localized defect modes that are sitting exactly within this band gap. And we can clearly see the localized defect modes as a series of discrete peaks sitting on a very quiet background. So this is what happens when we measure the displacement spectrum at room temperature in the optical interferometer close to the center of the membrane. So actually, we can once again perform a raster scan, the mode tomography of these defect modes. So this is what we measure by scanning the laser in this region. And these are the simulated mode profiles. So we have a very good understanding of what those modes are. And note that in our experiments, we will be mostly interested by this D1 mode, which has the maximum displacement at the center of the membrane. So an extra benefit of this phononic crystal membrane is the fact that not only we hope it's going to decouple the mode of interest from acoustic vibrations, but also it should lead to an enhanced dissipation dilution. So the reason for that, I want to come back a little bit to the comparison between a square membrane and this phononic crystal membrane. So if we look at the displacement profile for square membranes, so we see that essentially this displacement membrane at first sight doesn't depend on the stress, essentially on the dilution factor. It looks pretty much the same. However, if we zoom in a very small region close to the clamping point of the membrane, due to the boundary condition, we have this very sharp kink here that essentially becomes sharper and sharper as you increase the dilution factor, the stress. And this is actually very bad because here now I'm plotting the curvature of the mode profile, so second derivative of the profile as a function of x. And you see that this kink becomes higher and higher as you increase the stress. And so the reasoning that we made earlier, that essentially the energy that is stored in elongation grows as lambda, whereas the energy stored in bending remains the same, is not totally correct for this kind of system, because the energy stored in bending actually depends also on the stress. And actually, if you do the math correctly, you see that the energy stored in bending scales as the square root of this parameter lambda. And that's why at the end of the day, the Q factor scales also as the square root of this dilution factor lambda. On the other hand, in this soft clamping resonator, what you have is that the vibrations are exponentially damped away from the defect, such that essentially the defect mode doesn't see the clamping condition, and essentially the bending energy of the membrane is independent of stress, such that you get in the end the full dilution factor lambda instead of square root lambda. So you can actually calculate what the bending loss should be in your system by simply integrating the curvature over the mode profile. So this is done numerically, and we expect for our membrane parameter at room temperature a quality factor of 15,000. And so what we get is so you have several membranes that have been measured. So the different colors of the point correspond to the different vibration modes of the defect. And so what you see is that for mode D2 and D3 we are actually quite close from the value expected from this dissipation dilution. But for the mode D1, we scratched our head for some time because we saw a lot of dispersion in the quality factor of this membrane. And actually, we understood what was going on when we started to look at the vibration profile close to the edge of the membrane. So we displaced again our interferometer in this region. And we saw that in addition to the defect mode, we have here like a forest of modes. And these modes corresponds to edge modes of the structure. Close to the edge, you don't have anymore a perfectly periodic pattern. The symmetry is broken, and you can have edge modes that are simulated here. And these edge modes essentially are going to hybridize with your defect mode. And essentially at the end of the day, when this happens, you get a quality factor which is the average between the two kind of modes. So this is confirmed by doing the tomography of the different mode. Essentially, the D1 mode we see, especially for the samples where we have this strong reduction of the quality factor, is actually strongly hybridized with vibrational mode located on the edge. So how can we manage to avoid this problem? So well, we came up with this solution of adding several arrays of holes here. So essentially what this is doing is pushing up the frequency of these edge modes such that they don't coincide anymore with the interesting mode for us, the D1 mode. All these edge modes are now higher in frequency. And so you see that we get now much more reproducible result for the D1 mode. Of course, this comes at the price that the D2 and D3 modes have a tendency to hybridize, because now the frequency of these edge modes coincide with that of the higher excited mode of the defect. So now this is actually very good news. We see that the average quality factor of the mode of interest is within a factor of 2 of the optimal mode predicted by dissipation dilution. And essentially more than 50% of the samples are what we call good samples that have at least within 50% of this optimal quality factor. So of course, so what we are working at right now is to integrate this phononic, this softly clamped membrane in our electromechanical experiments, and keep in mind that we expect a similar boost of the quality factor at cryogenic temperatures. So that's more or less what I wanted to present on these electromechanical experiments. And now I would like to use the few time that is left in this presentation to talk about this work that we did in collaboration with LPENS to realize very low dark count single microwave photon detectors. So here we are going to now use really the tools of superconducting circuits with Josephson junctions to essentially count microwave photons with very high efficiency and low dark count. So our goal is to make a photon detector that is able to catch photons irrespective of the temporal waveform of the photons. And for that, we came up with a scheme, an original scheme exploiting reservoir engineering to efficiently convert the incoming photon here into a qubit excitation. So the schematic of the detector is depicted here. And it is composed of a transmont qubit that is sandwiched in between two linear resonator, a buffer resonator B and a waste resonator frequency omega W. And essentially the two resonators here are very strongly overcoupled to this transmission line, such that they have very low quality factor, and we are, in particular, we are going to use the waste as our cold reservoir for this reservoir engineering. So what we do is that now we pump the system at a well-chosen frequency here. So omega W is the frequency of the waste, omega sigma the frequency of the qubit, and omega B the buffer frequency. And in a way that is pretty similar to what we are used to in optomechanics, we end up amplifying essentially these two energy conserving terms in the Hamiltonian of the Josephson junction. So what these terms tell us, essentially, if we focus on this one, essentially you have annihilation operator of one photon here, creation of an excitation in the qubit, and creation of a photon in the waste. So what this process is, when a photon arrives on the buffer cavity, it can jump to the waste cavity and at the same time excite the qubit. And so this is essentially how we are going to detect this photon. At the end of the experimental sequence, we can simply read out the state of the qubit. And if we find the qubit in the excited state, it means that a photon has entered the system in the process. So the very important thing about this process is that the reciprocal process here, the Hermitian conjugate, essentially you see that this is the process that would require an excitation in the qubit and an excitation in this waste cavity to be allowed. And because this waste cavity is very strongly coupled to this measurement line, essentially, as soon as an excitation is created in here, it escapes such that the reciprocal process is totally forbidden. So actually, we can make this argument a bit more formal. We start for this from this parametrically activated Hamiltonian. We add up the loss operator for the waste cavity. And now if we perform the adiabatic elimination of the waste mode, we end up with this non-local loss operator. It is non-local in the sense that you have essentially two operators for this buffer cavity and the qubit. So what this loss operator describes is the fact that if you have a photon inside this cavity, it is going to decay down, and at the same time, the qubit is going to decay exponentially towards its excited state. So essentially what's going on is that the qubit population PE integrates the buffer occupation. So here is how the device actually looks like. It's made actually of standard microwave circuit elements. The buffer and the waste are made from a λ/4 resonator. And you have here in the center the transmont qubit that can be pumped via this external line. So to operate the detector, what we basically do is we switch on this parametric interaction by switching on the pump. And essentially this time is the time, the detection window, the time over which you are going to be able to detect incoming photons. Eventually, we send a very weak pulse at the input of the buffer cavity. And finally, at the end of the sequence, we read out the state of the qubit to know whether we have detected a photon or not. So we didn't have a single photon source, but instead we have calibrated precisely the flux of photons arriving on the buffer cavity, and we've sent very weak coherent pulses. And you see here, as a function of the number of photons in the coherent state, the probability to find the qubit in the excited states. We can now plot exactly the same data, but this time as a function 1 minus P0, so the probability to have to not have the vacuum state inside this coherence state. And essentially, the efficiency of the detector corresponds to the slope of this at the beginning of the curve. And here, I think for this 2 microsecond detection window, we get an efficiency of 58%. Actually, by repeating this experiment for various duration of the pulse, we see that we have a pretty good efficiency over very different pulse shape. And actually, we have a very good understanding of the noises and the limitations of the system. So here you can see the effect of the qubit lifetime. Simply, this is the fact that if your qubit gets excited at the beginning of the pulse, of course, after some time, if this pulse is comparable to the qubit lifetime, it's going to decay away and you lose efficiency. The red curve, the green curve, sorry, corresponds to the fact that the buffer cavity has a finite bandwidth, and if the pulse here is too short, essentially, it will have Fourier components that are rejected by the input cavity. And finally, this red lines corresponds to the fact that there is a mode matching condition inside the buffer cavity. Essentially, this parametric process corresponds to a loss process for the cavity, and you need the input mirror of the cavity to match exactly this nonlinear loss process. And this happens when these two effective damping are exactly the same. And this was not the case in our experiment. And essentially, this factor would have limited us to 0.8. So however, the message here is that we have a pretty good quantum efficiency in this experiment, and that we have a detector that is waveform insensitive. So now let's look at the real advantage of these schemes, which appears when we look at the dark count rate. So essentially, the advantage is that we expect that there is not really, except for environmental heating of the qubit, there is not an obvious process that triggers dark count in this scheme. And so you see here that the dark count rate stays at a very low level, even for very long detection windows. So this is in stark contrast with, for instance, experiments with Ramsey interferometry, where essentially after a dephasing time of the qubit, you end up at 50% chance to find the qubit in the excited state. So actually these numbers are typically, essentially the short time dark count rate is typically an order of magnitude below the state of the art. Okay, so this is my essentially my last slide. So an interesting aspect of this detector is that the photon that is detected here in the detector is not destroyed in the process. As we said, the photon escape through this waste cavity. And so instead of discarding this information, we can actually amplify and monitor this propagating photon. And so this is what we have done. We have used this actually nice technique from Laura's group to find the waveform, the temporal waveform of the photon rejected by the system. And then we perform the tomography of this photon. So we sort the data, of course, in two categories, whether we've detected the qubits in the ground state. So there we should recover essentially the ground state in this channel. And if we counted a click in the detector, here we obtain a very nice single photon Fock state. So I should mention here that we've calibrated the measurement, the losses of the measurement chain, and this is the state inferred directly at the output of the waste cavity. So the fidelity of this state is close to 81%. So in fact, what I'm showing here is the simplest heralding experiment that we can perform with such a detector. Okay, so yes, in summary, I've shown our progress towards the development of an electromechanical system with an ultra-coherent silicon nitride membrane. I've shown experiments at room temperature with a QF product of 10 to the 12, 10 to the 12 at 20 milli-K, cooling factor of 1,000. I've found a progress towards edge-guarded photonic crystal membrane, and here the QF product already is larger than 10 to the 13 at room temperature, and we're still needing to characterize these membranes at low temperature. A single microwave photon detector with very low dark count rate, efficient, and that is also waveform independent. So the next step are to test the acoustic isolation of phononic shielded membrane in an electromechanical cavity, and hopefully the preparation of non-Gaussian states with this system. Okay, so with this, I'd like to thank you for your attention. I hope we still have some time for questions.
Thank you, Samuel. Thank you for the interesting talk and for keeping to the time schedule. Are there any questions in the audience? Radim, please.
Yeah, nice and well, very good. Yeah, it's a really interesting detector. I was maybe not very sure at the end when you mentioned that sort of like Wigner tomography of your detection.
Yes.
Is that one with some correction for loss or noise?
Yes, exactly. We have to correct.
Yeah.
Yeah, we have to correct for losses. Essentially, what we do here is that we measure the Q function, because we essentially this amplifier is not quantum limited. It's a a low noise cryogenic amplifier that adds typically 10 photons of noise. However, if you average enough, basically, you can reconstruct the Q function of a strongly attenuated fog state. And by averaging that enough, you can deconvolute the effect of the noise and come back to the state that you would have here. So of course, you need a very good characterization of the losses of your system to do that. Yes.
It means when we use this for some like event-ready state preparation, the actual single phonon state which we will basically prepare will be heavily attenuated, or not? Like, will that?
No. This is different. This is different. This is essentially what I'm showing on this slide is a heralding experiment where you're using the detector, the photon detector, to herald the preparation of a single photon in this microwave line.
Okay. And then.
But this is different because in the real detection experiment, what counts is the detection efficiency of the qubit at the end of the experimental sequence, and this is very good. This is like 60%.
This was just to basically verify the performance of your detection. It will not be.
And also the performance is actually the number that I've quoted, the efficiency of something like 60% and very low dark count rate.
Very low dark count rate. Okay, perfect. Very good. And yeah, like maybe I have another question if I could, or
yeah.
No other.
Oh, I don't know.
Sure.
Yeah. I thought like in optics we typically multiplex the single photon detectors when we would like to count more photons that potentially prepare higher fog states. Did you think about any way how to do that? Whether that is possible to? Because like I will naively say, okay, you will put there more transmons and just split the input signal to the transmons, and then you will basically have the multiplex detector for such a type of the preparations. But
no, we
simple, or is that any?
I think actually that would be even. That would be actually even simpler than that, because if you look at this Hamilton, essentially what we are using here is a parametric pumping scheme where we start from the highly nonlinear Hamiltonian of the Josephson junction. There's a cosine term basically, and by pumping this system at the right frequency, we can select the process that we are interested in. So you could think of a process where you have B squared here, by simply pumping at a different frequency the system. So for instance, 2 omega B here. So this would be actually probably an even simpler way of doing this. On the other hand, I'm not very sure. We've been thinking a lot about that. What does it mean for, if your detector is not, is waveform insensitive, essentially, what does it mean to have a multi-photon state? Because it becomes a multi-mode at the input, basically.
Like in optics, like in Julian's or Nicola's experiment, we basically split our input signal to the more modes. It means you kind of like divide the energy, and then you plug it to the single photon detectors, right?
Yeah.
It means here, basically your input your input waveguide, which basically brings the signal, right?
Yeah.
We now through possibly the buffer with omega B split it to more transmons, which will kind of simultaneously count the microwave photons.
No, but what I'm saying here is that in principle you can do something even simpler. If instead of pumping at this frequency, you pump at a frequency where the resonant process becomes B squared sigma W. Okay, so essentially you would have a counter that only clicks when you have 2 photons at the input.
Okay, but then if you want to go up for 3 photons,
then you choose an even more nonlinear process where you have a BQ.
Okay. Okay, yeah, that's maybe elegant solution. It means it's kind of like that you go to the higher sidebands of that interaction, and then you can count more photons. And this is basically, these sidebands are so nice, so well sideband resolved and with low noise that you can do that.
Yes. Okay. So in principle, I guess the difficulty here is that what is hidden in the sky is essentially a pump. You have the pump photon that is so the usual thing of parametric pumping, basically, and the more nonlinear the process you want to amplify, the more you have to pump, and it's not very clear whether you can reach sufficient.
When we thought, for example, about the same approach with reptilians, there are always like higher sidebands, but to access them and to force them to work well, this is more complicated than maybe use sequence of the detection events. But yeah, maybe this we can talk later about that. Yeah, that's quite interesting. Very good.
Thank you.
Are there any other questions? I wanted to ask a short question, if I might. So you said it's a non-demolition detector, in the sense that you're having. So it works in a Geiger regime, right? Or in principle, you could also count photon with this.
I'm not sure. So it's non-demolition in the sense that essentially the incoming photons, if you want, arrives here, and it escapes at the end of the day in this channel at a different frequency, but in this sense, it is still available for measurement. So that's what we do here. So it's in this sense that it's non-demolition, but I'm not sure. So I'm not sure what you have in mind with this Geiger regime. Maybe I simply
it detects the presence of the photon, basically.
In the presence of the photon?
No, it detects that the photon is there, right?
Yes. Yes.
Okay.
Yeah.
Okay. So if there are no more questions, then thank you once again for the talk and the discussion.
Yeah, thanks for having me here. Thanks a lot.
Thank you. And the next speaker of this session is Valentina Parigi from LKB, who will talk about non-Gaussian quantum complex networks. So please, Valentina, if you could share your slides.
Yes. Can you see the slide?
Yep.
Can you hear me?
Yep. Yep.
Very
We
good.
hear you. We see the slides. So the floor is yours. Thank you.
So thank you so much. So thank you so much for having me here. Thank you for the organization of this workshop. Very interesting. And so I hope so. Also, thanks for the one that are here, the very last talk of the session. I will try not to be so long. That you have time to rest also before the poster session. And so also I'm lucky because actually I work in the very same group as Nicolas Trepp. So Nicolas already introduced many different concepts. So the physical concept has already been introduced. So I will go through again some of them in order to be sure that the context is clear on what I'm going to speak about, but I will speak about some different things then. So yes, today I'm going to speak about non-Gaussian quantum complex network. So here I have a pre-COVID picture, which is merged with two more picture of people arriving during the COVID time. So it's kind of a merging scale of what has been shown by Nicolas. And so here are the outline of my talk. So I will go through briefly the quantum complex network. So again, this is mainly my picture in which I'm working now, and but you will see that the physical concepts are really the same that Nicolas has been speaking about. And then I will concentrate more on the non-Gaussian part of what I'm doing, so which is the non-Gaussian cluster. And in particular, so I will go through the detection of ring negativity in a multimode cluster. So this is in a way also kind of a one of the possible answers to a question that Nicolas had in the previous talk, how you can characterize multimode non-Gaussian states in a more efficient way. And then I will go to benchmarking of complex of non-Gaussian cluster via complex network theory. So here it's a more theoretical problem. So when you can even go in the regime where, let's say experiment is not yet there actually, in the sense that you can have a large cluster with a lot of different non-Gaussian operation. How you can characterize this kind of states, it's not easy to benchmark. And then, well, one answer could be that we can use complex network tools for doing it. So very good. So let's start. So probably you already have seen this picture for the one that have had one of my talk in the last, let's say, 2-3 years. So I'm really interested now about complex networks. So when I speak about networks, what I have in mind is the picture of network theory. So complex network, any kind of object in which you can see nodes and links, and which is something in between being a regular network, in the sense that you have a deterministic rule for building it, and a random one, meaning that you have Merlino rule and it's totally probabilistic. So everything which is in between the two can be considered as complex networks. And complex network models are very interesting because they can describe real-world networks, so many different kinds of networks, social network, metabolic reaction, and of course, internet is a complex network that can be described as some of the complex network model that has been established. So they're classified via statistical property. Probability distribution, for example, of number of links is one of the main, so what is called the degree, which is often given. And from this property, you can characterize an emergent behavior like the small world community structure and corresponding functionalities to this network. So you can have networks that are more or less, for example, resilient to attack, for example. Very good. So the idea is to go quantum, meaning that, again, so you have object with node and links, but here nodes are quantum system. And link could be physical interaction or, for example, any kind of quantum correlation, like, for example, entanglement link. So these structures are interesting for me because can be used to simulate behavior of complex or quantum natural phenomena. And of course, they can be used to simulate kind of complex network structures you want to use in quantum communication and quantum information protocols. So the idea is that to develop theory and experiments for a continuous variable quantum complex network, and the kind of network that I have in mind so are the one in which nodes again are multi-modes, so different frequency temporal modes, like the one that Nicola has been shown before, and the kind of link are links that involve continuous variables. So it could be again physical interaction or quantum correlation, but we work in the continuous variable regime. So we're really interested about the continuous variable with these different modes. So of course, there is a quite typical kind of quantum network that has been evoked many times during this workshop already, which are cluster states, so in particular, continuous variable cluster state. And of course, actually, the graphical structure of a network is very important for cluster states. So you have an attention matrix that describe them, that gives you where actually you apply the CZ operation that builds the cluster state. Has been shown, so this cluster state can be approximated experimentally by using squeeze states and linear optics. So the basic, let's say, part of the network, if you just take the basic building blocks, if you just take two nodes and one link, well, this can be just built with two squeeze state that goes into a bin splitter. Or in an equivalent way, it can be built in a non-degenerate parametric process, which is more or less the picture that we have in mind in our group. So if you have a parametric process with a signalizer, you can directly get two modes squeeze state, which is mainly the basic building block of the cluster state. Of course, to build the larger cluster state, so the idea that you have many different squeeze modes that can undergo on different linear optic interaction, which are the one that choose, let's say, the shape of the class that you get at the end. And this again can be recast on multi-mode parametric non-conversion process meaning that we have a multicolor process because we have optical frequency combs, so we have many frequency entering the process. And the shape in this case, so the part of the linear optics is done by the measurement basis. So this is, I'm just recalling what Nicolas has told from a different point of view, a different picture, but is really exactly the same. So. What is very interesting in our case is that, as Nicolas told, it's quite easy to reshape the network, because maybe you can do it by just choosing the measurement basis in a multimodal modified detection. And it's not the only one thing that we can do. So so this I mean, the measurement basis for choosing the shape is what I call the linear process for choosing the basis that you can have a nonlinear process if you want it, is by changing the spectral shape of the pump of your process that can give you another degree of freedom in order to manipulate these states. So this again is what Nicolas have shown in the before in the experiment that we were speaking about. Different cluster state has been generated, and you can see that we can generate different shape and with a number of nodes that goes up to 12 for the moment involved in the experiment. And so Nicolas was showing a video of the experiment that put in picture of people that did the experiment. Again, you have pre-COVID and post and during COVID picture of people making stuff in the lab. Of course, also as has been evocated, actually, so we're not the only one doing cluster state, and of course there are experiments that go for larger states, especially the one of Ulrich and the one of Akira. I think he's also going to speak later on. And actually, we are not at the same points. Of course, here you have kind of cluster state that involve a million of nodes with also very particular structure that allow for measurement-based quantum computing. So the point is that I want to profit of the fact that we can really, I want to exploit the fact we can really shape the cluster easily in order to go towards cluster shape, complex shape of the cluster. And then I will go through why I think it is interesting. But of course, when you start to speak about complex network, with complex network people, well, they say, well, okay, if you have 20, or you can understand, if you have 20 modes, well, you can arrange as you want, but it's not so complex the shape that you can get from it. So of course, even for us, the idea is that it would be nice to have a larger cluster state. And actually, there is one more experiment that we have in the lab that is going through a larger number of modes. So the idea here is that we want to exploit both the spectral degree of freedom, so the spectral shape of our modes, but also include a kind of time beam configuration that corresponds to the pulses of our femtosecond laser. So the idea is that we go through a single pass squeezing configuration. So we have no more the cavity around the experiment. So we consider periodically pulled waveguides in order to increase the interaction and still keeping large value of squeezing, if the most recent results doesn't give very much large squeezing, but they're very preliminary results. And so the idea is that in this system, what we can get is that we have kind of multiplexing of the degree of freedom, because at each pulse, we can have a squeezing on different several spectral modes. And so this experiment has been done again with a femtosecond pulse laser source, which is around 800 nanometers, so very near infrared, and with a repetition rate on 153 megahertz and a pulse width of around 40 femtoseconds. So we have shorter pulses, larger spectrum length. So, And so we got some preliminary results from this experiment. So here is this single pass multimode squeezing. So you can see the experimental setup with a, so probably I can use pointer, yes. So here you can see the experimental setup with the periodically polled chip. So you have something like 30 waveguides, nonlinear waveguide on this chip. And you can see a picture here of the chip, which is a little bit, you have a zoom on the picture. And what we got is that we can have a measurement of something like about 14 squeeze modes with 0.6 dB of squeezing. So it's not very large, but we were able to measure these different modes for each time being. So at each pulse, we can measure squeezing for this 14 different spectral modes of light. So of course, what I'm showing here is what you get on a spectrum analyzer. So you cannot really see the fact that we are really sensitive to the single time beam, so the single pulse. So the idea is that, yes, I have to get out. Okay, probably. To convince about the fact that we can really measure pulse by pulse. So if you consider a very little portion of what we see in the spectrum analyzer for a given time that corresponds to squeezing, you can recover what an oscilloscope can see at the output of our homodyne detector. And here you can see that, for example, in 50 microseconds, you can have something like more than 7,000 pulses. So I can really zoom in order to see that we can really distinguish between different pulses. So you have the shape corresponding to different pulses on one photodiode of the homodyne detector, and then the homodyne signal that corresponds to each pulses. And so at the end of the day, we can recover this kind of picture. So this is the synchronization of the shape that we get while we are scanning the phase of the local oscillator on the spectrum analyzer. On the lower part, on the upper part, you get the value of different quadrature corresponding to different pulses. And we can recover exactly the same statistic that we can get directly from the spectrum analyzer in terms of squeezing. So we are very happy with these first results. Of course, the idea is that we want to improve the squeezing and the number of modes, the detection technique. So we're still working on our homodyne detector, which is a fast homodyne detector, so able to solve 100 pulses with 6 nanosecond distances. So I just want to show the picture of the 3 persons that did the work in the experiment that got these first preliminary results. And also I want to mention that we have a new setup that is coming at Telecom Wavelength that more or less is going to use the same kind of process in a single pass configuration. And if you want to know a little bit more about the theory, how to engineer the waveguides in this regime, you can look today at the poster of Victor that is going to present the post number 14, which is a work actually in collaboration with Lipsys. Actually, Victor worked in Lipsys and the people in Paderborn. Very good. So what we hope for the future is to get experimentally very large cluster that can be shaped in a complex way. So the question is why I'm interested in going through complex shape for cluster. Well, so there are many different things. One, the first is that it can be used for simulating structural quantum environments. So here, let's say I'm cheating a little bit because when I show this kind of picture, what I have in mind are network of harmonic oscillator with spring-like coupling. So it's not exactly cluster states, but they can be mapped on the very same experimental setup that we use for cluster state. So as far as you have Gaussian operation, you can find a way of mapping the multi-mode state to the one that we have in the experiment. So of course, a different kind of environment when you couple different systems give us different way of, different channel of dissipation that can be recast on what is called the spectral density environmental coupling. So the picture here shown, so the line is the theoretical calculation on given a particular shape of the environment, what is the spectral density environmental coupling. While the different dots are simulation or what we can get from our experimental setup, meaning that we can really recover the same kind of effects when we consider a bunch of mode of light that are recast in a complex environment, and then we couple them on a quantum system, which is again for us an harmonic oscillator. So these are numerical simulation based on the experimental details of our experiments. So the experiment is still going on. So the real experiment is ongoing, and Paul is working on getting the feature of this complex environment in the experimental setup. A second point that is interesting for going through a complex cluster is that we can consider them as a way to test routing protocol. So of course the idea is to test routing protocol for continuous variable networks. So we have studied so what we can get as a complex cluster in this regime. Of course, given the fact that normally you build graphs from experimental resource, so you have a certain distribution of squeezed mode of light, and then you use just linear optics in order to get the approximated cluster. And we have found how to optimize them given the linear optics and given the resource that we have. And also we have go through kind of quantum routing protocol. So the idea here is that in the multimode case, it's quite easy to get a large cluster with the shape that you want, and then you can distribute. And then you can rearrange, for example, you can distribute part of the network, the cluster, to Alice and part to the Bob, and then you want to rearrange your link. So for example, you just want to have a particular teleportation channel. And then the idea is to go there by using the most simple operation that you can do in continuous variable quantum optics. So at first you can just use linear optics operation in order to solve this problem. So the idea is that you allow Alice and Bob to just do linear optics operation on their side in order to go from this situation to the situation you have just one possible channel. And so we have played a little bit with it by starting with just, a basic shape, not really complex for the moment. And we have found condition, numerically, the condition where we can get this gain. So we have half of the cluster given to Alice, half of the cluster given to Bob, and try to see if we can rearrange in order to get a particular EPR channel on two nodes. And it's not always possible, depending on the shape of the classes. So this graph that we call Y is different from the fully connected. And we also got some kind of alternate configuration for a grid class. If you have double odd number of nodes, it's not the same as having double even number of nodes. And again, this is considering a case where you start from a squeeze state of light that's are experimentally given, and then you apply a linear optic operation. Of course, the idea is that we want to go to this kind of quantum routing also in complex networks. This is work in progress that we have now. And a work in progress that is quite finished, but not yet out, is to do routing also using measurements. So especially when you consider complex, so CV class, you can consider Y shortening or just removing some particular nodes and doing it with a particular combination or looking at a particular multipath scheme in order to get an advantage for example, for the entanglement concentration they can get in the EPR state at the end. Very good. So this is has been more or less the introduction on the idea of quantum complex networks, staying Gaussian. Now I go through the non-Gaussian part, so the non-Gaussian cluster. So as you know, what is interesting on Gaussian, of course, this is the topic of this workshop, and Nicolas already presented let's say the main experimental setup that we use in the lab for getting non-Gaussian states, which is by using some frequency generation in order to select the mode from which we want to subtract a single photon. This is not the only one that we are considering, so this scheme is going to be improved with the idea also to subtract more than one photon, and probably also to get photon addition that is mode dependent in the future. So I will start from it by probably repeating some of the things that Nicolas told, but that I mean are quite interesting to introduce what I want to present later on. So. As has been told, when if you have no click on the some frequency conversion, when nothing happened, and if you enter with a Gaussian state, you get out with a Gaussian state that can be fully characterized as far as you stay in the diagonal basis for the Hamiltonian, meaning that if you have the basis of a squeeze state, you can reconstruct the Wigner function. And of course, if you get a click with a gate that corresponds to a particular mode, you can get a negative Wigner function. So this is exactly the work that Nicolas has been shown before. And also, you can recast the thing by subtracting a photon from one node of a cluster. So again, recall that our cluster is just a combination of the linear combination of the modes that are diagonal from the Hamiltonian. So meaning that to subtract a photon from one of the nodes, you have to send a linear combination of this mode on the gate. And as Nicolas there are two things. The first is that if you subtract, for example, if you just consider the simple square graph, when you subtract from one node, so the maximum effect is on the other nodes, on the other corner. And the second point is that, so the characterization of this quantum state has been done by considering the excess kurtosis of each mode separately. No reconstruction of Wigner function has been done for this experiment because it's quite hard. It's quite hard if you consider the normal way of doing, of getting information about Wigner function, which is done via quantum tomography with maximum likelihood process. So here you have 4 modes, and it's already something that it's not possible in the sense that it's computationally too easy to solve for a maximal likelihood algorithm. Even if you, at first what is complicated is to directly get all the information that you need. So the experimental data, it's a very long process, and you have to be sure that your experiment is stable enough. But even if you get there, to get the maximal likelihood algorithm working, it's very hard. So this is one of the first challenges here that I'm going to tackle later on, which is how to get complete information on the non-Gaussian multimode quantum states, because actually multimode quantum tomography is hard in this regime. The second challenge is the classification of, theoretical classification of non-Gaussian multimode quantum states when you start to have large number of non-Gaussian operations there. So, and also here you see, again, I'm pointing out this case because as Nicolas told, so this case, if you just get into theory, is simple to explain why actually you get the maximal effect on the other corner. But imagine that you have a larger cluster, very complex, and then you should start to subtract even from a superposition of nodes. So, and then you have to look a little bit into the topology of this class. And also actually, if you go on the extreme regime where you can subtract many photons on a very large cluster, so we know that this is a scenario where you have the hardness of CV sampling, so this has been proved. But probably this is something in between that we can do, in the sense that we can try to classify these quantum states with some smart tool that is given by complex network theory. So I will start by going for the first challenge. So the first challenge is to get the complete information, so the Wigner negativity for multimode states, non-Gaussian. And so the answer that we have found is to use the use of neural networks. So, so this is a work that has been done in collaboration with Università Roma Tre, with Marco Barbieri, and especially actually the driving force of this work is Valeria Cimini, that did a lot of work. And actually, the question that we asked to our neural network is about the Wigner negativity. I have to say that we are not the first using neural network to get information from quantum state of light. So in particular here, I'm pointing out two different work on DV and CV regime. But both of them have been really used to get the quantum tomography of the state. So the idea is that you want to encode at least the space states into a neural network in order to get an efficient answer about quantum tomography. What we do here is to directly ask the neural network if our state has a negative Wigner function. So we don't go through the full reconstruction of the quantum states, but we just ask for the question that we want to answer. So how is the setting? So the idea is that we consider up to 10 mode states. So at the beginning, we have 10 squeeze modes that we can rearrange in any way. So meaning that, well, I'm just showing an actor shape, meaning that, I mean, they can undergo any linear optics operation. And then these states can undergo either nothing or a subtraction in any superposition of modes, or an addition on any superposition of modes. And then at the end of it, what you do is that you measure if you have 10 modes, you have 10 different homodyne measurements on 3 different phases, and you get 1,000, a statistical 1,000 quadrature for each. So this basis could be a totally different one. So it's not given that this is the one that is used, that correspond to the shape of the class, in the sense of not measuring. So this homodyne detection is not even is going to measure this node, can just measure a superposition of the nodes, and then this one, another superposition of any node, and so on. So this is repeat 4,000 times. So what is interesting in this scenario is that for up to 10 modes, we have the machinery that has been developed in the last year in our group, especially by Mattia Schatz, for simulating what is going on. So we have an analytical expression for the minimal value of Wigner function in these cases. So we can use the data that we have for training a neural network. So what we do is that each of the quadrature, each of the statistic of the quadrature measure is recast in 15 beans for each mode. They're given to different nodes in an input layer of a neural network. And then at the end, what we want to get is the answer. The Wigner is negative, yes or no. So the idea is that we use, so we have a kind of cross-validation procedure. We use as a training set 80% of the data, and then as the validation set 20% of the data. And then here you can see how the validation loss and the accuracy, so the first decrease and the second increase during the process. So here you have the published results for 3 different configurations, so considering 3, 5, and 10 modes. And so at that time, what we have demonstrated is that you can get something like 95% of accuracy for 3 modes, 90% for 5, and then something between 80 and 85 for 10. But I mean, we very recently were able to see that we can go farther, and even the one of 10 modes can increase up to 95% by adapting, for example, the binning that we choose here in our feeding of the network. Also, we tested the robustness with different classes of state, in the sense that we can use, so the classes of state that we use here is single photon added subtracted multimode squeeze state. But for example, you can use that for training and then try to validate actually by using, for example, Fox stakes. And it seems to work. So it seems to be a quite robust technique. Of course, it is really based on the fact that we are able to simulate numerically from the beginning and analytically the value of the Wigner function. But the fact that actually it's robust, even changing the quantum states that we used for testing, it seems that probably we can go beyond also for the 10 modes. For example, what we can do is try to simulate up to 10 modes, feed this value, and try to test something like multimode state of even mode. Of course, we did a comparison with the maximum likelihood. So here has been done by considering just 3 modes, which is the regime in which maximum likelihood can work. So the idea is that actually what we do with the maximum likelihood is to recast the density matrix on the Fock basis, and then getting the Wigner negativity from the parity operator. And so what is interesting is that, of course, when you have large number of measurements, maximum likelihood win is more accurate. But then what is interesting in our case, which is very interesting from the experimental point of view, is that the accuracy is really larger compared to maximum likelihood when you go to very low number of measurements. So here you go from 10 to 1,000, and we see that the 10 still, I mean, the method is quite robust, I mean, to tell us, quite good performance to tell us that the state is really negative or not. Okay, very good. And then I will go to the next part, to the next challenge, which is the classification, the theoretical classification of non-Gaussian multimode quantum states through complex network tools. So, well, again, here the answer is, so before was use neural network, here's the answer is to use complex network tools. So this is a work that has been done in collaboration with people at Colorado School of Mines, so Lincoln Carr and Bhuvanesh Sundar, that now moved to GILA. And so again, the idea is that these kind of states are not totally easy to benchmark. So I won't just start to debate to basis again. So what we do is to consider a graph, which is a cluster state, where we have a structure, which is the one of the imprinted network. So what we call the imprinted network is the graph of CZ gates that are imposed to this multimode state. So of course, there we already know that, so this picture doesn't tell everything. So of course, the Gaussian correlation between quadrature is known that go beyond the nearest neighbor. So Nicolas has been speaking a little bit about it. Also, we already did a lot of work. So again, Mattia did a lot of work on this regime by looking what is going on after photon subtraction on cluster states of regular shape, and especially by looking at a property, a local property, like for example, entanglement Wigner negativity. So when you do the operation of photon subtraction, so the correlation between quadrature go up to the second order, so the second neighbor. So this is what is happening also on entanglement Wigner negativity. They are reshaped, they are changed locally up to the second neighbor. But this is not the end of the story, because that, of course, I mean, what has been checked are regular cluster shape. So we would like to be also in the case of complex cluster shape. And the second point is that we would like to have an idea of what is going on quantum correlation between all the different nodes in the network. So look at 2-point correlation in all the nodes of the network. So we recast the general setting by considering an imprinted network, but allowing us to have complex network shape. For example, here I'm considering what is called Watt-Strogatz network, which is one of the model of a small world network. We consider 100 nodes, and then we look at what we call the emergent network. So we define a photon number correlation network in the multimode state, meaning that we look at any 2-point correlation between photon numbers. And then we rebuild an adjacency matrix of this emergent network starting from this property. So why we do it? Well, at first, because why we choose actually photon number correlation. First, because in principle, these are 2-point correlation that can be measured in principle in a quantum optics experiment. The second point is that they contain up to the third order moment. So they are sensitive to the non-Gaussian, let's say, properties of the state that we really want to understand how it changes when we consider, the single photon subtraction. So here I'm just showing the emergent photon number correlation of the very same network before photon subtraction. So of course you have more link. This is quite normal because, as I was telling before, actually the quadrature correlation go beyond just the first, the link that is given by the graphical structure of the class. And then we subtract up to 10 photons. So in this work, we started to subtract the photon locally. So we just keep subtracting the photon on the same nodes. And we can just choose either the highest connected node or a totally random node in the network. And then we look at the emergent photon number correlation, how it changes. So you can see that it's not exactly the same as in the case of Gaussian. And of course, if you're going to want to have some kind of statistical behavior, what we did is to repeat 100 times this procedure of network of 100 modes, and get statistic for degree and clustering, that are two network measures that normally are used to classify complex networks. So the degree is the number of link per nodes when you have adjacency metrics of 0, 1. So this is actually, we have weighted a network. And the clustering is normally in 0, 1 adjacency metrics. Normally you count as the number of triangle divided by the number of triplets. And then you get the statistics for this quantity. So this is what is the original one. So this is a typical degree statistic for Watt-Strogas network that I'm considering. And then this is the statistic of the emergent photon number correlation in the Gaussian case and in the non-Gaussian case. Well, you see that you have a little bump in the non-Gaussian cases. So the statistic is changed. The degree is increased. The average value of the degree is increasing. And you have this second bump. And then you can try to go a little bit more in detail. So what you can expect is that this bump come from the nodes that are closely related to the one from which you subtract the nodes. So you can expect that this comes totally from the nodes at distance 1. So we start to break up the statistic according to the distance from the subtraction node of the different nodes. So meaning that here I'm considering different subgraph. So the 1 is the subgraph of nodes that are at distance 1. The 2 is the subgraph of nodes that are distance 2, and then distance 3 from the points in which I'm doing the 10 photon subtraction. And you see that, well, of course, you have a huge bump that come from the node at distance 1, but not all of them contribute in the same way. So we started to look at it a little bit more into the statistic of this subgraph at distance 1. And then after a certain time, we discovered that the effect depends on the connectivity within the subgraph of the different nodes. So the nodes that are just connected to the node from which we subtract a photon, 10 photon, are very affected, let's say, in degree, while the one that have a lot of different connection with the other nodes in the same subgraph, well, actually are the one that they get actually the larger effect, the degree statistics. So the different group correspond to different connectivity with other nodes at the same distance. And this also explains why, for example, if you just consider a tree graph, or if you want is a Barabasi-Albert with parameter m equal 1, is one that seems to be less affected about it, because while you barely have node in the subgraph that they can have more than one connection. Also, actually, we tested different complex network model. So meaning that at the beginning, the imprinted network of CZ gates in the cluster structure is with adjacency matrix that corresponds to different network models. So this is, for example, again, is the Watt-Strogatz. So the Watt-Strogatz is built by starting from a regular network, and then you start to rewire the different connection, a different link, meaning that if you rewire, if the probability of rewiring is larger, you get a more random network. So it's something that could be really between a regular and a random network by just changing this rewiring probability. And then what we found, I found that the effect that is given statistically, for example, on the degree for the from the photon subtraction is larger, is the randomness is larger. The second classes that we have looked at are Barabasi-Albert network, that are the network go with the preferential attachment. So for example, these are the model that has been used, one of the models being used to describe the internet connection. And so these networks are characterized by, let's say, hubs, or community around a particular node. And then we can see a difference between the case in which we subtract from the highest connected node and the random node. And actually, the larger effect is subtracting from a random node. And this probably comes from the fact that the photon subtraction, let's say, as a finite power as, entanglement distillation. So of course, this correlation is like entanglement distillation correlation. And then of course, if the node from which you subtract is connected to many other nodes, like the hub, the effect that you get is diluted, let's say. While if you get a node randomly, it's quite probable that in the Barabasi-Albert network, you get something that is not connected to many other nodes. And then there actually, you can have a larger effect in terms of the correlation, how you're changing the correlation. So with this, I come to the end of this part. So what have been seen, by using these complex network tools for a large non-Gaussian cluster state, is that the photon subtraction profoundly changes the structure of correlation network when they're shaped as a complex network. So this comes from the fact also, of course, that in general, in complex network model, the distance between nodes is shorter in general than in regular network, meaning that you have a lot of, let's say, nodes that are close to the nodes that are the one from which we subtract the photon. Then we have seen that the amount of randomness and inhomogeneity of the complex network shape can change the effect of this emergent correlation network in photon subtraction. So different model can affect in different way actually the results that we get. And so we have kind of a general rule in the sense that in general, photon subtraction affect the bulk of the clustering degree distribution the same way. So meaning in a way you are increasing in any case the correlation by doing this operation. But the structure of the tails of this, statistical distribution of degree of clustering really depends on the complex network structure of the imprinted network. It can be really different. And also actually what we have seen is the importance of the local network structure around the subtraction points in order to look at this non-Gaussian property of our network. And actually with this, I thank for your attention.
Thank you very much, Valentina. So the talk is open for discussion. And I see that there is a question in Slido. So I will read the question and then let's hear the answer. So the question is, did I understand correctly that the cluster is realized from the SPO light with the help of linear optics? The light whose modes are initially squeezed but independent and have a different time profile. If you can comment on this.
So I'm not sure that I totally get the question, but actually, so the picture of linear optics is more, let's say, a picture to tell in general how, I mean, what is the effect of the measurement-based technique, in the sense that we decide the measurement basis in order to shape the different cluster shape. Then it depends on which part of the talk was referred to this question, actually. For example, for the moment, so in the experiment I was speaking about, in which we have time beam and frequency modes, we really are in the diagonal basis, meaning that we are just measuring squeezing. So we didn't build yet the cluster shape, regular or complex. Then actually, in the theoretical part, let's say, both for the mode that has been using for neural network and also for the non-Gaussian complex cluster, what we do actually in the theoretical mode is that we start with a bunch of multimode squeeze states. Then we apply any kind of linear optic operation, meaning that, I mean, you just change the correlation. You can see it as recasting any kind of cluster state shape. And then, of course, you can apply different operation in the sense that you can subtract a photon or add also a photon for the neural network case on any superposition of these nodes. And then you can measure on any superposition of, on a different superposition, meaning that you can apply linear optic transformation at any stage. So before doing the single photon subtraction, for example, and also before doing the homodyne detection. So theoretically, really, we can put basis chain everything. And this is in a way of being the most general as possible. That could also be a way of having more complexity. Because, of course, actually, the last part that I was showing concerned statistics we got by subtracting, keeping subtraction of one photon from a very particular node. But then if you start to subtract photon from superposition of nodes, well, there start to be a little bit harder to make calculation, but could be also the interesting part, because it's go towards this, let's say, hard to sample scenario.
Thank you. So to put the question simple, I also received some clarification in Zoom. What's actually in the nodes of those networks? Is this linear optical couplings?
So, so in general, actually, you have it's exactly the same experiment that Nicolas was showing, if you want, in the sense that you have different spectral temporal modes, and then according to which basis you detect this mode, you get different correlation between them, meaning that you build different clusters.
So it's defined also by the measurement.
Yes.
Okay.
Or you can change the spectral shape of the pump. They give you different correlation between different spectral temporal modes.
So by the pump shaping,
exactly,
you can affect this. Okay. Great. Any other questions? Please, Radim.
Yeah, maybe I have. I was thinking, did you ever try to play a bit with non-Gaussian random networks? Is there something what we can imagine in that way? Yeah,
non-Gaussian random. What do you mean with non-Gaussian random network? Just the fact that you have, I mean, random network and then you have non-Gaussian operation on it, or?
Yeah, that's one possibility, but maybe one could think about like a set of multiple Gaussian operations, which are random. And then they are randomly fed by Gaussian or non-Gaussian states, just maybe for simplicity by vacuum and Fox state 1. Then is there like any idea like how to investigate Gaussianity for such a
let's say
things? Because I feel when we like really, for example, fix the cluster states or any kind of specific states, then we sort of fix zero set measures of the states, and we investigate features of that. But in reality, yeah, we will not be exactly in that state. We will be a little bit off, and it might happen that our knowledge is just based on.
You're totally right. So actually, I mean, using the kind of cluster configuration is a way of let's say, visualizing what we are doing. Of course, we are not really building exact cluster state, especially experimentally. So the idea, for example, of the last part is that you can cast any kind of correlation. So could be, I mean, mutual information, could be steering that material is looking at, could be just entanglement correlation. I mean, it should be not really, I mean, the cluster structure in terms of Nurifier is not really what we are looking at. It's just a way of visualizing it. Then the fact of applying random non-Gaussian operation in a way is a little bit what we have done in the model of the neural network, in the sense that we can apply addition, subtraction in any combination of nodes. Of course, you can think also other kind of non-Gaussian operation, feeding Fox states or doing this kind of, this could be something that could be interesting to do. Yeah, I mean, there is a plethora of things that can be done. So actually, especially for the last part, meaning that the idea is that we wanted to start to use some complex network tools as a way of classifying what is going on a complex structure. But we really started from the very basic thing, in the sense that we consider the state that we are used to, by considering just photon subtraction and by just considering subtraction from one node. Of course, the idea is that we can have more complicated stuff, look at other, I mean, correlation that are, I mean, it's not, I mean, we decide to go for photon number correlation because it's just, I mean, if you go on the moments, is there, it is just beyond 2 in the sense that it's getting some information about the fact that you have a non-Gaussian state. But I mean, it's not really related to any kind of protocol. So for example, something that we are looking at this kind of state is to look at mutual information, how the Gaussian mutual information is modified by the non-Gaussian, let's say, feature, I mean, operation. On this nectar, for example, but I mean, could be many different. So actually, this kind of statistical tool for complex network, we are not the only one using it. Huh? So there, and we start to have kind of a bunch of, especially theoretical groups that are interested in it. Mainly, most on the DV side, actually, continuous variable. I mean, is mainly us with our collaborators, so, which are more or less around the world. But I mean. And the idea is that you can use for many different structure. I mean, you can have, I mean, mainly you can have kind of, for example, spin structure to look at, I mean, quantum phase transition too, with this kind of, I mean, of complex network tool on mutual information, for example, or entanglement correlation. And it's quite rich, I mean, class of tool that you can use for very different kind of system. But of course, actually applying random non-Gaussian operation could be really interesting. It's something that we would like to do too.
Yeah, because I really wonder if you have like a sufficiently large network in general of non-Gaussian, with non-Gaussian features, whether it's rather like that we have to measure more or less all modes in the network to realize the non-Gaussian feature, or it's more frequent that we can measure just a small part and see that quantum non-Gaussian feature, because I a little bit feel that losses, they can easily turn to noise in such networks, and noise is very destructive for these quantum non-Gaussian features. It means I a little bit guess that the trouble could be that we maybe have to measure more or less everything to realize that quantum non-Gaussian aspects in that complex networks are present. Yeah.
Could be. So here, for example, what we do, so I mean, from which actually we have this kind of network structure that you do, I mean, you look at 2 by 2, I mean, correlation. You don't really measure the correlation of, I mean, let's say multi-mode correlation, but you just measure 2 by 2. And you can already get some kind of nice feature there to understand what is going on. And for example, actually we have colleague that just did it for kind of, let's say, spin model, I mean, complex spin model system in order to follow actually is going on. I mean, what is going on with entanglement. So they call it kind of 2 by 2 tomography. By looking at the entanglements in 2 by 2, I mean, configuration. And then you can do statistics with this, and then try to get some.
With continuous, especially with continuous variable entanglement, this will be maybe understandable, because this is something like all these Gaussian continuous variable states. They are kind of like how WV states, how GAZ states. They have always these features that entanglement is somehow spread between the nodes, and we can figure out that. But the non-Gaussian, at least my personal experience, is quite bad.
Well, the idea is that
you have to really collect a lot of information from these modes to
of course, actually. So this is based on the fact that we have to do some numerics. I mean, this is quite as usual. It is also for complex network tools, of course. But I mean, if you just do the numeric and you don't have tools to interpret the numerics, I mean, it doesn't help. And that's, I mean, this kind of statistical interpretation has been done in complex network theory for a long time. I think there we can get some. Actually, you get the intuition of what is going on. Then, of course, I mean, if you want to look at the particular, information, a particular feature, you have to go a little bit closer. So, for example, I mean, we look at this bump and we didn't understand, I mean, well, okay, we have this bump, from where it comes. So you start to have some kind of intuition how things are going by looking at the statistical distribution. And then you go closer. And then, of course, actually, we were considering a case in which you know that you have an operation which is local. So it's not going to affect, 1 million of nodes in the cluster. But you start to understand what is going on by looking at the statistic, and then you can recast your statistical picture there. So it's so sorry, probably we are getting longer in discussion.
Yeah. We will continue at some point for sure. Thank you.
Thank you very much.
Yeah, especially as we have two more questions in Slido. So first one is, can you clarify what you mean by Gaussian correlations being greater than nearest neighbor? Is this only for the non-Gaussian clusters or also for the standard ones? If for the standard ones, why do not see it in the graph structure?
Actually, so no, it's also for the Gaussian one. So this is more or less what I wanted to look with this picture. So when you have the graphical structure of the cluster, it just tells you where you apply the CZ gate. But then the application of the CZ gate actually create correlation up to the second step. So I mean, this node is correlated to this node, but it's correlated also to this node, and then doesn't go beyond. And this is actually, I mean, again, by looking at network tool, you can try to recast actually, for example, the covariance matrices in the Gaussian case give you all the correlation you can get, and then you can see that actually you see appearing actually the square of the adjacency matrix of the graph. And then there, I mean, this is exactly the number of two-path, gives you the number of two-path, or path of distance 2 between different nodes. So you see that you go up to the second step in correlation. So this is known actually in the structure of the graph. And then, I mean, you get more when you go to the non-Gaussian cases actually.
Thank you. And there's another question. Could the advantage of neural network for low number of measurement mean that there is some unknown theoretical tool more powerful than maximum likelihood?
Could be. I don't know. Actually, yes. Yeah. The problem with neural network is that they work, and then I mean it's a little bit hard to directly get information. But in a way, also it depends on what you're asking, because what we discovered, and for the moment we just did numerical testing, is that actually we are not feeding the network with correlation between the different modes. In the sense that we made measurements of 10 modes that could be whatever, I mean, any combination of modes, but one by one. So normally maximum likelihood also you consider different correlation with the different. And actually it seems that for Wigner negativity, this doesn't count. And we tried hard, probably we didn't find, but we tried to feed with some states that we know that the correlation play a role. I mean, even how the Wigner negativity is distributed, for example, between different nodes. But it seems not to be, affected by these. So it seems that actually correlation between different modes is not an information that you need, which is an information you normally you use for the maximum likelihood for the full tomographic reconstruction. So probably, yes, there is some kind of, I mean, also witness, I don't know what, that can be used, that is, I mean, if you just want to ask for Wigner negativity, so the question is, the state has a Wigner negativity or not? It's not about how much it is. So probably there is some kind of different witness that can be used. So max Wick is not the best, could be, yeah, for sure.
Yeah. Thank you very much. Okay, I don't see more questions to be resolved on Slido. If there are no, any questions in the audience still? Okay, seems to be not the case. So thank you very much, Valentina, for the talk and the discussion, and thank to all the speakers in the afternoon session. And we conclude with that. I will continue tomorrow. Thank you very much. I think, Peter,
yeah,
you have an announcement to make? Okay.
Yeah, well, not really an announcement. I'd just like to say that, as Ladislav said, thanks to all the speakers, and this concludes the public section of our workshop for today. So to our YouTube watchers, I'd like to say goodbye, and we'll see you tomorrow. And with everyone else, we'll see each other after a short break on the poster section. So goodbye for now.